Langchain Community Vector Stores VDMS client. VDMS is a vector database that can be used with LangChain to store and retrieve embeddings. It provides a powerful way to manage and search large amounts of data in a highly efficient manner. VDMS allows you to store and retrieve embeddings, which are numerical representations of text data. This enables you to perform semantic search, where you can search for documents based on their meaning rather than just their keywords. Inputs. Text data can be any type of text, such as articles, blog posts, emails, or documents. LangChain can convert this text into embeddings that represent the meaning of the text. Embeddings. These are numerical representations of text data that capture the meaning of the text. They are used by VDMS to store and search for documents based on their semantic similarity. Outputs. Retrieved documents. When you search for a specific query using the VDMS client, it retrieves the documents that are most similar to your query based on their embeddings. Steps. Create a connection to the VDMS database. Establish a connection to the VDMS database using the VDMS client library. This step involves providing the necessary credentials, such as your application programming interface key, to authenticate and connect to the database. Upload your data to VDMS. Upload the text data you want to store in the database. The data can be in any format, such as plain text files or JSON documents. VDMS will process the data and convert it into embeddings, which are then stored in the database. Use the VDMS client to search for embeddings in the database. Query the database for embeddings that are most similar to your search query. The client uses the embeddings of the query to find the closest matches in the database based on semantic similarity. Prerequisites. VDMS account. Obtain a VDMS account from the VDMS website to access the platform and its features. This account provides you with the necessary credentials to interact with the VDMS database and manage your data. VDMS application programming interface key. This is a unique identifier that allows your application to access the VDMS database. You can obtain this key from the VDMS settings after creating an account. It is essential for authentication and authorization purposes when connecting to the database. Fine-tune parameters. Search parameters. These parameters are used to refine the search process and ensure that you retrieve relevant results. For example, you can adjust the distance threshold or specify the number of results to return. Query parameters. These parameters are used to define the specific characteristics of your search query. For example, you can use these parameters to specify the language of the query, the type of documents to search, or the specific fields to search within the documents. Challenges and fixes. Error connecting to VDMS. This error can occur if there is a problem with your connection to the VDMS database. To resolve this issue, verify that the VDMS application programming interface key you provided is correct and that your connection settings are properly configured. Check for any network connectivity issues or firewall restrictions that might be preventing you from connecting to the database. Upload error. This error can occur if there is a problem with the format of the data you are uploading. Make sure that your data is in a compatible format and follows the guidelines specified by VDMS. You may need to pre-process the data or convert it into a supported format before uploading it to the database. Search results not relevant. If the search results are not relevant to your query, you can refine your search parameters to improve the accuracy of the results. Experiment with different distance thresholds, query parameters, and search criteria to find the best settings for your specific use case. You can also try using different embedding models or modifying the query itself to ensure that it captures the desired meaning. Summary of LangChain Experimental Agents. Agent Toolkit. CSV Base. Create CSV Agent. This tool, Create CSV Agent, allows users to create an agent that can access information stored in a comma-separated value CSV file. Inputs: the path to the CSV file containing the data that the agent will access. For instance, if the CSV file is named data.csv and is located in the data folder, the input would be datadata.csv. Outputs: the CSV agent itself. This agent will have the capability of accessing information from the specified CSV file, performing queries, and providing relevant answers. Steps: loading the data from the CSV file using a suitable CSV reader library. This involves parsing the CSV file's format and extracting the data into a usable format for the agent. Using the Create CSV Agent function to create a new agent object. The function will take the loaded data and configure the agent with the ability to interact with the CSV data. Prerequisites: the LangChain library needs to be installed and accessible in your Python environment. This library provides the necessary functionalities to create and interact with agents. Fine-tune parameters: the complete path to the CSV file. This parameter allows the tool to correctly locate and access the CSV data. The desired type of agent: this could be a basic agent, a knowledge-based agent, or any other type depending on the specific requirements and capabilities of the agent. Challenges and fixes: the process of reading data from a CSV file, which may have different formats, encodings, and data structures. The solution involves utilizing a CSV reader library to handle the complexities of reading CSV files. The creation of the CSV agent itself. This might require configuring the agent with the correct settings and parameters to ensure it functions correctly with the CSV data. The solution is to utilize the Create CSV Agent function, which is specifically designed for creating agents that can access information from CSV files. The function will handle the necessary configurations and setup. LangChain Community Vector Stores VDMS Embedding 2 bytes summarized. This component converts an embedding to a byte string. An embedding is a vector of numbers that represents the meaning of a piece of text. This embedding can be used to find similar text or to perform other tasks. For example, you could use an embedding to find other documents that are similar to a given document. This embedding can be stored in a database and can be retrieved later for comparison. The conversion to bytes is necessary for storing and retrieving the embedding from the database. Inputs: embedding is a vector of numbers that represents the meaning of a piece of text. It is the result of an embedding model, which is a machine learning model trained to map text to numbers. This embedding can be used to find similar text or to perform other tasks. For example, you could use an embedding to find other documents that are similar to a given document. You can use various embeddings such as sentence transformers or OpenAI embeddings. Outputs: bytes are a sequence of 8-bit values that represent data. This byte string is the representation of the embedding, which can be stored and retrieved later. For example, you can store this byte string in a database and then retrieve it later for comparison. Steps: converting embedding to bytes involves taking the embedding, which is a vector of numbers, and converting it to a sequence of 8-bit values. This is done by using a standard encoding, such as the UTF-8 encoding. The resulting byte string can then be stored and retrieved later. Prerequisites. The VDMS Vector Database Management System library needs to be installed. VDMS is a library that is used to manage vector databases, which are databases that store and retrieve vectors. You can install VDMS by running pip install VDMS in your terminal. Fine-tune parameters. There are no fine-tuning parameters for this component. This is because the component is simply converting an embedding to bytes, and there is no need to adjust the conversion process. Challenges and fixes. Challenge 1. The embedding may be invalid. For example, the embedding may not be a valid vector, or it may be too large to be converted to bytes. Fixes to challenge 1. You can check if the embedding is valid by checking its type and size. You can also check if the embedding is too large to be converted to bytes. If the embedding is too large, you can try to reduce its size or use a different encoding. Challenge 2. The resulting bytes may not be valid. For example, the bytes may not be in the correct format, or they may be corrupted. Fixes to challenge 2. You can check if the bytes are valid by checking their format and size. You can also check if the bytes are corrupted by comparing them to the original embedding. If the bytes are corrupted, you can try to regenerate them or use a different encoding. Langchain Experimental Agents Agent Toolkits Pandas Base Create Pandas Data Frame Agent. This agent toolkit provides functionality to create a Pandas data frame from given data. It uses the Pandas library, a powerful tool for data manipulation and analysis in Python. Inputs. The input data to create the data frame. This data can be in various formats like lists, dictionaries, or even external data sources. For example, you could provide a list of customer names and their corresponding purchase amounts. The column names for the data frame. These names should match the structure of the provided data and represent the different categories or attributes of your data. For instance, if you are working with customer data, the column names could be customer name, purchase amount, and purchase date. Outputs. A Pandas data frame, which is a two-dimensional data structure. It represents data in a tabular format with rows and columns, making it easy to analyze and manipulate data. Steps. The agent first retrieves the input data from the user or from a specified source. This data is then processed and prepared for creating the data frame. The agent converts the input data into a list format. This ensures that the data is structured in a way that is compatible with Pandas data frames. The agent uses the converted list data and the provided column names to create the Pandas data frame. This step combines the data and the structure to build the final data frame. Prerequisites. The Pandas library needs to be installed on your system. You can install it using the command pip install pandas. Pandas provides the core functionalities for creating and working with data frames in Python. The LangChain library needs to be installed as well. LangChain provides the framework for integrating different components and tools like pandas into a larger workflow for data processing and analysis. Fine-tune parameters. This agent toolkit does not require any fine-tuning parameters. It is designed to be a general-purpose tool for creating data frames from various data sources. Challenges and fixes. One challenge might be that the data type of the input data does not match the expected type for the data frame. For instance, you might have strings representing numbers, which need to be converted to numeric data types. To address this, you can use type conversion functions provided by pandas to convert the data to the appropriate types. This ensures that the data is stored and manipulated correctly within the data frame. Another challenge could be providing incorrect column names that do not match the structure or they number of columns in the input data. To resolve this, you need to carefully check the provided column names and ensure they align with the data. If the names are incorrect, you need to provide the correct names to create a valid data frame. langchainexperimental, agents, agent toolkits.csv, base, create CSV agent. A detailed description of the function create CSV agent, which is part of the langchainexperimental, agents, agent toolkits.csv, base module. This function facilitates the creation of a CSV agent, a specialized agent designed to interact with and process data from comma-separated value CSV files. Inputs: the path to the CSV file that the agent will interact with. This path could be a local file system path or a remote path accessible through a network protocol, like HTTP or FTP. The prompt, or set of instructions, that will be given to the CSV agent. This prompt guides the agent's behavior and specifies what actions it should take on the CSV data. It could be a question, a request to perform a specific task, or a combination of both. Outputs: the CSV agent itself. This is a specialized agent capable of understanding and processing data from CSV files. It can be used to perform a variety of tasks like extracting data, analyzing trends, or generating reports based on the CSV file's contents. Steps: the first step in creating a CSV agent is reading the CSV file. This involves accessing the specified file path and loading the CSV data into memory. This step might require dealing with different CSV file formats and handling any potential errors that could occur during the file reading process. Once the CSV data has been loaded, the next step is to create the CSV agent. This involves configuring the agent with the necessary tools and settings, such as the prompt and any relevant parameters. The agent might also be initialized with a specific language model, depending on the intended use case. Prerequisites: the CSV tool, a specialized tool from the langchainexperimental, agents, agent toolkits.csv, base module, is necessary for interacting with the CSV data. This tool provides the functionality to read, write, and manipulate CSV files. A language model LM from the LangChain LLMS module is required. The LM is used to understand and process the prompt and generate appropriate responses based on the CSV data. The LM could be a powerful language model like GPT-3 or a simpler model tailored for specific tasks. Fine-tune parameters. The CSV tool parameter is used to specify the specific tool that will be used for interacting with the CSV file. This allows users to choose a tool that best suits their needs, whether it's a basic tool for simple CSV manipulation or a more advanced tool for handling complex CSV structures. Challenges and fixes. One potential challenge is that the CSV file might be too large to fit in memory. This could happen if the CSV file contains millions of rows or has a very complex structure. The solution to this challenge is to use a tool that can handle large CSV files. These tools might employ techniques like chunking or streaming to process the CSV data in smaller segments, avoiding memory overload. Another challenge is that the CSV file might not be properly formatted. This could involve missing or inconsistent data, incorrect delimiters, or other formatting issues. The solution is to use a tool that can handle poorly formatted CSV files. These tools might be able to identify and correct errors in the CSV data, or provide mechanisms for handling missing or inconsistent data, allowing for more robust and reliable processing. Langchain experimental agents agent toolkits Xorbits base create Xorbits agent. A function that creates an Xorbits agent. Xorbits is a tool for building agents that can interact with the world, such as a simple chatbot that can answer questions about the weather. This agent can be customized with different tools and large language models. Inputs. A large language model (LLM) is a type of artificial intelligence model that is trained on a massive amount of text data and can generate text, translate languages, write different kinds of creative content, and answer your questions in an informative way. For example, GPT-3 is a well-known LLM that can be used to create chatbots. A list of tools that the Xorbits agent will use to interact with the world. These tools could include web search, API access, or other functions that allow the agent to get information or perform actions. For example, if the agent needs to get the current weather, the tool could be a weather API. Outputs. The function returns an Xorbits agent. This agent can then be used to interact with the world and complete tasks. Steps. First, the function will instantiate an Xorbits agent. This is the basic structure of the agent that will be used to interact with the world. Next, the function will set the agent to use the provided tools. This will allow the agent to access the tools and use them to complete tasks. Finally, the function will set the agent to use the provided LLM. This will allow the agent to generate text and use its knowledge to complete tasks. Prerequisites. Install the necessary packages to use the Xorbits agent. This can be done using the pip package manager. Pip install langchain Xorbits. Import the necessary classes from the langchain experimental agents and langchain experimental agents agent toolkits modules to create and use the Xorbits agent. From langchain experimental agents import toolkits. From langchain experimental agents agent toolkits import Xorbits. Fine-tune parameters. The agent's max iterations parameter can be set to limit the number of iterations for each run of the agent. This parameter helps to prevent the agent from getting stuck in an infinite loop and helps to control the complexity of the agent's tasks. The agent's max execution time parameter can be set to limit the time of each run of the agent. This parameter helps to prevent the agent from running for too long and helps to control the resources used by the agent. Challenges and fixes. The agent may not be able to complete the task due to insufficient context. The LLM may not have enough information about the task or the world to complete the task. Increase the context window of the LLM. This will allow the LLM to access more information and may help to improve the agent's performance. The agent may be stuck in an infinite loop. This can happen if the agent is unable to complete a task or if the agent is given a task that is too complex. Increase the max iterations or max execution time parameters. This will allow the agent to run for longer and may help to prevent the agent from getting stuck in an infinite loop. Summary of langchain experimental agents agent toolkits Xorbits base create Xorbits agent. This function creates an Xorbits agent, a powerful tool for building intelligent agents that can interact with the real world using specified tools and configuration. Inputs. A list of tools that the agent can utilize, such as an application programming interface API to access external data or a search engine to retrieve relevant information. A dictionary containing configuration settings for the agent, including parameters like the agent's name, its memory capacity, and the specific instructions that guide its behavior. Outputs. An instance of an Xorbits agent that is ready to be used for tasks like question answering. information retrieval, or even creative writing. Steps. The function first initializes an Zobits agent instance using the provided tools and configuration. It then configures the agent's policy for how it uses these tools, such as which tools to use for different situations and in what order to utilize them. Prerequisites. The LangChain experimental package must be installed in the environment where this function is used. This package can be installed using the pip package manager with the following command: pip install langchain experimental. The Zobits server needs to be running for the agent to function correctly. You can start the Zobits server using the command xobits server start. Fine-tune parameters. Tool names: a list of the names of tools that will be available to the agent. These names must correspond to the actual tools defined in the agent's environment. For example, you might have a tool named Search that performs web searches and another named Calculator for basic calculations. Configure a dictionary containing various configuration settings that influence the agent's behavior. This could include parameters like the maximum number of steps the agent can take in performing a task, or the specific instructions that guide the agent in its decision-making process. Challenges and fixes. If the Zobits server is not running, the agent will not be able to connect to it and will fail to function. You can resolve this by starting the Zobits server using the command xobits server start. If the tool names or configuration settings are incorrect or invalid, the agent might not work as expected. To fix this, carefully verify the tool names and configuration settings against the Zobits documentation. Ensure that the tool names are correct, that they match the actual tools defined in the agent's environment, and that the configuration settings are within the expected ranges and formats. LangChain experimental, agents, agent toolkits, Python, base. Create Python agent summary. None. This function creates a Python agent that uses LangChain tools to execute Python code. This means the agent can leverage external tools and libraries to interact with the world, making it more versatile and powerful than a simple text-based agent. The function to be executed by the agent, which is the core piece of code that the agent will try to execute. This function defines the specific task that the agent is meant to accomplish. The tools that the agent can use are external utilities that provide the agent with capabilities beyond basic Python code execution. These could include tools like making API requests, interacting with databases, or accessing file systems. LangChain provides a library of tools that can be readily integrated with the agent. The language model to use is the underlying AI component that powers the agent. This model is responsible for understanding the user's input, generating code, and interacting with the tools. Popular options include OpenAI's GPT models. The agent type specifies the specific type of agent that will be created. Different agent types have different strengths and weaknesses, such as a conversational agent designed for dialogue-based interactions, or a tool using agent designed for task-oriented execution. The verbose flag controls how much information the agent outputs during its operation. Setting this to true will provide more detailed logging, which can be useful for debugging or understanding the agent's reasoning process. The max iterations is a limit on the number of attempts the agent will make to execute the function. This prevents the agent from running indefinitely in cases where it might get stuck in a loop. The max execution time is a limit on the amount of time the agent is allowed to spend executing a function. This prevents the agent from consuming excessive resources or taking too long to complete a task. The starting memory is a data structure that the agent starts with to keep track of its state and Context. This can be used to store intermediate results, user input, or other relevant information that can help the agent complete its tasks more effectively. The callbacks are functions that are executed at specific points during the agent's operation. These can be used for logging, monitoring, or controlling the agent's behavior. The agent executor is the component that manages the execution of the agent. It handles the interaction with the language model, the tools, and the execution of the provided function. The agent executor quarks are additional parameters that can be passed to the agent executor to customize its behavior. A Python agent that can execute Python code, equipped with the tools and capabilities defined in the input parameters. This agent is a self-contained entity that can be used to perform a variety of tasks based on the provided function and tools. The function that the user wants the agent to execute is passed to the agent. This function might be provided as code, or as a natural language description that the language model will then translate into code. The tools that the agent can use are passed to the agent. This allows the agent to access information, perform actions, or manipulate data using external resources. The language model to use is passed to the agent. This is the core AI component that will be responsible for the agent's reasoning, planning, and code generation. The agent type is passed to the agent. This determines the specific type of agent that will be created and how it will interact with the world. The verbose flag is passed to the agent, which controls how much information is output during the agent's operation. This can be useful for debugging or understanding the agent's internal reasoning. The max iterations is passed to the agent, which sets a limit on the number of attempts the agent will make to execute the function. This helps prevent the agent from getting stuck in an infinite loop. The max execution time is passed to the agent, which sets a limit on the amount of time the agent is allowed to spend executing the function. This helps prevent the agent from consuming excessive resources or taking too long to complete a task. The starting memory is passed to the agent, which is a data structure that the agent uses to keep track of its state and context. This can be used to store intermediate results, user input, or other relevant information that can help the agent complete its tasks more effectively. The callbacks are passed to the agent, which are functions that are executed at specific points during the agent's operation. These can be used for logging, monitoring, or controlling the agent's behavior. The agent executor is passed to the agent, which is the component that manages the execution of the agent. It handles the interaction with the language model, the tools, and the execution of the provided function. The agent executor quarks are passed to the agent, which are additional parameters that can be passed to the agent executor to customize its behavior. Python 3.7 or higher is required for the LangChain library to function correctly. Install LangChain using the pip package manager. Bash pip install langchain. A language model is needed to power the agent's reasoning and code generation capabilities. Popular options include OpenAI's GPT models, which can be accessed through their Application Programming Interface API. To use OpenAI's GPT models, you will need an API key, which can be obtained by signing up for an OpenAI account. Tools to be used by the agent are necessary for the agent to interact with the world beyond simple Python code execution. LangChain provides a library of tools that can be readily integrated with the agent. Or you can create your own custom tools to suit your specific needs. The function to be executed by the agent can be adjusted to change the specific task that the agent is meant to accomplish. This could involve modifying the logic of the function or changing the inputs and outputs that it uses. The tools that the agent can use can be customized to fit the requirements of the specific task. This could involve adding new tools, removing existing tools, or changing the way that the tools are used by the agent. The language model to use can be switched to a different model with different capabilities or performance characteristics. This could involve using a different model from the same provider, or exploring models from other providers. The agent type can be changed to create an agent with different strengths and weaknesses. For example, you could choose a conversational agent for dialogue-based interactions or a tool using agent for task-oriented execution. The verbose flag can be set to true or false to control how much information the agent outputs during its operation. This can be useful for debugging or understanding the agent's internal reasoning. The max iterations can be adjusted to set a limit on the number of attempts the agent will make to execute the function. This helps prevent the agent from getting stuck in an infinite loop. The max execution time can be adjusted to set a limit on the amount of time the agent is allowed to spend executing the function. This helps prevent the agent from consuming excessive resources or taking too long to complete a task. The starting memory can be customized to provide the agent with different initial information or context. This could involve adding specific data, changing the structure of the memory, or using different types of memory. The callbacks can be modified to customize the behavior of the agent during its execution. This could involve adding new callbacks, removing existing callbacks, or changing the logic of the callbacks. The agent executor can be changed to use a different execution strategy. This could involve using a different underlying library or implementing a custom executor. The agent executor quarks can be adjusted to fine-tune the behavior of the agent executor. This could involve changing parameters that control the interaction with the language model, the tools, or the execution of the provided function. The agent may not be able to execute the function correctly due to errors in the code, mismatches between the function and the tools, or limitations in the language model's understanding of the function. To resolve these issues, carefully check the function code and ensure that it is correctly written and compatible with the tools that the agent is using. Also, make sure that the language model is capable of understanding the function and generating appropriate code to execute it. The agent may not be able to use the tools correctly due to errors in the tool definitions, misunderstandings about how to use the tools, or limitations in the language model's ability to reason about the tools. To address these issues, carefully check the tools and their documentation to ensure that they are correctly defined and understood by the agent. Also, make sure that the language model is capable of reasoning about the tools and using them appropriately. The agent may not be able to use the language model correctly due to misunderstandings about the model's capabilities, limitations in the model's ability to understand the user's intentions, or errors in the way the model is being used. To address these issues, carefully check the language model documentation and understand its capabilities and limitations. Also, make sure that the user's input is clear and unambiguous, and that the model is being used in a way that is consistent with its intended purpose. The agent may not be able to handle errors correctly due to missing or inadequate error handling mechanisms, misunderstandings about the potential errors that might occur, or limitations in the language model's ability to reason about errors. To address these issues, carefully check the error handling code and ensure that it is comprehensive and robust also. Make sure that the language model is capable of understanding the potential errors that might occur in generating appropriate code to handle them. Summary of LangChain Experimental Agents. Agent Toolkits. Zorbits Base. Create Zorbits Agent. An agent that leverages the capabilities of Zorbits to interact with the physical world. Zorbits is a platform that allows you to create agents that can interact with the real world through physical devices. This agent utilizes Zorbits to bridge the gap between the digital and physical domains, enabling automation and control of real-world processes. Inputs. An application programming interface key used to authenticate and authorize access to the Zorbits platform. It serves as a unique identifier and security credential for the agent to communicate with the Zorbits API. Outputs. A programmatically defined agent that can execute actions and interact with the physical environment through Zorbits. The agent's behavior and capabilities are governed by its configuration and the permissions granted by the Zorbits platform. Steps. Initialize the Zorbits agent by creating an instance of the agent class provided by the Zorbits SDK. This step involves setting up the basic structure and configuration of the agent, including its name and any initial settings. Configure the agent by providing the required application programming interface key, ensuring the agent can connect to the Zorbits platform and access its resources. This step involves associating the agent with a specific Zorbits account and granting it appropriate permissions. Define the agent's capabilities by specifying the specific actions and interactions it can perform in the real world. This involves defining the agent's allowed functionalities, such as controlling physical devices, accessing sensor data, or interacting with the Zorbits platform's services. Prerequisites. A valid application programming interface key is essential for the agent to access the Zorbits platform. This key should be obtained from your Zorbits account and stored securely. Your Zorbits API key. The Zorbits Software Development Kit SDK is a collection of libraries and tools that provide the necessary functionality to interact with the Zorbits platform. It enables you to create, configure, and manage Zorbits agents within your applications. Pip install Zorbits. Fine-tune parameters. A descriptive name that uniquely identifies the agent within your Zorbits environment. This name should clearly reflect the agent's purpose and functionality. A detailed description that explains the agent's intended use case and capabilities. This description should provide context and clarity for understanding the agent's purpose and behavior. Specific actions and interactions the agent is authorized to perform in the real world. Defining its capabilities and limitations. This includes specifying the physical devices the agent can control, the sensors it can access, and the services it can utilize on the Zorbits platform. Challenges and fixes. Ensure the agent has a valid application programming interface key and is connected to a stable network. Verify the API key's validity and check your network connection for any issues. Ensure that you have a valid API key and that your network is connected. Access the Zorbits dashboard and review the agent's permissions, granting necessary privileges for the agent to interact with the desired resources. Verify that the agent has been granted the appropriate permissions to control the specific physical devices or services it requires. Grant the agent the necessary permissions in the Zorbits dashboard. Thoroughly review the agent's code and configuration to identify any errors or inconsistencies that might be preventing it from functioning as expected. Ensure the agent's capabilities are accurately defined and consistent with its intended behavior. Review the agent's code and configuration. Make sure that the agent's capabilities are defined correctly. Summary of LangChain Experimental Agents Agent Toolkit CSV Base creates CSV agent. This agent is a LangChain tool that can be used to create a CSV agent. A CSV agent can be used to access and analyze data from a comma-separated values CSV file. Inputs. Path to the CSV file. This is the location on your computer where the CSV file is stored. For example, it might be a path like C users John documents my data.csv or home John documents my data.csv. Outputs. This tool creates a CSV agent, which is a tool that can be used to perform various operations on a CSV file. These operations can include extracting data from the file, filtering data based on specific criteria, and performing calculations on the data. Steps. Read the CSV file into memory using the appropriate libraries. This involves parsing the file contents and understanding the data structure within it, often with the help of libraries like pandas. Create a CSV agent using the LangChain framework. This involves configuring the agent to utilize the CSV data you've loaded. This may involve defining how the agent can interact with the data, what questions it can answer, and what actions it can perform. Prerequisites. The LangChain library needs to be installed. LangChain is a framework for building powerful language models and agents. To install LangChain, use the following command in your terminal: pip install langchain. The pandas library needs to be installed. Pandas is a powerful Python library for data analysis and manipulation. To install pandas, use the following command in your terminal: pip install pandas. Fine-tune parameters. The CSV path parameter specifies the path to the CSV file you want to use. For example, this might be C users John documents my data.csv. The delimiter parameter specifies the character that separates the values in the CSV file. The most common delimiter is a comma, but other delimiters are possible, like a semicolon or a tab T. Challenges and fixes. If the CSV file is not found, make sure that the path specified in the CSV path parameter is correct. This includes verifying the file name and location. If the CSV file is not readable, check the file format. Make sure the file is a valid CSV file and not corrupted. You can also try opening the file in a text editor to inspect its contents and see if there are any issues. If the delimiter is not specified, the agent might not be able to properly interpret the data in the CSV file. You can specify the delimiter using the delimiter parameter. For example, if the CSV file uses a semicolon as a delimiter, you would specify delimiter in your agent configuration. LangChain Experimental Autonomous Agents. LangChain Experimental Autonomous Agents is a framework for constructing artificial intelligence (AI) agents that can independently finish tasks by utilizing tools and language models. These agents are designed to operate without direct human intervention, leveraging their knowledge and capabilities to accomplish given objectives. Inputs. A natural language description of the task that the AI agent is expected to complete. This input serves as the initial instruction for the agent, outlining the goal and desired outcome. Optional context or additional information related to the task. This can include relevant background information, constraints, or any specific details that could aid the agent in understanding the task and achieving its objective. Outputs. The completed task, often presented as a specific output or an action taken by the agent. This output represents the result of the agent's efforts to fulfill the task description, showcasing the outcome of its autonomous actions. Optional log of the agent's reasoning and actions. This detailed log provides insights into the agent's internal thought processes and decision making. During task execution, it outlines the steps taken, the rationale behind each step, and any challenges encountered along the way, offering transparency and understanding of the agent's behavior. Steps. Agent receives task input. The agent begins its task by receiving the initial input, which provides the instructions and context for its actions. Agent passes input and identifies tools or information needed. The agent analyzes the received task input, identifying any relevant tools or information sources required to complete the task effectively. This step involves understanding the task's requirements and matching them to available resources. Agent interacts with tools or information sources. Based on the identified tools and information sources, the agent interacts with them to gather the necessary data or execute the required actions. This step involves engaging with external resources, such as application programming interfaces (APIs), databases, or online services, to retrieve relevant information or complete specific operations. Agent generates output based on gathered information. After gathering the necessary information and completing the required interactions with tools, the agent synthesizes its findings and generates the final output for the task. This involves processing the acquired information, drawing conclusions, and producing the desired outcome according to the task description. Agent logs its reasoning and actions. Throughout the entire process, the agent keeps a log of its reasoning and actions. This log documents the agent's thought process, including the steps taken, the reasoning behind each step, and any encountered challenges or decisions made. This log provides valuable insights into the agent's behavior and facilitates debugging or understanding its decision-making process. Prerequisites. Knowledge of LangChain, including tools and language models. A fundamental understanding of LangChain, a framework for building applications powered by language models, is essential. This includes familiarity with the available tools and language models within the LangChain ecosystem, allowing for informed selection and utilization of these resources by the AI agent. Basic understanding of AI agent concepts. A basic understanding of AI agent concepts is crucial for comprehending the functionalities and limitations of autonomous agents. This involves familiarity with key concepts like goal-oriented behavior, environment interaction, and decision-making processes, enabling effective design and evaluation of AI agents. Fine-tune parameters. Agent's memory and reasoning abilities. This parameter refers to the agent's capacity to retain and recall information over time, influencing its ability to learn from past experiences and apply acquired knowledge to new situations. It also encompasses the agent's ability to reason logically and draw conclusions based on available information, impacting its decision-making process. Agent's tool selection and usage strategies. This parameter involves the agent's ability to select and effectively utilize the appropriate tools for a given task. It encompasses the agent's understanding of the capabilities and limitations of different tools, allowing it to make informed decisions regarding tool selection and application. Challenges and fixes. Agent getting stuck in infinite loops or failing to converge on a solution. This challenge arises when the agent's actions repeatedly lead to the same state without reaching a desired outcome. A potential fix involves implementing timeout mechanisms, which limit the agent's execution time for a specific task. Introducing task completion criteria provides clear goals for the agent to achieve, guiding it toward a successful conclusion. Agent choosing incorrect tools or making inefficient decisions. This challenge occurs when the agent selects inappropriate tools or takes actions that are not optimal for the task at hand. Addressing this challenge requires refining the agent's tool selection strategies, incorporating better reasoning capabilities to evaluate tool efficacy, and leveraging more comprehensive training data to improve its decision making. Agent not being able to handle unforeseen situations. This challenge arises when the agent encounters unexpected situations or events that were not explicitly included in its training data. Designing robust error handling mechanisms allows the agent to gracefully handle unexpected situations, preventing task failure. Training the agent on a wider range of scenarios, including diverse and unexpected situations, equips it with greater adaptability and resilience in handling unforeseen circumstances. Summary of LangChain Experimental Autonomous Agents AutoGPT Output Parser Base AutoGPT Output Parser. This parser is designed to interpret the output generated by AutoGPT, a powerful tool that leverages language models to automate tasks. AutoGPT utilizes a combination of natural language processing and code execution to perform actions. In the real world, the output from AutoGPT, which typically includes both textual descriptions and code snippets, is processed by the base AutoGPT output parser to extract meaningful information and determine the next steps in the automation process. Inputs. Tool code: the code generated by AutoGPT, which represents an action or task to be performed. Intermediate steps: a record of the actions already executed by AutoGPT, providing context for the current step. Outputs. Final output: the final result of the executed code or action, presented in a user-friendly format. Next action: the action to be taken next based on the analysis of the current output and previous actions. Steps. Parse output: the parser analyzes the raw output from AutoGPT, identifying relevant information such as code snippets, textual descriptions, and potential errors. Extract tool code: the code generated by AutoGPT is extracted and analyzed to determine the type of action being requested. Determine next action based on the extracted code and the context provided by the intermediate steps. The parser determines the next appropriate action. Prerequisites. Tool code format: the code generated by AutoGPT must adhere to a specific format, typically Python code. This format ensures that the parser can accurately interpret and execute the code. Action format: the actions performed by AutoGPT are predefined and consistent. This standardization allows for the parser to anticipate and interpret the actions based on the code generated. Fine-tune parameters. Tool code regex: a regular expression used to identify and extract the code from the output. The tool code regex can be fine-tuned to match the specific code format used by AutoGPT. Action regex: a regular expression used to identify and extract the actions from the output. The action regex can be fine-tuned to match the specific action format used by AutoGPT. Challenges and fixes. Unrecognized tool code: if the parser encounters code that doesn't match the expected format or is not recognized, it will default to a predefined action. This ensures that the automation process continues even when encountering unexpected code. Invalid action: if the parser encounters an action that is not valid or cannot be executed, it will reevaluate the code and potentially attempt to generate a new action based on the context. This allows for error handling and recovery during the automation process. A summary of AutoGPT agent in LangChain. NaN. A comprehensive description of the AutoGPT agent within LangChain. A powerful tool for building autonomous agents. AutoGPT is an experimental agent designed to leverage the capabilities of AutoGPT for complex and goal-oriented tasks. Inputs: a clear and well-defined goal or objective that the agent should accomplish. For instance, write a blog post about the benefits of using LangChain for building autonomous agents. Optional contextual information or starting point for the agent. This could include existing research on the topic, relevant articles, or specific requirements for the goal. Outputs: a series of actions and outputs generated by the agent towards the specified goal. These outputs could include code, text, or other relevant information. For example, the agent could generate a Python script to scrape relevant data, draft a blog post outline, and then create the final blog post content. An evaluation of the agent's performance and effectiveness in achieving the goal. This evaluation could include metrics such as the accuracy of the generated content, the time taken to complete the task, and the overall success in meeting the stated goal. Steps: the agent receives the goal and any initial context. This could be provided through user input or by reading from a file. The agent breaks down the goal into smaller, manageable tasks. This helps to simplify the problem and make it easier for the agent to solve. For example, the agent could break down the blog post writing task into subtasks like data gathering, research, outlining, writing, and editing. The agent uses a language model to generate code, text, or other outputs relevant to the current task. This could involve using the language model to generate Python code for data scraping, write the blog post outline, or even create the final blog post content. The agent executes the generated code or instructions. This step ensures that the agent can take concrete actions and move towards achieving the goal. For example, the agent could execute the Python script to scrape data, then use the scraped data to generate the blog post outline. The agent evaluates the results of each task and iteratively refines its approach. This feedback loop allows the agent to learn from its mistakes and improve its performance over time. For example, if the generated blog post outline is not satisfactory, the agent could reevaluate its approach, adjust the language model's parameters, or seek additional context to improve the output. The agent repeats steps 35 until the goal is achieved or a termination condition is met. The agent could continue to generate code, execute tasks, and refine its approach until it has successfully written the blog post or until it reaches a predefined time limit or other termination criteria. Prerequisites: access to a powerful language model, e.g., GPT-4. This requires an API key from OpenAI for accessing their GPT models or a suitable model from Hugging Face. A suitable programming environment for code execution. This could be Python, Node, JS, or another suitable language with access to libraries and frameworks for interacting with language models and executing code. Fine-tune parameters. Agent's memory size and persistence. This refers to the amount of information the agent can store and retain over time. A larger memory allows the agent to remember more context and improve its reasoning abilities. Level of creativity and risk-taking in code generation. This parameter allows the user to control how creative and experimental the agent's code generation is. A higher level of creativity could lead to more innovative solutions, while a lower level emphasizes more conventional and reliable approaches. Constraints and safety guidelines for code execution. This parameter allows the user to define limitations and safeguards for the agent's code execution. This could include restrictions on accessing sensitive data, limits on the amount of resources the agent can consume, or specific safety checks to prevent the execution of harmful or malicious code. Challenges and fixes. Agent may get stuck in a loop or fail to progress towards the goal. This could happen if the goal is poorly defined, the agent lacks sufficient context, or the agent encounters unforeseen challenges. To address this, the user could reevaluate the goal, provide more specific instructions, or introduce external feedback mechanisms to guide the agent's progress. Agent may generate incorrect or unsafe code. This could occur if the language model is not adequately trained, the agent has limited context, or it lacks robust code verification steps. To mitigate this, the user could implement code verification steps, provide clear safety guidelines, and use a robust code execution environment that includes security checks and safeguards. Agent may encounter limitations in its knowledge or abilities. This could be due to the limitations of the language model, the availability of external data sources, or the lack of specialized tools and APIs. To address these challenges, the user could provide access to external data sources, integrate specialized tools and APIs, and allow for human intervention when necessary to augment the agent's capabilities. AutoGPT action summarization. An action that AutoGPT can perform. This action is used by the output parser to transform the output of a large language model (LLM) into a format that AutoGPT can understand and carry out. Inputs. The output of an LLM or another tool, which is processed into an AutoGPT action. For instance, if an LLM suggests opening a website or running a command, this output would need to be passed into a format that AutoGPT can utilize. Outputs. An AutoGPT action object, which can be executed by the AutoGPT agent. This object essentially represents a specific action, like opening a web page or sending an email. Steps. Analyze the output from the LLM using the output parser. This step involves breaking down the LLM's output into meaningful components that can be understood by AutoGPT. Transform the parsed output into an AutoGPT action object. This entails converting the LLM's output into a structured format that AutoGPT can readily execute. Perform the action defined by the AutoGPT action object. This is the final step where AutoGPT takes the action based on the parsed and structured information from the LLM. Prerequisites. The LLM output must be in a format that can be converted into an AutoGPT action. This means the output must be structured in a way that can be easily understood and parsed. A suitable output parser must be available for the specific LLM used. The parser must be able to interpret the LLM's output format and translate it into a format that AutoGPT can utilize. Fine-tune parameters. Action type specifies the type of action that needs to be performed. Examples include opening a URL, sending an email, or executing a command. Action input. The input data required for the action. This could be a URL for a web page, the recipient's email address, or the command to be executed. Challenges and fixes. Challenge. The LLM output might not be formatted in a way that can be directly converted into an AutoGPT action. For example, the LLM's output may be unstructured or use a different format than what AutoGPT expects. Fixes. Adjust the output parser to handle the LLM's specific output format. This might involve modifying the parser's logic or rules to recognize and process the unique format of the LLM's output. Challenge. The generated AutoGPT action object may not be executed correctly. For instance, There could be errors in the action's definition, such as incorrect URLs, email addresses, or command syntax. Fixes. Debug the AutoGPT action object in the execution logic. This may involve inspecting the object's properties, verifying the accuracy of the input data, and testing the execution process to identify and fix any errors. Summary of LangChain Experimental Autonomous Agents Baby Aji. This text describes the Baby Aji agent, an experimental autonomous agent. The agent is designed to complete tasks in a goal-driven manner, meaning it focuses on accomplishing a specific objective. Baby Aji utilizes various tools and steps to achieve this, aiming to be an effective task completion agent. Inputs. The Baby Aji agent takes a goal or task as input. This task could be anything from writing a poem to summarizing a research paper. The agent then uses its capabilities to break down the task into smaller, manageable subtasks and ultimately complete the goal. Outputs. The output of the Baby Aji agent is a set of completed tasks. Each task is a subtask that contributes to achieving the original goal. By completing these subtasks, the agent effectively fulfills the overall goal or task. Steps. The first step of the Baby Aji agent involves breaking down the given task into smaller, more manageable subtasks. This step ensures that the agent can tackle the task in a systematic and organized way, improving its chances of success. Once the task is broken down into subtasks, the Baby Aji agent prioritizes these subtasks. This prioritization helps ensure that the agent focuses on the most important tasks first, leading to an efficient and focused approach to task completion. After prioritizing subtasks, the Baby Aji agent executes each subtask using a tool. The tools used can range from APIs, which allow the agent to interact with other applications and services, to scripts, which are small programs that automate specific actions. The final step in the Baby Aji agent process is reviewing the results of each completed subtask and iterating based on the outcome. The agent can learn from its experiences and adjust its approach to improve its efficiency and effectiveness. Prerequisites. The Baby Aji agent relies on a large language model (LLM) as a core component. LLMs are advanced AI systems trained on vast amounts of text data, enabling them to understand and generate human-like text. Popular examples of LLMs used with Baby Aji include OpenAI's GPT-3 and Google's Palm 2. In addition to an LLM, the Baby Aji agent requires a set of tools to execute tasks. These tools could include application programming interfaces (APIs) that allow the agent to interact with other services, or scripts, which are small programs designed to automate specific actions. The tools chosen depend on the nature of the tasks the agent is designed to complete. Fine-tune parameters. The choice of the LLM used in the Baby Aji agent is a critical parameter that influences its performance and capabilities. Different LLMs have different strengths and weaknesses, and selecting the right one is essential for optimizing the agent's ability to perform the desired tasks. The tools used by the Baby Aji agent are also an essential factor determining its performance. Choosing the right tools ensures that the agent has the necessary resources to complete its assigned tasks effectively. Challenges and fixes. One of the challenges faced by the Baby Aji agent is difficulty in understanding the initial goal. This can be addressed by redefining the goal in simpler terms, breaking it down into smaller, more easily understood parts. Another challenge is limited memory of past tasks. This can be overcome by using a memory to store previous tasks. This memory can help the agent learn from past experiences and make more informed decisions in the future. The Baby AG agent may struggle to handle complex tasks. This can be mitigated by breaking down complex tasks into simpler ones. This approach allows the agent to tackle each component separately, ultimately making the complex task more manageable. The Baby AG agent may lack context awareness. Providing more context to the LLM can help address this challenge. By providing additional information about the task and its surroundings, the agent can better understand the context and perform tasks more effectively. LangChain Experimental Autonomous Agents Baby AG Task Creation Chain. Task creation chain is a crucial component of Baby AG, an innovative framework that empowers the creation of autonomous agents. It plays a pivotal role in driving the agent's continuous progress by generating new tasks based on the outcomes of previously completed tasks. Imagine a virtual assistant tasked with researching a new product for a business. The task creation chain would analyze the results of the initial research tasks, such as gathering market data or competitor analysis, and then generate follow-up tasks like compare features of similar products or identify potential target audience groups. This iterative process allows the agent to adapt and refine its actions based on evolving information. Inputs. The task creation chain requires two main inputs to function effectively. The first is a dictionary that encapsulates the results of the preceding task. This dictionary acts as a repository of information gleaned from the previous action, providing context for the creation of new tasks. For instance, if the previous task was search for articles about artificial intelligence, the results dictionary might contain the URLs of relevant articles, their titles, and key excerpts. The second input is a string representing the overarching goal of the agent. This goal acts as a guiding principle for the task creation chain, ensuring that the generated tasks are aligned with the agent's intended outcome. In the example of a virtual assistant tasked with researching a new product, the goal string might be conduct a comprehensive market analysis for a new smartphone. Outputs. The output of the task creation chain is a list of new tasks that are ready to be added to the agent's task queue. These tasks represent the next steps in the agent's journey towards achieving its goal. In the context of the smartphone research example, the output might include tasks like analyze customer reviews of existing smartphones or identify potential marketing channels for the new product. Steps. At the heart of the task creation chain lies a language model that possesses the ability to comprehend and generate natural language text. This model first analyzes the results of the previous task, extracting relevant information that will inform the creation of new tasks. In the case of a virtual assistant analyzing articles about artificial intelligence, the language model might identify key themes, emerging trends, and specific technologies discussed in the articles. Once the language model has identified relevant information, it then leverages another language model to generate new tasks based on the extracted data and the agent's overarching goal. This process involves the model understanding the agent's goal and decomposing it into a series of smaller, more manageable tasks. In our example, the model might generate tasks like compare the features of different AI models or investigate the potential impact of AI on various industries. Prerequisites. A fundamental prerequisite for the task creation chain is the presence of a language model that can effectively understand and generate natural language text. This model serves as the foundation for the chain's ability to extract information and generate new tasks. The language model should be capable of performing tasks such as text summarization, sentiment analysis, and question answering. Fine-tune parameters. The task creation chain can be fine-tuned to generate tasks that are more specific or more general, depending on the needs of the agent and the complexity of the goal. This fine-tuning process involves adjusting the parameters of the language models used within a chain to influence the types of tasks that are generated. For example, if the agent is working on a complex project with many subtasks, the task creation chain can be fine-tuned to generate more specific tasks, breaking down the overarching goal into smaller, more manageable steps. Conversely, if the agent is working on a simpler task, the task creation chain can be fine-tuned to generate more general tasks, providing a high-level overview of the next steps. Challenges and fixes. Challenge 1. One potential challenge associated with the task creation chain is that it may generate tasks that are not directly relevant to the agent's current goal. This can happen when the language model misinterprets the extracted information or fails to fully understand the agent's overarching goal. For instance, in the smartphone research example, the task creation chain might generate a task like research the history of mobile phones even though this task might not be directly relevant to the current goal of analyzing the market for a new smartphone. Fixes to challenge 1. This challenge can be addressed by fine-tuning the task creation chain to ensure that it generates more relevant tasks. This fine-tuning process involves providing the language model with more context and training data that is specifically tailored to the agent's goal. For example, the model could be trained on a dataset of tasks that are relevant to the smartphone industry, which would help it to better understand the context and generate more relevant tasks. Challenge 2. Another challenge is that the task creation chain may generate tasks that are either too complex or too simple for the agent to complete. This can occur if the language model does not accurately assess the agent's capabilities or the complexity of the task. For instance, the task creation chain might generate a task like conduct a comprehensive analysis of global smartphone markets for an agent that is only capable of performing simple web searches. Fixes to challenge 2. This challenge can be addressed by fine-tuning the task creation chain to generate tasks that are appropriate for the agent's capabilities. This fine-tuning process involves providing the language model with information about the agent's capabilities and limitations. For example, the model could be trained on a dataset of tasks that the agent has successfully completed in the past, which would help it to understand the agent's abilities and generate tasks that are within its reach. Elaborated description of task creation chain in Baby AGI framework. The task execution chain is a component within the Baby AGI framework, responsible for carrying out specific tasks based on given instructions. It acts as the operational core, translating instructions into actionable steps and executing them using appropriate tools and chains. Inputs. Task instructions. This refers to the detailed instructions provided to the task execution chain. These instructions define the specific task to be executed, outlining the desired outcome and any relevant context. For instance, an instruction might be research the top 5 restaurants in New York City and summarize their reviews, clearly outlining the goal and scope of the task. Intermediate steps. This represents the list of steps already completed during the execution of a larger task. This allows the task execution chain to maintain context and efficiently manage a sequence of steps within a broader workflow. For example, if a task involves gathering information from multiple sources, This list would track which sources have already been consulted, preventing redundancy. Outputs. Output. This is the result of executing the task. It can be any form of data, depending on the nature of the task. For example, it could be a summary of restaurant reviews, a list of contacts, or a generated creative text. Intermediate steps. This is the updated list of completed steps, reflecting the progress made during the task execution. It ensures that the chain keeps track of its progress and avoids repeating steps. Continuing the restaurant review example. This output would include the updated list of sources consulted, reflecting the completion of the current step. Steps. 1. Pass the task instructions into a list of individual steps. This involves breaking down the overall task into a series of smaller, more manageable steps. For example, the task research the top 5 restaurants in New York City and summarize their reviews could be broken down into steps such as identify top 5 restaurants in New York City, gather reviews for each restaurant, and summarize the gathered reviews. 2. Identify the current step that needs to be executed. This involves determining which step in the list of past steps should be executed next. The task execution chain uses the list of intermediate steps to determine which step is yet to be completed and requires execution. 3. Execute the current step using the appropriate tool or chain once the current step is identified. The task execution chain selects and utilizes the appropriate tool or chain to carry out the step. This could involve using a search engine to gather information, an API to interact with external services, or a language model to generate content. 4. Update the list of completed steps after executing the current step. The task execution chain updates the list of completed steps, marking the just executed step as complete. This ensures the chain maintains a record of its progress, enabling it to move efficiently through subsequent steps. 5. Return the output of the task execution and the updated list of steps. Finally, the task execution chain returns the output of the executed step, providing the results of the task, along with the updated list of completed steps. This allows the chain to communicate its progress and output to higher-level processes or agents. Prerequisites. LangChain. LangChain is a powerful Python library specifically designed for working with language models (LMs). It provides a framework for building applications that utilize LMs, offering functionalities for data access, model interaction, and chain creation. For example, using LangChain, you could build a system that uses a language model to analyze documents, extract information, and generate summaries. Task instructions. For the task execution chain to function effectively, clear and concise task instructions are crucial. These instructions guide the chain, defining the specific task to be executed, its desired outcome, and any relevant context. For instance, an instruction could be write a short story about a robot who falls in love with a human, clearly outlining the task and its desired outcome. Fine-tune parameters. Tools. This parameter defines the list of tools that the task execution chain can utilize during task execution. Tools could include search engines like Google Search for gathering information, APIs for accessing external data, or even custom-built tools for specific functionalities. Having a diverse set of tools allows the task execution chain to handle a wider range of tasks efficiently. Chains. This parameter specifies the list of chains that the task execution chain can utilize during task execution. Chains, in the context of LangChain, are a sequence of components designed to execute a specific task. For example, a chain could involve retrieving information from a database, processing it with a language model, and then formatting the output for presentation. Having a variety of chains allows the task execution chain to adapt to different task requirements and leverage predefined workflows for specific operations. Challenges and fixes. Challenge 1. The task instructions may be ambiguous or incomplete. Ambiguity and incompleteness in task instructions can hinder the task execution chain's ability to correctly understand and execute the task. For instance, a task instruction like write a story without further context or specifications leaves room for interpretation and can lead to undesired results. Fixes to challenge 1. To address this challenge, it's essential to provide clear, concise, and unambiguous task instructions. The instructions should explicitly define the task, desired outcome, and any relevant context. For example, instead of write a story, a clearer instruction could be write a short story about a robot who falls in love with a human, set in a futuristic city. This eliminates ambiguity and provides the necessary context for the task execution chain to correctly understand and execute the task. Challenge 2. The tools or chains may not be able to execute the task properly. The task execution chain relies on tools and chains to carry out specific steps. However, these tools and chains may not always be perfectly equipped to handle all task requirements. For instance, a tool designed for simple text generation might struggle with complex tasks involving data analysis or logical reasoning. Fixes to challenge 2. To mitigate this challenge, it's crucial to select tools and chains that are appropriate for the specific task at hand. This involves carefully considering the task requirements and choosing tools and chains that have the capabilities to execute the task effectively. If no existing tool or chain is suitable, developing custom tools or chains tailored to the task-specific needs can provide the necessary functionality. Langchainexperimental, autonomous agents, Baby AGI, task prioritization chain. A chain that prioritizes tasks based on their importance and urgency. The importance and urgency are determined by an underlying language model, which assigns weights to each task based on the specified criteria. For instance, a task requiring immediate completion might be assigned a high urgency weight, while a task with significant impact on long-term goals could receive a high importance weight. This chain is particularly useful when dealing with a large number of tasks, as it allows for the efficient allocation of resources and attention. Inputs: a list of tasks that need to be prioritized. Each task is represented as a string, which can be a description of the task, a title, or a brief summary of the task's objective. For example, a list of tasks for a project manager could include draft a project proposal, schedule a team meeting, and finalize budget allocation. Outputs: a prioritized list of tasks, sorted based on their importance and urgency. The chain outputs a list of strings, where each string represents a task. The tasks are ordered in descending order of priority, with the most important and urgent tasks appearing at the top of the list. This prioritization helps the user focus on the most crucial tasks first, ensuring efficient task completion and improved productivity. Steps: the chain uses a language model to assess the importance and urgency of each task. The language model analyzes the text description of each task and assigns scores for its importance and urgency. These scores are determined by the model's understanding of the task's context, its impact on the overall goals, and its time sensitivity. This process involves extracting key information from the task descriptions and utilizing the model's knowledge of language and task management principles to determine the relative importance. and urgency of each task. The chain ranks the tasks based on their importance and urgency. The ranking algorithm typically assigns a weighted score to each task, considering both the importance score and urgency score. The weights can be adjusted based on the specific requirements of the user and the context of the tasks. For example, in a critical situation, the urgency weight might be increased, giving priority to tasks with immediate deadlines. The tasks are then sorted in descending order based on their weighted scores, resulting in a prioritized list of tasks. This prioritization process ensures that the most important and urgent tasks are tackled first, maximizing efficiency and productivity. Prerequisites: a list of tasks to be prioritized. This is the input to the chain, and it's essential for the chain to function. The tasks can be provided in any format that allows for clear identification and description. Fine-tune parameters. Importance weight. This parameter determines the relative weight assigned to the importance score of each task. A higher importance weight indicates that the importance of the task plays a greater role in determining its priority. For instance, a higher importance weight might be used in scenarios where strategic goals and long-term impact are paramount. Urgency weight. This parameter controls the weight assigned to the urgency score of each task. A higher urgency weight signifies that the task's deadline and time sensitivity are more influential in determining its priority. This parameter might be increased in situations where immediate action is required or time constraints are critical. Challenges and fixes. The language model may not be able to accurately assess the importance and urgency of all tasks. For instance, the model might struggle with subjective tasks where the importance and urgency are based on individual perspectives or complex, nuanced information. To address this challenge, the language model can be fine-tuned on a dataset of tasks and their corresponding importance and urgency. This dataset can be manually curated or generated using a combination of expert input and crowdsourcing techniques. By training the model on a diverse set of task examples, the model can learn to better understand the context and nuances associated with different task types, improving its ability to accurately assess importance and urgency. The ranking algorithm may not be optimal. The ranking algorithm is a critical component of the task prioritization chain, as it determines the final ordering of tasks based on their assigned weights. However, different ranking algorithms have different strengths and weaknesses, and the optimal algorithm may vary depending on the specific context and requirements. To overcome this challenge, different ranking algorithms can be experimented with to identify the most suitable option for a particular task set. This process might involve comparing the performance of different algorithms on benchmark datasets, or testing them on real-world task sets to evaluate their effectiveness in different scenarios. Experimentation with various algorithms can help optimize the prioritization process and ensure that the most relevant tasks are prioritized effectively. Langchain experimental, autonomous agents, Baby AGI, task prioritization chain. Task prioritization chain is a component of Baby AGI, an autonomous agent framework. It prioritizes a list of tasks based on their urgency and importance. This chain uses a combination of task analysis, scoring, and sorting to determine the optimal order for completing tasks. Inputs: a list of tasks that need to be completed. For example, do laundry, write a report, and schedule meeting. The current context related to the tasks. For instance, laundry is due tomorrow, report is due next week, and meeting is scheduled for next week provides context for the tasks. Outputs: a prioritized list of tasks. For example, do laundry, schedule meeting, and write a report could be the prioritized list of tasks based on the urgency and importance. Steps: analyze each task in the list for urgency and importance based on the provided context. For example, do laundry is urgent based on the context that laundry is due tomorrow. Score each task based on urgency and importance, assigning a higher score to more urgent and important tasks. Sort the tasks in descending order of scores, resulting in a prioritized list of tasks. Prerequisites: a list of tasks that need to be completed. Do laundry. This task refers to washing and drying clothes. Write a report. This task refers to creating a written document summarizing a topic or providing information. Schedule meeting. This task refers to planning a meeting with one or more individuals. Current context that provides additional information related to the tasks. Laundry is due tomorrow. This indicates that laundry needs to be done urgently as it is due the next day. Report is due next week. This indicates that the report is less urgent than laundry, as it is due next week. Meeting is scheduled for next week. This provides information about the meeting's timing, which is relevant for scheduling purposes. Fine-tune parameters. Urgency weight. This parameter allows for tuning the relative importance of urgency in the scoring system. Importance weight. This parameter allows for tuning the relative importance of importance in the scoring system. Challenges and fixes. Handling ambiguous tasks. Sometimes the tasks might not be clear. Clarify tasks with user. Engage with the user to get further information on the tasks and ensure clarity. For example, if the task is send email, the user can be asked about the content of the email and the recipient. Use a language model to infer intent. Use a language model like GPT-3 to interpret the task and infer its intended meaning. For example, if the task is make a reservation, the language model can infer that it refers to making a reservation for a restaurant or a hotel. Determining task importance. Assessing the relative importance of different tasks can be tricky. Use a task scoring model. Develop a scoring model that assigns points based on various factors like deadlines, consequences of not completing the task, and alignment with goals. Use a language model to assess importance. Use a language model to evaluate the importance of tasks based on the provided context and any external knowledge. For instance, if the task is research a topic, the language model could determine the importance of the task by analyzing its relevance to current projects or goals. LangChain experimental autonomous agents. Hugging GPT response generator. Response generation chain. This YAML file describes the LangChain experimental autonomous agents Hugging GPT response generator. Response generation chain, which is a chain that uses Hugging GPT as the response generator. It takes in a prompt and generates a response using Hugging GPT. Inputs: a textual input to be processed by the Hugging GPT instance to generate the response. For example, a question, a statement, or a request. Outputs: the text generated by the Hugging GPT instance in response to the prompt. For example, an answer to the question, a response to the statement, or a fulfillment of the request. Steps: creates a Hugging GPT instance. Hugging GPT is a large language model (LLM) that is designed to be used for dialogue applications. The instance will be used to process the prompt and generate the response. Passes the prompt to the Hugging GPT instance. The prompt is the input text that the Hugging GPT instance will use to generate the response. Generates the response. The Hugging GPT instance processes the prompt and generates the response. The response is the output text that is returned by the Hugging GPT instance. Prerequisites. Hugging GPT is a large language model that is designed to be used for dialogue. Applications. It is trained on a massive dataset of text and code, and can be used to generate text, translate languages, write different kinds of creative content, and answer your questions in an informative way. For example, if you ask Hugging GPT what is the capital of France, it will respond Paris. Langchain is a framework for building and deploying LLM applications. Langchain provides a set of tools and libraries that make it easy to integrate LLMs into your applications. For example, you can use Langchain to build a chatbot that uses Hugging GPT to generate responses to user queries. Fine-tune parameters. The name of the language model to be used for response generation. For example, GPT 3.5 Turbo. The temperature parameter controls the randomness of the generated text. A higher temperature value will result in more creative and unpredictable responses, while a lower temperature value will result in more predictable and consistent responses. For example, if you set the temperature to 0.5, the responses will be more consistent with the prompt, while if you set the temperature to 1.0, the responses will be more creative and unpredictable. The top K parameter controls the number of most likely tokens to consider when generating a response. A higher top K value will result in more diverse and creative responses, while a lower top K value will result in more predictable and consistent responses. For example, if you set the top K to 10, the responses will be more diverse, while if you set the top K to 1, the responses will be more predictable. The top P parameter controls the probability of sampling tokens from the distribution of possible tokens. A higher top P value will result in more diverse and creative responses, while a lower top P value will result in more predictable and consistent responses. For example, if you set the top P to 0.9, the responses will be more diverse, while if you set the top P to 0.1, the responses will be more predictable. The maximum length of the generated response in tokens. For example, if you set the max length to 100, the generated response will be no longer than 100 tokens. Challenges and fixes. Hugging GPT may not be available. Install Hugging GPT using the appropriate package manager for your operating system. For example, if you are using pip, you can install Hugging GPT by running the following command: pip install Hugging GPT. Hugging GPT may not be able to generate a response. Ensure that the prompt is well-formed and contains the necessary information for Hugging GPT to generate a response. For example, if you are asking a question, make sure that the question is grammatically correct and complete. If you are asking for a specific piece of information, make sure that the prompt provides enough context for Hugging GPT to understand what you are looking for. Summary of Langchain Experimental Autonomous Agents Hugging GPT Response Generator. Response Generation Chain generates text from a Hugging Face model. This chain utilizes a pre-trained model from the Hugging Face library to produce text based on a provided input. The model can be any transformer-based language model, allowing for a wide range of text generation capabilities. Inputs. Input text to the model. This is the text that the model will use as context for generating new text. It could be a prompt, a question, or any other piece of text. For example, you could provide the model with a sentence like "The quick brown fox jumps over the lazy dog." The model to use. This refers to the specific pre-trained language model from Hugging Face that will be employed for Text generation. Some popular examples include GPT-3, BERT, and Roberta. These models have been trained on vast amounts of text data, enabling them to generate coherent and relevant text based on the provided input. Outputs. The generated text. This is the output produced by the Hugging Face model based on the input text and the selected model. The generated text will be a continuation or expansion of the input text, reflecting the model's understanding and capabilities. Steps. Initialize the Hugging Face model. This step involves loading the pre-trained language model from Hugging Face. It is essentially setting up the model and preparing it for text generation. This process includes loading the model's weights and parameters, which contain the knowledge learned during training. Call the model on the input text. This is where the actual text generation occurs. The input text is fed to the model, and the model generates new text based on its learned knowledge in the input's context. The output of this step is the generated text. Prerequisites. Hugging Face model. This refers to a pre-trained language model available on the Hugging Face platform. These models are developed and trained by researchers and developers, making them readily accessible for various text-based tasks. Examples of popular Hugging Face models include GPT-3, BERT, and Roberta, which excel in different aspects of language understanding and generation. Example values for Prerequisite 1 GPT-3, BERT, Roberta. GPT-3, BERT, and Roberta are prominent examples of pre-trained language models available on Hugging Face. GPT-3 Generative Pre-trained Transformer 3 is known for its impressive text generation abilities, while BERT bidirectional encoder representations from transformers excels in language understanding, tasks like question answering and sentiment analysis. Roberta, a robustly optimized BERT pre-training approach, is a variant of BERT that has been fine-tuned to achieve even better performance. These models are versatile and widely used in natural language processing (NLP) applications, enabling tasks like text summarization, machine translation, and chatbot development. Fine-tune parameters. Temperature. This parameter influences the creativity and randomness of the generated text. A higher temperature value encourages the model to explore more diverse and unexpected outputs, while a lower value results in more predictable and coherent text. Top K. This parameter controls the number of possible outputs considered by the model during text generation. A higher top K value allows the model to explore a wider range of options, leading to more diverse outputs. A lower value restricts the model's choices, resulting in more predictable and focused text generation. Challenges and fixes. Model may not be available. This challenge occurs when the specific Hugging Face model required for text generation is unavailable or inaccessible. This could be due to network connectivity issues, model maintenance, or other factors. Fixes to challenge 1. Check if the model is available on the Hugging Face Hub. The Hugging Face Hub is the central repository for pre-trained language models and datasets. By checking the availability of the model on the hub, users can verify if the model is accessible and ready for use. If the model is not found on the hub, it might indicate that the model is not publicly available or has been removed. Model may not be able to generate text. This challenge arises when the chosen Hugging Face model is not specifically designed for text generation. While some models excel at understanding and analyzing text, others are primarily focused on tasks like sentiment analysis or question answering. Fixes to challenge 2. Ensure that the model is a text generation model. To overcome this challenge, it's crucial to select a model that is explicitly designed for text generation. This can be determined by checking the model's documentation on the Hugging Face Hub or consulting with online resources. Models like GPT-3 and GPT-2 are specifically designed for text generation and are suitable for generating creative and coherent text. Example values for prerequisite to GPT-3. GPT-2. GPT-3 and GPT-2 are popular examples of pre-trained language models that are specifically designed for text generation. GPT-3, in particular, is known for its impressive abilities to generate human-like text, write different kinds of creative content, and answer your questions in an informative way. GPT-2 is a slightly older version of GPT-3 but still demonstrates strong text generation capabilities. Both models are valuable tools for various text-based applications, including content creation, chatbot development, and language translation. Summary of LangChain Experimental Autonomous Agents Baby AGI Task Execution Chain. This is a comprehensive description of the task execution chain, which is a component within the LangChain framework designed for executing tasks in an autonomous manner. Inputs. This is a description of the input to the task execution chain, which is a task to be completed. An example of such a task could be generate a summary of the latest advancements in the field of artificial intelligence. Outputs. This is a description of the output of the task execution chain, which is a result. The result will be the culmination of the steps that the task execution chain executes. Steps. This is a description of the first step involved in the task execution chain, identifying the task to be completed. The task could be something like writing a blog post on a given topic or summarizing a news article. This is a description of the second step involved in the task execution chain, breaking down the task into smaller steps. These smaller steps are meant to be simpler and more manageable. As an example, a blog post might be broken down into smaller steps such as research, outlining, writing, editing, and publishing. This is a description of the third step involved in the task execution chain, executing each step using appropriate tools. This involves leveraging various tools available to the agent, such as a search engine for research, a text generator for writing, or a code execution tool for data processing. This is a description of the fourth step involved in the task execution chain, combining the results of each step to produce the final output. This step ensures that the individual results of each step are integrated effectively to form a complete outcome. Prerequisites. This is a description of the prerequisite involved in the task execution chain, a task to be completed. This is the core input to the task execution chain and serves as the starting point for the entire execution process. For example, a user might ask the agent to write a blog post about the latest advancements in language models, which would be considered the task to be completed. This is a description of the prerequisite involved in the task execution chain, access to tools that can be used to complete the task. These tools are crucial for the task execution chain to successfully execute each step of the task. They could range from simple tools like Google Search for information retrieval to more specialized tools like text generators for creative content or code execution tools for data analysis. For example, an agent might require access to Google Search for research, a text generator for creating content, and a code execution tool for processing data. Fine-tune parameters. This is a description of the fine-tune parameter tools, which represents a list of tools that can be utilized to complete the task. These tools could include search engines for information retrieval, text generators for content creation, code execution tools for data processing, and many others. The agent utilizes these tools to perform the necessary tasks to reach the final outcome. This is a description of the fine-tune parameter verbose, which is a parameter that controls the level of detail in the output of the task execution chain. When the verbose parameter is set to true, the agent will print out the steps it takes as it completes the task. This can be helpful for debugging and understanding the agent's decision-making process. Challenges and fixes. This is a description of the challenge and fix unable to find a tool to complete a step. This challenge arises when the task execution chain encounters a step that cannot be fulfilled by the available tools. To overcome this challenge, the agent would try to utilize the most related tool available, even if it might not be a perfect fit. This allows the agent to continue executing the task even with limited tools. This is a description of the challenge and fix tool fails to complete the step. This challenge occurs when the agent encounters a step where the selected tool is unable to produce the expected result. The fix for this challenge is to try a different tool. This approach allows the agent to explore alternative options and improve the likelihood of successfully completing the step. This is a description of the challenge and fix tools are not available. This challenge arises when the agent lacks the necessary tools to perform certain steps. To address this, relevant tools need to be added to the agent's configuration. This ensures that the agent has access to the required resources for successful task execution. LangChain Experimental Autonomous Agents Hugging GPT Task Executor. A description of the Hugging GPT Task Executor and its purpose. The Hugging GPT Task Executor is an experimental autonomous agent designed for completing tasks by leveraging a variety of language models. Inputs: a human-readable, natural language description of the task to be completed by the Hugging GPT Task Executor. For example, a user might ask the task executor to summarize the main points of the article at this URL. A list of relevant files, URLs, or other data inputs required for the task executor to successfully complete the task. These inputs could include text documents, images, audio recordings, or even code. Outputs: the final output of the task execution, returned to the user in a format determined by the nature of the task. For instance, a summary task might yield a concise bullet point list, while a code generation task could produce functional code. A log detailing the steps taken by the task executor to execute the task. This log can be useful for debugging or understanding the reasoning process behind the task executor's decisions. The log typically includes information such as the chosen language models, their inputs, outputs, and any relevant error messages. Steps: the task executor receives a natural language task description from the user, outlining what they want to achieve. The task executor breaks down the complex task into a sequence of smaller, more manageable subtasks. This helps to ensure that the task is completed in a systematic and efficient manner. For example, a summarize an article task might be broken down into subtasks like extract key sentences, identify important concepts, and generate a concise summary. The task executor identifies the most suitable language model from a collection of models for each subtask. The task executor might select a model specialized in summarizing text for the extract key sentences subtask, and a different model for generating concise summaries for the final subtask. This ensures that the task executor utilizes the most appropriate tool for each part of the task. The task executor executes the subtasks using the chosen language models. feeding them the relevant inputs and receiving their outputs. For example, the task executor would feed the article text to the chosen extract key sentences model and use the model's output to inform the generate a concise summary model. The task executor combines the results of the subtasks to produce the final output for the original complex task. This could involve merging the results of multiple subtasks, applying further processing to refine the output, or simply presenting the results in a structured format. Prerequisites: the LangChain and Hugging Face libraries must be installed to use the Hugging GPT task executor. This can be accomplished by running the following command in a suitable terminal environment. Pip install LangChain transformers. Access to the Hugging Face hub is required to utilize the task executor. The hub is a platform that hosts a vast collection of pre-trained language models. Access can be granted through an API token or an access key to a specific Hugging Face model. Fine-tune parameters. A key parameter for tuning the performance of the task executor is the model selection strategy. This strategy determines how the task executor chooses the most suitable language model for each subtask. Different strategies might consider factors such as model accuracy, performance, cost, or the specific task requirements. Another critical parameter is the subtask decomposition algorithm, which dictates how the task executor breaks down the complex task into manageable subtasks. This algorithm should be carefully designed to ensure that the subtasks are logically connected, provide a clear path to the final goal, and are suitable for execution by available language models. Challenges and fixes. A major challenge for the task executor is ensuring that the correct language model is chosen for each subtask. If the wrong model is selected, it might lead to incorrect or suboptimal results. To address this, the model selection strategy can be modified to incorporate more factors or use a more sophisticated approach. The decomposition of the task into subtasks should be carefully designed. Errors in task decomposition can lead to inconsistent or incomplete results. Adjusting the subtask decomposition algorithm, possibly incorporating more domain-specific knowledge or using a more robust decomposition strategy, can mitigate this challenge. Language models, despite their sophistication, are not infallible. They can encounter errors during execution, resulting in failure to complete subtasks. To handle this, the task executor can implement mechanisms to gracefully manage these errors, such as retrying the subtask, using a different model, or providing the user with a relevant error message. Combining the results of multiple subtasks into a cohesive final output can be a complex task. The task executor may need to perform additional processing or analysis to integrate the results effectively. To address this, the task executor can implement robust result aggregation strategies that consider the nature of the subtasks, the expected output format, and any potential inconsistencies or redundancies. A crucial aspect of task execution is context awareness. Without sufficient context, the task executor may make incorrect decisions or produce inaccurate outputs. To improve context awareness, the task description can be augmented with relevant background information, or the task executor can be designed to access and utilize external information sources. Unclear task specifications can lead to misunderstandings and incorrect execution. Providing more precise task instructions, including clear objectives, constraints, and expected output format, can help avoid ambiguity and ensure that the task executor accurately understands the user's intentions. Limited access to external information can hinder the task executor's ability to complete certain tasks. To address this, external information sources, such as knowledge bases, databases, or search engines, can be integrated into the task executor's infrastructure, allowing it to access and utilize a broader range of knowledge. Security is a vital concern for any system that interacts with sensitive data or executes tasks on behalf of users. To mitigate security risks, the task executor can implement appropriate security measures, such as access control mechanisms, data encryption, and regular security audits. These measures can help to ensure the safety and integrity of the system and protect users from unauthorized access or data breaches. Langchain Experimental Autonomous Agents Hugging GPT Task Planner Base Planner Summary. A base planner that uses a Hugging GPT model to generate a plan. The Hugging GPT model, a large language model LLM with access to various application programming interfaces (APIs), can be used for various tasks, including planning. This planner utilizes the Hugging GPT model to take a user's goal and context as input, and then generates a plan that addresses the user's goal. The generated plan is then used to create a list of tasks that can be executed to achieve the goal. Inputs: user's goal, the user's desired outcome or objective, such as write a poem about a cat. Optional context: additional information that may be relevant to the user's goal. This could be anything from background information about the task to specific constraints or preferences. For example, the context could specify that the poem should be written in a specific style or that it should be no longer than 50 words. Outputs: list of tasks, a set of individual steps that must be completed to reach the user's goal. The tasks will be specific to the user's goal and the provided context. For example, a task list generated for the goal write a poem about a cat could include tasks such as research cat-related themes, choose a rhyme scheme, and write the poem. Steps: 1. Generate a plan using Hugging GPT. The planner uses Hugging GPT to create a plan that outlines the steps necessary to achieve the user's goal. This plan might involve various tools and APIs depending on the nature of the task. 2. Return a list of tasks. The planner converts the generated plan into a list of individual tasks that can be executed. Each task represents a specific step that must be completed to achieve the user's goal. Prerequisites: Hugging GPT model, a large language model that can access and utilize various application programming interfaces (APIs). The Hugging GPT model is essential for generating plans and providing access to the tools needed for execution. LangChain, an open-source framework that allows for the creation and execution of complex chains of tasks. LangChain provides the infrastructure needed to manage the planner, execute the tasks, and handle data flow. Fine-tune parameters. Hugging GPT model parameters. The planner may need to adjust the Hugging GPT model parameters to fine-tune its performance for specific tasks. This could involve modifying parameters related to the model's size, training data, or output format. Task planner parameters. The planner itself may have various parameters that can be adjusted to optimize its performance. These parameters could relate to the planning algorithm, task prioritization, or the level of detail provided in the generated plans. Challenges and fixes. Challenge 1: Hugging GPT might not be able to generate a plan. The Hugging GPT model may struggle to generate a plan if the user's goal is too complex, too specific, or if there is insufficient context provided. Fixes to challenge 1: use a different model with a broader knowledge base or specialized in a specific domain may be better suited to generating a plan for the user's goal. For example, a model trained on code could be more effective for generating a plan related to software development. Provide more context, providing more information about the user's goal, desired outcome, and any relevant constraints can help the model understand the task and generate a more accurate plan. Challenge 2: the plan might not be feasible. The plan generated by Hugging GPT may not be practically executable. For example, the plan may require resources that are not readily available, involve steps that are impossible to complete, or violate specific constraints. Fixes to challenge 2: modify the plan. The planner may need to modify the generated plan to make it feasible. This could involve removing or replacing certain tasks, adjusting the order of the tasks, or introducing new constraints. Add more constraints. Adding more constraints to the planning process can help ensure that the generated plan is more realistic and easier to execute. Challenge 3: the plan might not be complete. The generated plan might not cover all aspects of the user's goal or may omit certain steps that are necessary for successful completion. Fixes to challenge 3: add more tasks. The planner may need to add more tasks to the generated plan to ensure that it is comprehensive and covers all necessary steps for achieving the user's goal. Use a more comprehensive model. A larger or more specialized model could be better equipped to generate a more detailed and complete plan. For example, a model with a broader knowledge base or trained on a specific domain may be able to provide a more thorough understanding of the task and its requirements. Langchain Experimental Autonomous Agents Hugging GPT Task Planner Plan. This plan outlines the design and functionality of an experimental autonomous agent that leverages the Hugging GPT framework and LangChain for task planning. The agent aims to seamlessly translate user instructions into structured task plans and subsequently generate Python code to execute these plans. Inputs: the user's input, representing the desired action or goal. This can be a simple request like summarize this article or a more complex command like write a Python program to extract data from a website and analyze it. Contextual information that aids in understanding the user's intent and the environment the task is executed in. This can be supplementary text, a URL, or any data relevant to the task. Outputs: a structured task plan, outlining the sequence of steps needed to complete the user's instruction. This plan breaks down the high-level goal into smaller, manageable subtasks. Python code generated to execute each subtask within the task plan. The code is generated based on the specific task and the available libraries and tools. Steps: the agent interprets the user's intent by analyzing the instruction and the provided context. This involves identifying the task type, relevant entities, and potential constraints. The agent decomposes the overall task into a series of smaller subtasks that are more manageable. This process leverages the available knowledge and tools to define a logical workflow. For each subtask, the agent generates Python code using the Hugging GPT framework. This involves selecting the most appropriate model and parameters for the task and then using natural language prompts to guide the code generation. Prerequisites: the Hugging Face Transformers library is a crucial prerequisite for this agent. This library provides a wide range of pre-trained models and tools for natural language processing tasks, including text summarization, translation, and code generation. Install the Hugging Face Transformers library using a package manager like pip install transformers. The LangChain library facilitates the creation and management of chains of language models and other tools. It provides features for connecting models, integrating external APIs, and building sophisticated AI agents. Install the LangChain library using a package manager like pip install langchain. Fine-tune parameters. The type of model used for code generation is a critical parameter. Factors like the model's size, architecture, and training data influence the code generation quality. For example, one could choose between a large language model like GPT-3 or a model specialized for code generation. The number of steps or subtasks in the task plan can be adjusted to balance the complexity of a task and the granularity of the plan. A more complex task may require a greater number of steps for a clear and detailed plan. Challenges and fixes. Task complexity can pose a challenge for the agent. Complex tasks may require more sophisticated subtasks and potentially multiple iterations of a planning process. To address this, the agent can utilize more fine-grained subtasks or decompose the task into smaller, more manageable steps. Ambiguity in user instructions is a common issue in human-machine interactions. The agent may require clarification to accurately understand the intent and context of the user's input. To handle ambiguity, the agent can employ prompting techniques to clarify the user's intent. This can involve asking clarifying questions, providing examples, or presenting options for the user to choose from. Code generation errors can occur due to various factors such as limitations in the model, incorrect prompts, or issues with the execution environment. To address code generation errors, the agent can utilize debugging tools to identify and resolve code issues. This may involve stepping through the code, inspecting variables, and using debugging libraries. LangChain Experimental Autonomous Agents Hugging GPT Task Executor. A description of the capabilities of this agent. It executes tasks using pre-trained models from Hugging Face, a popular platform for sharing and deploying machine learning models. Inputs. A detailed description of the task to be performed by the agent. This should be clear and specific to ensure that the agent can properly interpret and execute the task. Any data required for the task. This could be raw text, structured data, or any other format that the selected model can accept. Outputs. The result of executing the task using the selected model. This could be text, a classification label, or any other format produced by the model. Steps. The agent first needs to understand the task description. This involves parsing the text, identifying the key elements, and determining the appropriate action to take. Based on the task description and the available input data, the agent selects an appropriate model from the Hugging Face Model Hub. This selection is based on the model's capabilities and the task requirements. Once a model is selected, the agent executes the model using the provided input data. This involves sending the data to the model and receiving the output. Prerequisites. The Hugging Face Transformers library is a Python library that provides access to a wide range of pre-trained models and tools for working with them. This library is essential for using Hugging Face models with LangChain. This refers to the Python package named Transformers, available for installation via pip. It offers utilities for loading and using pre-trained models, processing text, and performing various NLP tasks. Example: pip install transformers. The Hugging Face Model Hub is a centralized repository for sharing and deploying machine learning models. It provides a vast collection of models, including pre-trained models for tasks such as text classification, translation, summarization, and more. This refers to the website Hugging Face Co-Models. Users can browse, download, and use these models for their projects. Fine-tune parameters. This refers to the name of the specific pre-trained model to be used. Each model has its own unique name and is associated with specific capabilities and training data. For instance, GPT-2 or BERT-base encased are model names. These are the adjustable parameters specific to the chosen model. Model parameters control its behavior, like the number of layers, learning rate, and other hyperparameters. For instance, adjusting the temperature parameter in a text generation model can control how creative or predictable the generated text is. Challenges and fixes. If the required model is not available on the Hugging Face Model Hub, the agent may need to search for an alternative model or download the model directly from a source, like GitHub. For example, if the agent is tasked with a specific NLP task but the corresponding pre-trained model is not on the Hugging Face Model Hub, it may search for a similar model from other sources. If the selected model fails to execute properly, the agent should check the inputs and outputs, ensuring they match the model's requirements. For instance, if the model expects a specific format of input data, the agent needs to ensure that the provided data is correctly formatted. Adjusting model parameters can sometimes fix execution issues. For example, changing the learning rate or the number of layers might improve model performance. Debugging the code, checking for errors and inconsistencies, can identify the root cause of the problem. If the issue persists, it's recommended to report it to the Hugging Face team for further investigation and possible fixes. LangchainExperimental, Autonomous Agents, Hugging GPT, Task Planner, Base Planner Summarization. Base Planner for Hugging GPT Autonomous Agent. Base Planner is the core planning component for the Hugging GPT Autonomous Agent, which is designed to understand and execute user instructions by leveraging the capabilities of various Hugging Face models. It outlines the fundamental steps and considerations involved in planning and executing tasks within the Hugging GPT framework. Inputs. The user prompt is the initial input to the base planner, containing the user's request or instruction. It serves as the starting point for the planning process, defining the desired outcome. For example, a user prompt could be write a poem about a cat or generate a Python script to analyze a dataset. Outputs. The output of the base planner is a list of tasks, which represent the individual steps needed to fulfill the user's request. Each task is a well-defined unit of work that can be independently processed by the Hugging GPT agent. These tasks are generated based on the analysis of the user prompt and the capabilities of Hugging Face models available within the system. Steps. The first step in the planning process is to pass the user prompt into a list of tasks. This involves understanding the user's intent, identifying the key components of the request, and breaking it down into manageable subtasks. This step leverages natural language processing techniques to extract meaning from the user prompt. For instance, the prompt "write a poem about a cat" might be broken down into tasks like identify the relevant cat-related concepts, generate rhyming lines, and structure the poem. Once the tasks are defined, the base planner generates code for each task. This code is specific to the selected Hugging Face models and their functionalities. The code instructs the models to perform the necessary operations to complete the tasks. For example, the task generate rhyming lines could be implemented using a language model like GPT-2. While the task analyze a dataset might require a model trained for data analysis. After generating the code, the base planner executes the code. This involves invoking the chosen Hugging Face models and passing the generated code as input. The models then process the code, perform the designated actions, and produce the desired outputs. These outputs could be text, code, images, or any other format supported by the models. Prerequisites. The Hugging GPT model is a prerequisite for the base planner to function. It serves as the central orchestrator, coordinating the interaction between different Hugging Face models. The Hugging GPT model itself might be based on a large language model like GPT-3, providing the ability to understand complex user instructions and map them to appropriate model capabilities. Fine-tune parameters. Model size refers to the number of parameters in the Hugging Face models used for task execution. Larger models typically have more computational resources and can handle more complex tasks, while smaller models might be more efficient for simpler tasks. Choosing an appropriate model size is crucial for balancing performance and resource consumption. For example, a larger model like GPT-3 could be employed for complex language generation tasks, while a smaller model like Distilbert could be suitable for tasks involving text classification. Temperature is a parameter that controls the randomness or creativity of the model's outputs. Higher temperature values result in more unpredictable and creative outputs, while lower values produce more deterministic and predictable outputs. This parameter is particularly relevant for tasks involving text generation, where it influences the diversity and style of the generated content. For instance, a higher temperature could lead to more unusual and imaginative poems, while a lower temperature might generate more conventional poems. Challenges and fixes. A challenge that can arise is that the model might not understand the user prompt. This can occur if the prompt is ambiguous, lacks context, or uses unfamiliar terminology. To address this, prompt engineering techniques can be employed to provide the model with more explicit instructions and context. This might involve rephrasing the prompt, adding examples, or providing background information relevant to the user's request. Another challenge is that the model might generate incorrect code. This could be due to limitations in the model's understanding of the task, errors in the model's training data, or inconsistencies between the model's output and the expected code format. To mitigate this, using a more powerful model with enhanced code generation capabilities can be beneficial. Alternatively, implementing code verification mechanisms to check the generated code for errors before execution can help ensure correctness. A final challenge is that the model might not be able to execute the code. This could happen if the code requires access to external resources, specific libraries, or certain environment configurations, providing more context to the model, such as the relevant environment variables, dependencies, and execution instructions, can enhance its ability to successfully execute the code. Langchain Experimental Autonomous Agents Hugging GPT Task Planner Planning Output Parser Summary. This component parses the output of a Hugging GPT task planner and provides a structured representation of the plan. The Hugging GPT task planner uses a large language model (LLM) to generate a plan for a given task. This parser takes the output of the planner and converts it into a dictionary containing the plan's description, steps, prerequisites, fine-tuning parameters, and challenges and their corresponding fixes. Inputs. The output of the Hugging GPT task planner, which is a string containing the plan. The plan can be represented as a sequence of steps, each step being a task or a subtask. For example, if the task is to write a blog post, the plan might be to research the topic, write the blog post, edit the blog post, and publish the blog post. Outputs. A dictionary containing the following keys: description, a description of the plan. This is a summary of the plan, outlining the overall objective and the key steps involved. For example, the description for the plan to write a blog post might be: this plan outlines the steps involved in writing a blog post on a given topic. Steps: a list of steps to complete the plan. These steps are the individual tasks or subtasks that need to be completed to achieve the overall goal of the plan. Each step should be actionable and specific. For example, the steps for the plan to write a blog post might be: research the topic, write the blog post, edit the blog post, and publish the blog post. Prerequisites: a dictionary of prerequisites for the plan. These are the conditions that must be met before the plan can be executed. For example, the prerequisites for the plan to write a blog post might be access to a computer with an internet connection, access to a blogging platform, and knowledge of the topic. Fine-tune parameters: a dictionary of fine-tune parameters for the plan. These are parameters that can be used to adjust the behavior of the plan. For example, the fine-tune parameters for the plan to write a blog post might be target audience, desired tone, and length of the post. Challenges and fixes: a dictionary of challenges and fixes for the plan. These are potential issues that might arise during the execution of the plan and their corresponding solutions. For example, the challenges and fixes for the plan to write a blog post might be: writer's block, take a break and come back to it later, lack of information, do more research on the topic, and technical issues, contact the blogging platform's support team. Steps: pass the output of the Hugging GPT task planner and extract the relevant information. This step involves identifying the different components of the plan, such as the description, steps, prerequisites, fine-tuning parameters, and challenges and fixes. It may involve parsing the text, identifying keywords and phrases, and extracting the relevant information. Convert the extracted information into a structured format. This step involves organizing the extracted information into a structured format, such as a dictionary. This step ensures that the information is organized in a way that is easy to understand and use. Return the structured format as a dictionary. This step involves returning the structured representation of the plan as a dictionary. This dictionary can then be used by other components of the system, such as the task executor, to execute the plan. Prerequisites: the Hugging GPT task planner must be installed and configured. This prerequisite ensures that the system has access to the necessary tools to generate a plan. The Hugging GPT task planner requires a specific version of Python and other libraries to run successfully. The Hugging GPT task planner must be able to generate a plan. This prerequisite ensures that the system is capable of generating a plan for the given task. The Hugging GPT task planner must be trained on a sufficient amount of data to be able to generate meaningful plans. Fine-tune parameters: the max length parameter can be used to control the length of the generated plan. This parameter allows the user to specify the maximum number of steps in the plan. For example, the user might want to limit the plan to a maximum of 5 steps. This parameter helps to ensure that the plan is concise and manageable. Challenges and fixes: the Hugging GPT task planner may not be able to generate a plan for all tasks. This challenge arises when the task is too complex or the task planner is not trained on sufficient data related to the task. Fix: the task may need to be broken down into smaller subtasks. This involves dividing the task into smaller, more manageable tasks that the task planner can handle. For example, if the task is to write a book, the task could be broken down into smaller tasks such as writing the first chapter, writing the second chapter, and so on. The Hugging GPT task planner may generate a plan that is not feasible. This challenge arises when the plan contains steps that are impossible to execute or involve unrealistic assumptions. Fix the plan may need to be manually adjusted. This involves reviewing the generated plan and making necessary adjustments to make the plan feasible. For example, if the plan includes a step that requires access to a specific tool that is not available, the step could be replaced with an alternative step that uses a different tool. Langchain Experimental Autonomous Agents Hugging GPT Task Planner Summary. This is a detailed summary of the task planner for autonomous agents, which utilizes Hugging GPT and LangChain. This planner enables agents to autonomously handle tasks by leveraging the capabilities of both Hugging GPT, a large language model adept at interacting with various tools, and LangChain, a library dedicated to building and deploying applications powered by large language models. Inputs. The input to the task planner is a combination of user input, representing the desired task or goal, and the context, comprising any relevant information or background knowledge pertaining to the task. The context provided to the task planner could include information such as the user's previous interactions, the current state of the system, or any relevant external data that the planner can access. Outputs. The task planner generates a list of tasks that need to be executed to achieve the desired goal or fulfill the user's request. These tasks are meticulously planned, taking into account the available tools and the context of the task. Finally, the task planner produces a comprehensive and human-readable response that summarizes the executed tasks, the results achieved, and any relevant insights gained during the task execution process. Steps. The first step in the task planner's execution is to pass the user input, breaking down the request into its constituent components, and identifying the core intent behind the user's request. Once the user's input has been passed, the task planner identifies the relevant tools that can be employed to fulfill the request. This involves analyzing the task's requirements and selecting appropriate tools from the available toolset. The task planner then plans the sequence of tasks that need to be executed to achieve the desired outcome. This step involves prioritizing the tasks, taking into account the dependencies between them, and ensuring that the chosen tools are optimally utilized. After planning the tasks, the task planner proceeds to execute them in the order specified. This involves interacting with the chosen tools, retrieving necessary data, and performing the required actions. Finally, the task planner returns the final response to the user, summarizing the results of the executed tasks, any insights gained, and the overall outcome of the task execution process. Prerequisites. Hugging GPT, a large language model, is a key prerequisite for the task planner. It plays a crucial role in understanding and interpreting user input, identifying the appropriate tools, and communicating with those tools to execute the planned tasks. LangChain serves as the foundation for the task planner, providing the necessary infrastructure and components for building and deploying the LLM-powered application. It facilitates the interaction between the task planner and Hugging GPT, enabling the seamless integration of various tools and the efficient execution of tasks. Fine-tune parameters. Task prioritization is a crucial parameter that can be fine-tuned to optimize the task planner's performance. This involves adjusting the relative importance of different tasks based on factors such as their urgency, impact, and dependencies on other Tasks. Tool selection is another important parameter that can be fine-tuned to improve the task planner's efficiency and accuracy. This involves customizing the criteria for selecting the most appropriate tools for each task, based on factors such as the tool's capabilities, availability, and cost. Challenges and fixes. Task ambiguity. A common challenge in natural language processing can arise when the user's request is unclear or open to multiple interpretations. This can be addressed by employing conversation-based clarification techniques to unambiguously determine the user's intent. Selecting the right tools for each task can be challenging, especially when the available tools are diverse and complex. To address this challenge, the task planner utilizes a combination of a knowledge graph and a large language model. The knowledge graph provides a structured representation of the tools and their capabilities, while the LLM assists in interpreting the task's requirements and selecting the most appropriate tools from the knowledge graph. Task execution may encounter errors or unexpected issues, which can lead to task failures. To handle such situations, the task planner implements error handling mechanisms that attempt to resolve the errors and retry failed tasks. This ensures that the task execution process is resilient and can handle unforeseen challenges, generating a response that is both comprehensive and human-readable is crucial for effective communication with the user. The task planner addresses this challenge by generating responses that clearly summarize the executed tasks, the results obtained, and any relevant insights gained during the task execution process. The response is tailored to be understandable by a human user, without requiring specialized knowledge or technical expertise. Langchain Experimental Autonomous Agents Hugging GPT Task Planner. Task Planner is a component in the Hugging GPT framework, used for planning tasks. It takes a user's goal and the current context as input and generates a list of tasks to achieve the goal. The tasks are decomposed, prioritized, and assigned to specific tools. For example, if the user's goal is to write a blog post, the task planner could decompose it into subtasks like researching the topic, writing the post, editing it, and publishing it. The task planner could then assign these subtasks to different tools, such as a search engine for research, a text editor for writing, and a social media platform for publishing. Inputs. The user's goal is the desired outcome or objective that the user wants to achieve. It could be a simple task like find a restaurant in New York City or a complex goal like write a research paper on artificial intelligence. The current context refers to the relevant information or knowledge available to the task planner. This could include information about the user's preferences, past interactions, or the environment. For instance, if the user has already expressed interest in Italian food, the current context could include information about Italian restaurants in New York City. Outputs. The output of the task planner is a list of tasks that are generated to achieve the user's goal. These tasks are typically organized in a logical order and can be assigned to specific tools for execution. For example, the task planner might output a list of tasks like search for Italian restaurants in New York City, read reviews for the restaurants, make a reservation, and go to the restaurant. Steps. The first step in task planning is to decompose the user's goal into a series of subtasks. This involves breaking down the goal into smaller, more manageable tasks that can be completed individually. For instance, if the goal is to write a research paper, the subtasks might include gathering research, outlining the paper, writing the introduction, writing the body paragraphs, and writing the conclusion. Once the goal has been decomposed into subtasks, the next step is to prioritize them. This involves determining the order in which the subtasks should be completed to achieve a overall goal most effectively. Some subtasks might be more critical than others, or some might need to be completed before others can be started. For example, in writing a research paper, gathering research might be prioritized over writing the introduction. The final step in task planning is to assign each subtask to a specific tool. This involves identifying the appropriate tool or resource for completing each subtask. The task planner can draw from a wide range of tools, including search engines, text editors, translation tools, and more. For instance, the task of gathering research for a research paper could be assigned to a search engine, while the task of writing the paper could be assigned to a text editor. Prerequisites. The Hugging GPT model is a large language model (LLM) that serves as the foundation for the task planner. It provides the knowledge and understanding required to decompose tasks, prioritize them, and assign them to specific tools. The Hugging GPT model is trained on a massive dataset of text and code, allowing it to understand natural language, generate text, and perform various tasks. Fine-tune parameters. The model size is one of the important parameters that can be fine-tuned for the task planner. It refers to the number of parameters in the Hugging GPT model. A larger model generally has a higher capacity to handle more complex tasks and understand nuanced language. However, it also requires more computational resources and can be slower to train. Challenges and fixes. One challenge in task planning is that the task planner may not be able to decompose a complex goal into subtasks effectively. This can happen when the goal is very abstract, ill-defined, or requires a deep understanding of a specific domain. For example, if the goal is to become a successful entrepreneur, the task planner might struggle to decompose it into meaningful subtasks. One way to address this challenge is to train the task planner on more complex goals. This can involve providing it with examples of complex goals that have been successfully decomposed into subtasks. By learning from these examples, the task planner can improve its ability to handle complex goals. Another challenge is that the task planner may not be able to prioritize subtasks correctly. This could be due to a lack of understanding of the user's preferences, the importance of different subtasks, or the dependencies between them. For instance, the task planner might incorrectly prioritize writing the introduction of a research paper over gathering research, leading to an incomplete paper. To address this challenge, the task planner can be trained on data that includes task priorities. This could involve providing it with examples of goals and their corresponding subtasks, where the subtasks are labeled with their priorities. By learning from these examples, the task planner can improve its ability to prioritize tasks effectively. Finally, the task planner may not be able to assign subtasks to the correct tools. This could be due to a limited understanding of the capabilities of different tools, a lack of knowledge about which tools are available, or an inability to identify the best tool for a given subtask. For example, the task planner might incorrectly assign the task of writing a research paper to a translation tool instead of a text editor. To address this challenge, the task planner can be trained on data that includes tool assignments. This could involve providing it with examples of goals and their corresponding subtasks, where the subtasks are labeled with the tools that are best suited for completing them. By learning from these examples, The task planner can improve its ability to assign tasks to the correct tools. LangChain Experimental Autonomous Agents AutoGPT Prompt Generator Get Prompt Summary. This agent generates a prompt for AutoGPT based on inputs and desired outputs. Inputs: the current context, situation, or knowledge related to the task. For example, if the task is to find the best restaurant in a city, the input could be the city name, the type of food desired, and the user's budget. The desired outcome or goal of the task. For example, if the task is to find the best restaurant in a city, the desired outcome could be a list of top-rated restaurants with their addresses, phone numbers, and reviews. Outputs: a prompt that is fed to AutoGPT. This prompt will be specific to the task and will include all of the necessary information for AutoGPT to complete the task. Steps: gather information about the task and its context. This includes understanding the user's intent, the available resources, and the desired outcome. Analyze the inputs and outputs to identify the required actions. This involves breaking down the task into smaller steps and determining which actions AutoGPT needs to take to achieve the desired outcome. Craft a prompt that outlines the task, context, and desired outputs. The prompt should be clear, concise, and specific. It should guide AutoGPT towards completing the task successfully. Prerequisites: an AutoGPT instance, which is a large language model (LLM) that can be used to automate tasks. AutoGPT is available as an open source project and can be set up on a personal computer or cloud server. A clear understanding of the task and its desired outputs. This includes knowing what the user wants to achieve and what the expected outcome should look like. Fine-tune parameters. The length of the prompt. A longer prompt can provide more context and detail, while a shorter prompt can be more concise and to the point. The specificity of instructions. More specific instructions can help AutoGPT complete the task more accurately, while less specific instructions can give AutoGPT more freedom to explore different options. Challenges and fixes. The prompt being too general. Provide more specific instructions and context. For example, instead of asking AutoGPT to find the best restaurant in the city, specify the type of food desired, the budget, and the location within the city. The prompt being too complex. Break down the task into smaller subtasks. For example, instead of asking AutoGPT to write a blog post about a specific topic, break the task down into smaller steps, such as researching the topic, outlining the blog post, writing the blog post, and editing the blog post. The prompt being ambiguous. Reword the prompt for clarity. For example, instead of asking AutoGPT to find information about a specific topic, specify the type of information desired, such as research papers, news articles, or blog posts. LangChain Experimental Autonomous Agents Hugging GPT Response Generator Load Response Generator. Summary. This component is a response generator within the Hugging GPT framework. It leverages Hugging Face models to generate text responses based on user prompts. The component essentially acts as an interface between the user input and the chosen Hugging Face model. Inputs. This refers to the text prompt that is provided to the Hugging GPT response generator. It acts as the initial input, prompting the model to generate a response based on the context and intent expressed within the text. An example of this could be a question, a request for a summary, or a creative writing prompt. Outputs. This refers to the generated text output produced by the Hugging Face model based on the input Prompt. It is a textual response tailored to the input prompt and guided by the model's training data and parameters. For instance, if the prompt is a question, the output would be a textual answer. If the prompt is a creative writing prompt, the output would be a generated story or poem. Steps. This step involves loading the specified Hugging Face model into the component's memory. It entails fetching the model's weights and architecture from Hugging Face's repository and preparing the model for processing the input prompt. The model is selected based on the requirements of the task and the desired response style, like generating code, summarizing text, or translating languages. The model chosen could be a pre-trained model like BART or GPT-2. Or it could be a fine-tuned model trained on a specific dataset. This step involves processing the input prompt using the loaded Hugging Face model. It entails feeding the prompt to the model, allowing it to interpret the prompt's context and intent. The model then generates a text response based on its internal representation of language and its training on a massive dataset of text. The model predicts the most likely sequence of words that aligns with the input prompt, ensuring a coherent and relevant response. Prerequisites. This refers to the necessary components and resources required to successfully execute the Hugging GPT response generator. The core prerequisite is the presence of a Hugging Face model, specifically one that aligns with the desired functionality and response style. This model should be available within the Hugging Face repository, allowing the component to access its weights and architecture. This refers to the specific name of the Hugging Face model that will be used by the component. It acts as a reference to a unique model within the Hugging Face repository. The model name often reflects the model's architecture, like BART, GPT-2, or a specific fine-tuned version of the model. For instance, Facebook BART Large CNN refers to the BART model fine-tuned on CNN news articles. Challenges and fixes. This refers to an error that might occur during the initial loading of the Hugging Face model. This can be caused by issues like network connectivity problems or the model being unavailable within the Hugging Face repository. This refers to verifying the availability of the specified Hugging Face model within the Hugging Face repository. It involves checking if the model exists, if it is correctly identified, and if there are any issues with accessing it. This step is crucial to ensure that the component can successfully load the model and proceed with the text generation process. This refers to errors that might occur during the text generation process, where the loaded Hugging Face model fails to generate a response despite being successfully loaded. This could be due to issues with the model's configuration or the input prompt itself. This refers to examining the model's configuration parameters, such as the maximum sequence length or temperature, which influence the model's text generation behavior. It involves reviewing these parameters and ensuring they align with the requirements of the input prompt and the expected response style. A misconfigured parameter, like a very short sequence length, could result in truncated responses or the model's inability to generate the expected output. This refers to reviewing the input prompt provided to the Hugging GPT response generator. This involves analyzing the prompt structure, clarity, and potential ambiguity. It ensures that the prompt is well-formed, unambiguous, and provides enough context for the model to understand the desired response. An unclear prompt, lacking context or expressing multiple intents, could result in a response that deviates from the user's expectations or a model failure to understand the prompt's intended meaning. Langchain-experimental, autonomous agents, Hugging GPT, Task Planner, Load Chat Planner. This function loads a chat planner from a file or string. A chat planner is a file or string that defines the steps and actions for a conversational agent. It typically includes information on the agent's goals, the types of questions it can answer, and the responses it should provide. Inputs. Path to the chat planner file. This input specifies the location of the chat planner file on the system. For example, the path could be home usage planner, JSON. String containing the chat planner. This input represents the content of the chat planner as a string. The string contains all the necessary information to define the chat planner, including goals, questions, and responses. For example, the string could be goals: greet user, answer questions. Questions: what is your name? What is your favorite color? Responses: hello, what's your name? My favorite color is blue. Outputs. Chat planner object. This output is a chat planner object, which is a representation of the chat planner in memory. It can be used to access the chat planner's information and execute its defined actions. Steps. 1. Read the chat planner file or string. The function first reads the chat planner file or string, depending on the provided input. If the input is a file path, the function reads the contents of the file. If the input is a string, the function directly uses the provided string. To parse the chat planner, the function then parses the chat planner to extract its information. This involves understanding the format of the chat planner file or string and extracting the relevant data, such as goals, questions, and responses. 3. Create a chat planner object from the parsed data. Finally, the function creates a chat planner object using the parsed data. This object encapsulates the chat planner's information and provides methods for accessing and manipulating it. Prerequisites. Hugging Face Hub library. This prerequisite involves installing the Hugging Face Hub library, which is a library for interacting with the Hugging Face Hub, a platform for sharing and collaborating on machine learning models and datasets. It is likely that this library is required for accessing or managing chat planners stored on the Hugging Face Hub. Fine-tune parameters. None. This indicates that the function does not have any fine-tuning parameters. Fine-tuning parameters are adjustable settings that can be used to customize the behavior of a function. In this case, the function's behavior is likely determined by the provided chat planner and does not require any further configuration. Challenges and fixes. Challenge 1. The chat planner file is not found. This challenge arises if the provided path to the chat planner file does not lead to an existing file. For example, if the path is home usage planner, JSON, but the file does not exist at that location, this challenge occurs. Fixes to challenge 1. Check the path to the chat planner file to fix this issue. Ensure that the provided path is correct and points to an existing file. Verify the file name, directory path, and file extension. Challenge 2. The chat planner file is invalid. This challenge occurs if the chat planner file exists, but its format is not recognized by the function. For example, the file might be in an incorrect format, e.g., XML instead of JSON, or have syntax errors. Fixes to challenge 2. Check the format of the chat planner file to address this challenge. Verify the format of the chat planner file. Ensure it matches the expected format, such as JSON or YAML. Inspect the file for any syntax errors, such as missing or incorrect characters. Challenge 3. The chat planner file is corrupted. This challenge happens if the chat planner file exists but its content has been corrupted. This could be due to various reasons, such as data loss during file transfer or a system error. Fixes to challenge 3. Try to repair the chat planner file to address this challenge. Attempt to repair the chat planner file. You can try methods like using data recovery software or examining the file's contents to identify and correct any corrupted parts. If the corruption is severe, you might need to recreate the file from a backup or start from scratch. LangchainExperimental, Autonomous Agents, Hugging GPT, Task Planner, Load Chat Planner. This function loads a chat-based planner from a file. A chat-based planner is a type of planner that utilizes a conversational approach to plan tasks. These planners are often implemented using large language models (LLMs) like GPT 3.5 Turbo, which can generate plans based on prompts and conversation history. Inputs. The path to the planner file is a string representing the location of the planner file on your system. For example, planner, JSON or home user planner, YAML. Optional arguments are parameters that can be passed to the planner to customize its behavior. These arguments may include things like the desired format of the output plan, the level of detail in the plan, or the specific LLM to use for generating the plan. Outputs. The output of this function is an instance of the chat-based planner. This instance can be used to interact with the planner to generate plans and manage tasks. Steps. Reading the planner file involves retrieving the planner data from the specified path using file handling functions. The data typically contains information about the planner's structure, configuration, and any predefined steps or actions. Parsing the planner file means interpreting the structure and content of the file. The planner data is processed and translated into a representation that can be understood by the planner object. This step may involve validating the file format, extracting relevant information, and creating necessary data structures to store the planner's configuration. Prerequisites. Hugging GPT is an open-source Python library that enables interaction with various large language models for tasks such as text generation, translation, summarization, and question answering. It is often used in conjunction with other libraries like LangChain to build complex agents and workflows. The pip command is used to install Python packages. It acts as a package manager, allowing you to download and install libraries and their dependencies directly from the Python package index PyPI repository. In this context, pip install Hugging GPT downloads the Hugging GPT library and its required components to your system. A valid planner file is a file that adheres to the expected format and structure defined by the load chat planner function. This file typically contains instructions, rules, and configuration details that define how the planner operates. Existence refers to the requirement that the file must actually be present in the specified location on your computer's file system. Fine-tune parameters. The planner type refers to the approach used by the planner in generating plans. Zero-shot implies that the planner does not require any specific training examples or past experiences to generate a plan. It relies solely on the prompt and its understanding of language to generate a plan. Few-shot suggests that the planner may benefit from a few examples of past plans or task scenarios to refine its understanding and improve plan generation. This can lead to more tailored and accurate plans. The planner model is the specific large language model that will be used to power the chat-based planner. GPT 3.5 Turbo is a powerful language model developed by OpenAI. It can understand and generate human-like text, making it suitable for tasks like generating creative content, translating languages, writing different kinds of creative text formats, and answering your questions in an informative way. Challenges and fixes. An invalid planner file format occurs when the file does not meet the requirements of the planner's structure and format. This can happen if the file uses an incorrect syntax, contains missing data, or has a structure that does not comply with the planner's expectations. A valid planner file format is crucial for the planner to correctly parse and interpret the information within the file. Using a valid planner file format involves adhering to the specific structure and syntax rules defined by the load chat planner function. This might involve ensuring the file is in a specific format like JSON JavaScript object notation or YAML YAML int markup language. A planner file not found error occurs when the specified file path does not lead to an existing file on your system. This means the file you are trying to load cannot be located at the provided path. It could be due to a typo in the file name, an incorrect path, or the file simply not being present. Ensuring the file exists at the given path requires verifying the correctness of the path you have provided and checking if the file is actually present in that location. You may need to double-check the file name, the directory structure, or use a file explorer to verify the file's location. A planner model not found error arises when the planner cannot locate the specified LLM that is supposed to be used for plan generation. This could be because the model is not installed or is not available in the environment where the planner is running. Installing the required planner model involves obtaining and installing the necessary LLM library or package on your system. This might involve using package managers like pip or conda to download and install the specific model you need. LangchainExperimental, Autonomous Agents, Hugging GPT, Task Planner, Step Summary. LangchainExperimental, Autonomous Agents, Hugging GPT, Task Planner, Step Summary. A step in a Hugging GPT Task Planner agent. It is a fundamental building block of the Hugging GPT agent, responsible for executing a specific task, updating the context, and potentially generating a subsequent task. Inputs: the current task, representing the action the agent is currently working on. This can be anything from fetching information, summarizing text, to generating creative content. It's the driving force behind the agent's actions. The current context, which is a compilation of all the relevant information gathered and processed so far. This includes the initial task, previous results, and any relevant external knowledge retrieved during the execution. Outputs: the next task, which is the new action the agent should execute after completing the current task. This could be a related task based on the current task's outcome, or a completely different task determined by the context and the agent's overall objective. The next context, which is the updated context, incorporating the results of the current task, any new information gathered, and potentially other relevant data. This updated context serves as the foundation for the subsequent tasks and ensures the agent maintains a consistent and relevant understanding of the situation. Steps: 1. Get the current task retrieves the currently assigned task from the agent's task queue. 2. Get the current context retrieves the current context, which is the accumulated knowledge relevant to the ongoing task execution. 3. Call the Hugging GPT model to get the next task and context interacts with the Hugging GPT modeler. Large language model specialized for planning and execution. Passing in the current task and context. The model then uses its understanding of the task and the available information to generate the next task and the corresponding updated context. 4. Return the next task and context outputs the next task and the updated context to the agent. This allows the agent to seamlessly transition to the next task and continue its execution with the most relevant information. Prerequisites. A Hugging GPT model. This refers to the Hugging GPT model, a large language model specifically trained to perform planning and execution tasks. This model is the core component of the Hugging GPT agent, responsible for generating the next task and updating the context. Fine-tune parameters. None. There are no specific parameters to fine-tune for this step, as the core functionality is handled by the Hugging GPT model, which has its own tuning process. Challenges and fixes. The Hugging GPT model may not be able to generate a valid next task or context. It's possible that the model might fail to generate a coherent and relevant next task or context due to ambiguity, lack of information, or errors in the model's understanding. Try using a different Hugging GPT model if the current model struggles to generate valid outputs. Experimenting with different Hugging GPT models, each with its strengths and biases, could potentially yield better results. This involves choosing a model known for its performance in similar tasks or exploring models specifically trained for planning and execution. The Hugging GPT model may generate a task or context that is not relevant to the current task. The model's understanding of the context and its ability to predict relevant tasks may be limited, leading to irrelevant outputs. Try providing more context to the Hugging GPT model to improve the model's ability to generate relevant outputs. Enriching the context with more specific information can be crucial. This involves providing the model with a more detailed description of the current task, relevant background information, or any prior knowledge related to the task's domain. This helps guide the model towards generating more pertinent tasks and contexts. Llama 2 Chat Wrapper Summary. This wrapper provides a concise description of the Llama 2 chat model and its use cases. It outlines the input and output of this wrapper and the steps involved in using it. It also highlights the prerequisites, fine-tuning parameters, and potential challenges and their solutions. Inputs. The user provides a question or prompt as input to the model. For example, what is the capital of France? The wrapper takes this input and passes it to the Llama 2 chat model. The chat history stores the previous conversation turns, allowing the model to maintain context and provide consistent responses. This helps in creating more engaging and coherent conversations. Outputs. The model generates a text response based on the user input and chat history. The response can be an answer to the question, a continuation of the conversation, or a creative text piece based on the prompt. Steps. The Llama 2 chat object is initialized. This step sets up the model and prepares it for processing user input. The predict method is called with the user input and chat history. This method utilizes the Llama 2 model to generate the response. Prerequisites. Install the LangChain and Transformers libraries using the following command: pip install langchain. Transformers. These libraries are essential for interacting with the Llama 2 model and managing the chat history. Install the Llama 2 model using the Transformers library pip install transformers. This command installs the necessary components to load and use the Llama 2 model. Fine-tune parameters. The temperature parameter controls the randomness of the generated text. Higher temperature values result in more creative and unpredictable responses, while lower values produce more predictable and conservative outputs. The top P parameter limits the probability distribution of the next token to be generated. A lower value restricts the model to more probable words, while a higher value allows for more diverse and less predictable outputs. Challenges and fixes. The model might generate repetitive or nonsensical responses. This can be addressed by adjusting the temperature or top p-values, effectively controlling the model's randomness and probability distribution. The model might not be able to access external information. To address this, use a different wrapper that supports external information retrieval. This allows the model to access knowledge bases, search engines, or other external resources to provide more comprehensive and accurate responses. LangchainExperimental, chatmodels.llm wrapper, Mixtral summary. A LangChain wrapper for the Mixtral large language model. This wrapper allows you to use the powerful Mixtral language model in your LangChain applications. Inputs. Text input the text you want to provide to the Mixtral model. For example, you can input a question, a request for a summary, or a creative writing prompt. Outputs. Text output the generated output from the Mixtral model, based on the input text. This could be a response to a question, a summary, or a creative piece of writing. Steps. Initialize the Mixtral model. The wrapper sets up the Mixtral model. Send the input to the model. The input text is sent to the initialized Mixtral model for processing. Return the output from the model after processing the input. The Mixtral model generates an output, which is returned by the wrapper. Prerequisites. Install the Mixtral library. Install the Mixtral library using the command pip install Mixtral. This allows you to use the Mixtral model in your Python environment. Install LangChain. Install the LangChain library using the command pip install LangChain. This provides the framework for interacting with and managing language models. Fine-tune parameters. Temperature controls the randomness of the output. A higher temperature value will result in more creative and unexpected outputs, while a lower value will lead to more deterministic and predictable outputs. Top K limits the number of possible tokens to be considered during text generation. This helps to constrain the model's outputs to a more focused range of possibilities. Challenges and fixes. Error model not found. If you encounter this error, it means that the Mixtral library is not installed. You can fix this by installing the Mixtral library using pip install Mixtral. Incorrect output format. If you are experiencing issues with the output format, you can specify the desired format by using the format argument of the Mixtral class. For instance, you can specify JSON, text, or HTML to control the output format. LangchainExperimental, chatmodels.llm wrapper, Llama 2 chat summary. This wrapper provides access to Llama 2 chat models. Llama 2 is a large language model developed by Meta that excels in conversational tasks. This wrapper enables developers to integrate Llama 2 into their applications for natural language understanding and generation. Inputs. Textual input provided to the Llama 2 model. This can be a question, a prompt, or a conversational turn in a dialogue. Outputs. Textual output generated by the Llama 2 model in response to the provided input. This can be an answer, a generated text, or a continuation of the conversation. Steps. Initialize the LLM. The wrapper first requires the user to provide the name or path of the Llama 2 model they want to use. This step sets up the connection to the chosen model. Load the model after initialization. The wrapper loads the Llama 2 model into memory, making it ready to process user input. Prerequisites. Llama.cpp installation to utilize the Llama 2 chat model. Llama.cpp is a crucial component. It enables the model to be run locally without the need for a large cloud infrastructure. The installation is straightforward with the command pip install llamasp python. Model weights. Llama 2 model weights are necessary for the model to function. These weights are a set of parameters that the model has learned during its training. Meta provides these weights for various versions of Llama 2 on its official website. Fine-tune parameters. Temperature. This parameter controls the randomness and creativity of the model's output. A higher temperature value leads to more diverse and potentially unexpected responses, while a lower temperature value produces more predictable and consistent results. Top K. This parameter restricts the set of possible words the model can choose from at each step of text generation. A smaller top K value limits the model's vocabulary, making its output more concise and focused. A larger value provides more flexibility and potential for creative expression. Top P. This parameter controls the probability distribution of possible words that the model can select from at each step. It uses a method called nucleus sampling, which ensures that the model only considers a subset of the most probable words. This helps to avoid generating unexpected or nonsensical outputs. Challenges and fixes. Model loading error. One common issue that users may encounter is a model loading error. This can be caused by missing prerequisites, incorrect model paths, or incompatible versions of llama.cpp or the model weights. To resolve this, ensure that llama.cpp is installed correctly and that the model weights are located in a specified directory. It's also essential to double-check the compatibility between the llama.cpp version and the model. Slow inference speed. The time it takes for the model to process input and generate output can be a challenge, especially when dealing with large and complex models. Users may experience slow inference speeds if they are running the model on a machine with limited resources. To address this, using a GPU can significantly improve performance. Optimizing the llama.cpp configuration by adjusting parameters like the number of threads and memory usage can also enhance speed. Langchainexperimental, chatmodels.llm wrapper, Ocker summary. This wrapper allows the use of the Ocker language model from Microsoft within the LangChain framework. It acts as a bridge, enabling interaction with the Ocker model's capabilities through LangChain's API. Inputs. The input to the Ocker model is text, which can be a question, a prompt, or any text requiring processing by the model. For example, if you want to generate a summary of a news article, you would provide the article text as input. Outputs. The output from the Ocker model is also text, which may be a summary, a response to a question, a generated piece of text, or any other output that the model is capable of producing. The specific output depends on the nature of the input and the task that the model is asked to perform. Steps. The wrapper initializes the Ocker model by loading the necessary resources, setting up the model's configuration, and preparing it for processing input. This involves specifying the model's parameters, such as the version or variant of the Ocker model being used. The input text is then passed to the initialized Ocker model. This step involves converting the input text into a format that the model can understand and processing it using the model's algorithms. The Ocker model produces an output based on the input text. This output is then returned by the wrapper, making the results available to the user or for further processing within the LangChain framework. Prerequisites. LangChain is a library that provides a framework for building and deploying language model applications. It simplifies the process of integrating large language models into applications and offers tools for working with various models, tasks, and data sources. Transformers is a library developed by Hugging Face that provides tools and infrastructure for working with transformers-based language models. It facilitates training, fine-tuning, and deploying a wide range of pre-trained models, including OCR, fine-tune parameters. Fine-tuning refers to the process of customizing a pre-trained language model for a specific task. For example, fine-tuning an OCR model could involve providing it with a set of training examples related to a particular domain or task, such as summarizing legal documents or writing creative stories. In this case, the OCR model wrapper does not offer any fine-tuning options. The wrapper focuses on providing a basic interface for using the OCR model without modification. Challenges and fixes. The availability of the OCR model may vary depending on the region or location of the user. If the model is not accessible in a particular region, it's recommended to switch to a different model or use a different region. For instance, if the OCR model is not accessible in Europe, a different model or a region where the OCR model is accessible can be used. The OCR model may not be able to handle all types of input, particularly if the input text is formatted in a way that the model does not recognize or understand. Ensuring that the input text is in a format the model can process is crucial for successful interaction. For example, if the input text is a code snippet, it should be formatted in a way that the OCR model understands, such as using a specific code highlighting syntax or delimiters. The OCR model, like any language model, can sometimes produce incorrect or nonsensical outputs. This can happen due to various factors, such as ambiguity in the input text, the model's limitations, or unexpected variations in the training data. If the model's output is not satisfactory, consider using a different model that is better suited for the task or providing more context in the input. For example, instead of asking what is the meaning of life, one could provide more context by asking what is the meaning of life according to the philosophy of Aristotle. Langchain experimental chat models LLM wrapper Vicuna. Vicuna is a wrapper for the Vicuna large language model LLM, enabling its integration and utilization within the LangChain framework. It serves as an interface that allows LangChain to interact with Vicuna LLM, leveraging its capabilities for various natural language processing tasks. Inputs. A prompt string, representing the textual input provided to the Vicuna LLM. The prompt serves as the initial instruction or query that the LLM processes to generate a response. For example, a prompt could be write a short story about a cat who goes on an adventure. Outputs. The textual response generated by the Vicuna LLM in response to the provided prompt. This output may consist of multiple sentences or paragraphs, depending on the complexity of the prompt and the LLM's capabilities. For instance, in response to the prompt write a short story about a cat who goes on an adventure, the LLM might output a narrative that describes a cat's journey through a forest, encountering various obstacles and characters along the way. Steps. The prompt string is sent to the Vicuna LLM for processing. This involves the LLM analyzing the prompt and understanding its intent and context. The Vicuna LLM generates a textual response based on the input prompt. This response is generated by the LLM using its internal language model, trained on a massive dataset of text and code. The generated text response is returned as the output of the wrapper. This output is then available for further processing or use within the LangChain framework. Prerequisites. Vicuna LLM installed and accessible. This means that the Vicuna LLM software needs to be installed on the system and configured correctly for use. This may involve downloading and installing the necessary software packages. configuring environment variables, and setting up connections to any required external services. For example, one might install the Vicuna LLM from its official website and configure it to run on a local machine, ensuring that all dependencies are met. Install Vicuna LLM through the official channels. This involves obtaining the necessary software packages and following the installation instructions provided by the Vicuna LLM developers. The process may involve using package managers like pip or conda, depending on the chosen operating system and LLM version. Configure the LLM to run on your system. This step involves setting up the LLM environment to ensure it functions correctly on the target system. This might include configuring environment variables, setting up necessary dependencies, and ensuring access to any required resources like GPUs or cloud computing services. For instance, one might configure the LLM to use a specific GPU for accelerated processing, if available, or connect it to a cloud storage service for accessing data. LangChain installed and configured. LangChain is a framework that provides tools and utilities for building and working with language models, including LLM wrappers. Installing and configuring LangChain is necessary for using the Vicuna LLM wrapper. This typically involves installing the LangChain package using a package manager like pip and configuring it to work with the installed Vicuna LLM. Install LangChain using pip install LangChain. This command installs the LangChain package from Python package index pypi. Initialize LangChain and configure the required components. This involves setting up the LangChain environment by importing necessary modules and configuring its components, such as the LLM wrapper, to interact with the Vicuna LLM. Fine-tune parameters. Temperature controls the randomness of the generated text. A higher temperature value leads to more creative and unpredictable responses, while a lower value results in more deterministic and consistent outputs. For example, a temperature of 0.5 might produce responses that are more focused on the prompt's intent, while a temperature of 1.0 could lead to responses with greater variability and potentially unexpected elements. Top P probability threshold for sampling words from the vocabulary. It determines the range of words considered during text generation. A lower top P value narrows the range, resulting in more predictable and conservative outputs, while a higher value widens the range, allowing for more diverse and potentially surprising word choices. For instance, a top P of 0.8 might lead to outputs where the LLM prioritizes words that are highly probable within the context, while a top P of 0.95 could allow for a broader selection of words, potentially including less common but still contextually relevant choices. Top K number of most likely words to consider during sampling. It influences the diversity of the generated text by limiting the number of potential words for a LLM to choose from. A smaller top K value restricts the options, leading to more predictable outputs, while a larger value allows for more variation and potentially unexpected word choices. For instance, a top K of 10 might focus on the most probable words, producing outputs with a higher level of predictability, while a top K of 50 could introduce a greater range of possible words, leading to more diverse and potentially creative responses. Max length, maximum length of the generated text. It sets a limit on the number of tokens or words that the LLM can generate in response to a prompt. This parameter helps control the length of the output, preventing excessively long or short responses. For example, A max length of 100 could limit the LLM to generating a maximum of 100 words, while a max length of 500 would allow for a longer output. Repetition penalty for repeating words or phrases within the generated text. This parameter discourages the LLM from generating repetitive text by penalizing the repeated use of words or phrases. A higher repetition penalty value increases the penalty, resulting in less repetitive outputs, while a lower value decreases the penalty, allowing for more repetition in the generated text. For example, a repetition penalty of 1.2 might discourage the LLM from repeating certain words or phrases, while a repetition penalty of 0.8 might allow for a higher degree of repetition. Challenges and fixes. Challenge 1: the LLM may generate irrelevant or inaccurate information. This challenge arises from the nature of language models, which rely on statistical patterns and may not always be able to accurately interpret or represent real-world knowledge. For instance, a prompt asking for information about a specific historical event might result in an output that includes inaccurate details or misrepresents the event. Ensure that the prompt is clear and specific to guide the LLM to generate accurate responses. A well-defined prompt with precise instructions and relevant context can help the LLM understand the desired output and minimize the risk of generating inaccurate information. For example, instead of a vague prompt like "Tell me about the American Revolution," a more specific prompt like "Describe the key events that led to the American Revolution" is more likely to elicit accurate information. Utilize prompt engineering techniques to enhance the quality of generated text. Prompt engineering involves crafting prompts that guide the LLM towards generating accurate and relevant responses. This includes techniques like providing context, using specific keywords, and structuring prompts in a way that helps the LLM understand the desired output. For instance, a prompt like "Write a short biography about Abraham Lincoln," highlighting his key achievements, uses specific keywords and provides context to guide the LLM in generating a relevant and accurate response. Challenge 2: the LLM may struggle with complex reasoning and knowledge-intensive tasks. Language models are often trained on vast amounts of text data, but their ability to perform complex reasoning and knowledge-intensive tasks may be limited. For instance, a prompt asking the LLM to solve a complex logic puzzle or provide an in-depth analysis of a scientific concept might exceed its capabilities. Consider using a specialized language model for complex tasks. For tasks requiring specialized knowledge or reasoning abilities, a language model trained specifically for that domain might be more suitable. For instance, a language model trained on medical literature could be better suited for answering questions about healthcare, while a language model trained on legal documents could be more effective for providing legal advice. Combine Vicuna with other tools and techniques to augment its capabilities. Integrating Vicuna with other tools and techniques, such as knowledge graphs, search engines, or external APIs, can enhance its ability to handle complex tasks. For example, combining Vicuna with a knowledge graph could provide it with access to a vast repository of structured information, enabling it to answer more complex questions. Challenge 3: the LLM may produce biased or offensive text. Language models are trained on massive datasets of text, which may contain biases and prejudices present in the real world. This can lead to the LLM generating text that reflects these biases, potentially causing harm or offense. For instance, a prompt asking the LLM to write a story about a doctor might result in an output that reinforces gender stereotypes. Ensure that the LLM is trained on a diverse and inclusive dataset. Training the LLM on a dataset that is representative of diverse perspectives and experiences can help mitigate bias in the generated text. This involves ensuring that the dataset includes text from a wide range of sources, authors, and perspectives, representing different cultures, languages, and backgrounds. Employ bias detection and mitigation techniques to reduce bias in generated text. Techniques such as bias detection algorithms and prompt engineering can help identify and address bias in the generated text. Bias detection algorithms can analyze text outputs for potential biases, while prompt engineering techniques can help mitigate bias by crafting prompts that are more inclusive and equitable. Challenge 4: the LLM may generate text that is not coherent or grammatically correct. Language models are trained to predict the next word in a sequence. And while this is effective for generating fluent text, it may not always result in perfectly coherent or grammatically correct outputs. For instance, the LLM might generate sentences with incorrect grammar or introduce inconsistencies in the overall narrative. Use prompt engineering techniques to improve text quality. Prompt engineering can help guide the LLM towards generating more coherent and grammatically correct text. This includes techniques like providing clear instructions, using specific keywords, and structuring the prompt in a way that encourages the LLM to produce well-written outputs. Consider integrating a language editing tool to enhance coherence and grammar. A language editing tool, such as a grammar checker or a style guide, can be integrated with the LLM wrapper to automatically review and improve the generated text for coherence and grammatical accuracy. This can help ensure that the final output is of a high standard, even if the LLM's initial response contains errors or inconsistencies. Prompt Generator Get Prompt Summary. This module is responsible for creating instructions for AutoGPT, a powerful AI agent that can automate tasks. The prompt generator takes context and a defined task as input. Inputs. Context: this refers to the overall background information and details related to the task AutoGPT needs to accomplish. It provides a comprehensive understanding of the situation and the desired outcome. An example of context would be: write a Python script to access the Weather API and retrieve current weather data for New York City. Task: this defines the specific action or objective AutoGPT needs to achieve. It should be clear, concise, and well defined. For instance, a task could be retrieve weather data for New York City using Open Weather Map API. Outputs. Prompt a thoughtfully constructed set of instructions for AutoGPT that guide it to complete the assigned task successfully. The prompt should be formatted in a way that AutoGPT can easily understand and execute. Here's an example of a prompt: use the Open Weather Map API to access current weather data for New York City. Retrieve data for temperature, humidity, and wind speed. Steps. Analyze context and task. Carefully examine the provided context and task to understand the overall objective and identify any essential information or requirements. Identify relevant information for the prompt. Extract specific details from the context and task that are crucial for AutoGPT to understand and execute. For instance, if the task involves using an application programming interface API, ensure the prompt includes API name, endpoint URLs, and required parameters. Structure prompt with clear instructions. Compose a clear and concise prompt with explicit instructions for AutoGPT. Use simple language. Break down complex tasks into smaller steps. And provide any necessary examples or guidelines to ensure successful completion. Prerequisites. Context: a clear and concise description of the task that provides all the necessary background information. It should be well defined, avoiding ambiguity and ensuring a clear understanding of the goal. For example, instead of analyze the market, provide a more specific context like analyze the current market trends for electric vehicles in the United States. Task: a specific and achievable goal that AutoGPT can accomplish within its capabilities. It should be well defined, with a clear objective and scope. An example of a well-defined task would be generate a report on the market trends for electric vehicles in the United States, including sales data, consumer preferences, and industry growth projections. Fine-tune parameters. Prompt length: this parameter determines the desired length of the generated prompt, depending on the complexity of the task and the amount of information required. The prompt length can be adjusted accordingly. For instance, a complex task may require a longer prompt to provide detailed instructions, while a simple task might be sufficiently described with a shorter prompt. Prompt complexity: this parameter refers to the level of detail and complexity required in the generated prompt. A higher prompt complexity would involve more detailed instructions, specific guidelines, and possibly multiple steps to ensure accurate execution. Conversely, a lower prompt complexity might focus on a more straightforward approach with fewer steps and less detailed instructions. Challenges and fixes. Challenge 1: ambiguous or unclear context. If the provided context is unclear or ambiguous, it can lead to inaccurate or incomplete prompts. For example, a context like analyze the market is too broad and lacks specific information. To address this challenge, clarify the context by providing specific details, such as the target market, time frame, or specific aspects to be analyzed. Challenge 2: unrealistic or overly complex task. If the assigned task is overly complex or unrealistic, it might be difficult for AutoGPT to complete successfully. For instance, a task like cure cancer is overly ambitious and outside the capabilities of AutoGPT. To resolve this, simplify the task by breaking it down into smaller, more manageable steps. Alternatively, consider reframing the task to focus on a specific aspect or subproblem that is within the scope of AutoGPT's abilities. Langchain Experimental Chat Models LLM Wrapper Mixtral Summary. This document provides a detailed explanation of the LangChain wrapper for the Mixtral large language model. LangChain is a powerful framework for building and deploying language models. And this wrapper enables seamless integration of Mixtral into LangChain workflows. Inputs. This refers to the text data that is provided as input to the Mixtral model. For example, a user's query, a piece of text to summarize, or a prompt for generating creative content. Outputs. This represents the output generated by the Mixtral model in response to the provided input. The output could be a summarized version of the input text, a generated creative text, or a response to a user's question. Steps. This step involves setting up the Mixtral model within the LangChain environment. This typically involves using the LangChain wrapper to load the Mixtral model and configure it for use. This step involves providing the text input to the Mixtral model. The input could be provided directly to the model or through a LangChain chain that manages the input and output flow. This step involves receiving the output generated by the Mixtral model and processing it as needed. This might involve formatting the output, extracting relevant information, or integrating it into a larger application. Prerequisites. This refers to the necessary software libraries that need to be installed for using the LangChain wrapper with the Mixtral model. LangChain provides a unified interface for working with different language models, making it easier to integrate Mixtral into your projects. This refers to the specific library that provides the Mixtral model and its associated functionalities. Installing this library is essential for using the Mixtral model with LangChain. Fine-tune parameters. These are the settings and configurations that can be adjusted to tailor the behavior of the Mixtral model for specific tasks or domains. Fine-tuning allows you to optimize the model's performance for specific use cases by customizing its parameters. For instance, you can adjust the model's temperature for controlling the randomness of the generated text or change the top K parameter for filtering the model's vocabulary. Challenges and fixes. Integrating Mixtral with LangChain might come with challenges, like setting up the model correctly and ensuring smooth communication between the two frameworks. However, there are solutions to address these issues and optimize the integration process. This refers to troubleshooting steps involved in ensuring the Mixtral model is properly set up and functioning within the LangChain environment. This might involve checking if the necessary libraries are installed, verifying the compatibility of LangChain and Mixtral versions, and resolving any conflicts or dependencies between them. The Mixtral model, like any large language model, might have limitations and biases inherent in its training data and architecture. These issues can impact the model's performance and output quality. It is important to understand and address these challenges to ensure the model produces accurate and reliable results. This refers to the steps taken to address potential issues related to the performance and quality of the Mixtral model's outputs. These steps could include investigating the model's limitations and biases, exploring alternative model parameters or fine-tuning strategies to improve its performance, or considering using alternative language models or techniques if the Mixtral model does not meet specific requirements. LangChain Experimental Comprehend Moderation Base Summary. A LangChain tool that leverages Amazon Comprehends moderation capabilities to assess the suitability of text content. This tool utilizes Amazon Comprehends moderation features to analyze text and identify potentially inappropriate or harmful content. It leverages the power of Amazon Comprehend to help developers and organizations ensure that their text content adheres to community guidelines and policies. Inputs. Text to be moderated. This refers to the text content that needs to be evaluated for its suitability. It could be a comment, a post, a review, or any other form of text content. Outputs. Moderation labels with associated confidence scores. These are the labels assigned to the text based on its content, along with a confidence score indicating the likelihood of the label being accurate. For example, the tool might assign labels like hate speech, violence, or sexual content, with a confidence score ranging from 0 to 1. Steps. Send text to Amazon Comprehend for moderation analysis. This step involves sending the input text to Amazon Comprehend's moderation API. Amazon Comprehend will then analyze the text using its machine learning algorithms to identify any potential issues. Receive moderation labels and confidence scores. Once Amazon Comprehend finishes analyzing the text, it will return a set of labels and confidence scores. The labels represent the potential issues identified in the text, and the confidence scores indicate how likely it is that the label is accurate. Prerequisites. AWS account. An AWS account is required to use Amazon Comprehends Moderation API. This is the central account on the Amazon Web Services platform, providing access to various services like Amazon Comprehend. AWS credentials configured for access to Amazon Comprehend. This refers to the access keys and secret keys associated with your AWS account. These credentials grant your application the necessary permissions to interact with the Amazon Comprehend API. Fine-tune parameters. Language code for text analysis, e.g. NFR. This parameter specifies the language of the input text. It's crucial to provide the correct language code for accurate moderation analysis, as Amazon Comprehend uses different models for different languages. Threshold for confidence scores. To consider a label as applicable, this parameter determines the minimum confidence score required for a label to be considered a valid match. It allows you to customize the sensitivity of the moderation process, depending on your specific requirements and risk tolerance. Challenges and fixes. Rate limits on Amazon Comprehend API calls. Amazon Comprehend imposes rate limits on the number of API calls you can make per second or per minute. Exceeding these limits can result in API throttling, slowing down your application or even preventing it from accessing the service. Handling potential errors during API calls. API calls can sometimes fail due to network issues, service outages, or other unexpected factors. It's important to implement robust error handling mechanisms to gracefully handle such situations, preventing application crashes and ensuring a smooth user experience. LangChain Experimental Comprehend Moderation Base Moderation Config Moderation Prompt Safety Config. Inputs. Text that is input to the model, for example, a user prompt or a query. Text that is generated by the model in response to the input. For example, a response or a generated text. Outputs. A categorization of the safety of the input and response, indicating whether the text contains potentially harmful or inappropriate content. Steps. The input text is provided to the system, which is typically a language model or a chatbot. The model processes the input text and generates a response. The input text and the model response are compared using a predefined set of criteria, analyzing the content for potential risks. Based on the comparison, the system outputs a safety categorization, assigning a label that reflects the level of risk associated with the text. Prerequisites. Amazon Comprehend, a service provided by Amazon Web Services (AWS), is configured and available for use. Fine-tune parameters. Threshold values are set for different safety categories, defining the level of risk that triggers a particular categorization. Challenges and fixes. The system may incorrectly categorize content as safe or unsafe, resulting in false positives or negatives. The threshold values for different safety categories can be refined to improve the accuracy of the categorization, aiming to minimize false positives and negatives. The system may not be able to identify all potential safety risks due to the limitations of its current categorization system. New safety categories can be added to the system, expanding its ability to identify and categorize a wider range of potential risks. LangChain Experimental Chat Models LLM Wrapper Mixtral. A detailed description of the Mixtral LLM wrapper, including its capabilities, inputs, outputs, steps involved, prerequisites, fine-tuning parameters, and potential challenges and fixes. Inputs. The input to the Mixtral LLM wrapper is a text prompt, which is the text that the user wants the model to generate a response to. For example, the user may provide a prompt such as write a poem about a cat. Outputs. The output of the Mixtral LLM wrapper is a generated text response based on the input prompt. The generated text can take many forms, including poems, stories, articles, summaries, and translations. The response is determined by the model's training data and the specific parameters used during generation. Steps. The first step in using the Mixtral LLM wrapper is to initialize the Mixtral model. This involves loading the model's weights and parameters into memory, which allows the model to be used for text generation. Once the Mixtral model is initialized, the user's text prompt is sent to the model. The model then processes the prompt and uses its knowledge to generate a corresponding response. The final step is to receive the generated text from the Mixtral model. This text is then returned to the user as the output of the LLM wrapper. Prerequisites. Python is a widely used, high-level programming language known for its readability and versatility. It's a key requirement for utilizing the Mixtral LLM wrapper, as it provides the necessary environment for running the wrapper's code. The Mixtral library is a Python library that provides access to the Mixtral language model. It allows users to interact with the model and perform tasks like text generation, translation, and summarization. Having this library installed is essential for leveraging the capabilities of the Mixtral LLM wrapper. Fine-tune parameters. Temperature is a hyperparameter used in language models to control the creativity and randomness of the generated text. A higher temperature value increases the model's tendency to generate more unpredictable and diverse outputs, while a lower temperature value results in more predictable and consistent responses. For example, a higher temperature might encourage the model to explore more unconventional word choices or sentence structures, while a lower temperature might lead to a more conservative and predictable output. Top K is a parameter that limits the number of possible words the model considers at each prediction step during text generation. For example, with a top K value of 10, the model would only consider the 10 most likely words at each step, effectively limiting the potential output space. This parameter can help control the diversity and quality of the generated text, potentially reducing the risk of generating nonsensical or repetitive content. Top P is a parameter that controls the probability distribution of the model's word predictions during text generation. It works by setting a threshold, P, and selecting words whose cumulative probability exceeds that threshold. For example, with a top P value of 0.9, the model would select words whose cumulative probability reaches 90 or more, effectively excluding low probability words from the prediction space. This helps to ensure that the model generates more relevant and coherent text, reducing the likelihood of generating nonsensical or irrelevant content. Challenges and fixes. A common challenge when working with language models is that they may not always generate coherent and meaningful text. This could be due to factors like the model's training data, the complexity of the prompt, or the parameter settings used during text generation. Adjusting temperature, top K, and top P parameters can significantly influence the quality and coherence of the generated text. Temperature controls the model's creativity. Top K limits the vocabulary, and top P influences the probability distribution of word choices. By experimenting with these parameters, users can find settings that produce more coherent and relevant responses. For example, Lowering the temperature might result in more predictable and well-structured text, while increasing top K could introduce more diverse word choices, potentially enhancing creativity. Another challenge is that language models, especially large ones, can take a significant amount of time to generate responses. This can be attributed to the complexity of the model's calculations and the extensive processing required to generate meaningful text. One potential fix for this is to reduce the length of the input prompt. A shorter prompt can simplify the task for the model, leading to faster generation times. Additionally, if possible, users can consider using a smaller language model. Smaller models generally require less computational resources and can therefore generate responses more quickly. For example, if the prompt is complex and requires a lot of processing, using a smaller model or shortening the prompt could significantly reduce generation time. Langchain-experimental comprehend moderation base moderation exceptions moderation P error. This error is raised by the moderation system when it detects potentially personally identifiable information P within the input text. P refers to data that can be used to identify an individual, such as names, addresses, social security numbers, or credit card details. The moderation system is designed to prevent the disclosure of such sensitive information. And this error signifies that the input text has been flagged for containing P. Inputs: the input text that is being processed by the moderation system. This text is analyzed to determine if it contains any P. For example, if a user submits a review that includes their full name and address, this text would be considered an input. Outputs: an error message is generated indicating that the moderation system has detected P in the input text. This error message typically provides details about the detected P and may include suggestions for how to resolve the issue, such as removing or redacting the P from the input text. Steps: the moderation system analyzes the input text using a pre-trained model or algorithm specifically designed to identify P. This analysis involves comparing the text against a database of known P patterns and identifiers. If the system finds any matching patterns, it flags the text as potentially containing P. If the analysis determines that the input text contains P, the moderation system raises the moderation P error. This error is then handled by the application or system that invoked the moderation process, potentially triggering actions like preventing the text from being published or requiring the user to modify the input to remove the P. Prerequisites: the Amazon Comprehend service, a cloud-based natural language processing (NLP) service offered by Amazon Web Services (AWS, needs to be installed and configured. Comprehend provides pre-trained models for analyzing text, including identifying P. The moderation system relies on Comprehend's capabilities to perform the P detection analysis. Challenges and fixes: the P detection model may sometimes flag text that does not actually contain P, resulting in a false positive. This can occur due to the complexity of identifying P across various contexts and languages. To mitigate false positives, the P detection settings can be reviewed and adjusted. This involves configuring the model's sensitivity levels and thresholds, allowing for a more nuanced analysis that reduces the likelihood of mistakenly identifying non-PII content as P. Additionally, training the model with more specific and context-aware data can improve its accuracy. The P detection logic may struggle to recognize complex P patterns or variations. This can lead to cases where P is present but not detected, potentially resulting in a false negative. For instance, A phone number that is disguised using punctuation or special characters might not be recognized by a standard P detection system. To overcome this challenge, the P detection logic needs to be enhanced. This involves incorporating more sophisticated algorithms and expanding the database of P patterns to include more intricate and context-dependent variations. Regular updates to the model and logic are essential to stay ahead of evolving P obfuscation techniques and ensure comprehensive detection. Moderation toxicity config summary. A langchain moderation config for assessing the toxicity of text. This configuration defines the input, output, steps, prerequisites, fine-tuning parameters and challenges along with their fixes for moderating text content based on its toxicity. Inputs. Text to be moderated. The text that will be analyzed for potential toxicity. This input is the raw text content that needs to be moderated. Outputs. Toxicity score. This is a numerical score representing the level of toxicity detected in the text. A higher score indicates more toxic content. Moderation labels. These are labels indicating specific types of toxicity detected in the text. For example, hate speech, violence, or sexual content could be detected. Steps. Tokenize input text. This involves breaking down the input text into individual words or units called tokens. This is necessary for most natural language processing tasks, including toxicity detection. Send tokens to moderation API. The tokens are then sent to a moderation API, which is a service specifically designed to analyze text for toxicity. Receive toxicity score and labels. The moderation API returns a toxicity score and associated labels based on the provided tokens. This information provides a comprehensive assessment of the text's toxicity. Prerequisites. Amazon Comprehend API key. This is a unique identifier that grants access to the Amazon Comprehend API, which provides natural language processing capabilities, including toxicity detection. It is used for authenticating requests sent to the Amazon Comprehend API. Your Amazon Comprehend API key. This is the specific API key you have obtained from Amazon Comprehend to access its services. It's crucial to ensure this key is valid and securely stored. Amazon Comprehend API endpoint. The API endpoint is the specific address of the Amazon Comprehend API service. This is where your requests are directed for processing. It's important to have the correct endpoint to ensure successful communication with the API. Your Amazon Comprehend API endpoint. This is the specific API endpoint you use to interact with the Amazon Comprehend API. It is usually a unique URL provided by Amazon Comprehend. Fine-tune parameters. Threshold. The toxicity score threshold for triggering moderation. This determines the level of toxicity that triggers moderation actions, such as blocking or flagging the content. Labels. A list of moderation labels to check for. This specifies the particular types of toxic content that you are interested in detecting. For example, you might want to check for hate speech, violence, or sexual content. Challenges and fixes. Incorrect API key. This happens if the provided API key is invalid, expired, or does not have the required permissions to access the Amazon Comprehend API. Ensure the API key is correct and has the necessary permissions. Double-check the API key you are using and make sure it's valid and has the right permissions for accessing the Amazon Comprehend API. Incorrect API endpoint. This occurs if the API endpoint used in the request is incorrect or inaccessible. Ensure the API endpoint is correct and accessible. Make sure you are using the correct endpoint provided by Amazon Comprehend. Verify that the endpoint is accessible and that there are no network issues preventing Communication. Rate limiting. This happens when the number of requests sent to the API exceeds the allowed rate limit. Implement a rate limiting mechanism to avoid exceeding the API request limit. To avoid exceeding the API request limit, you can implement a rate limiting mechanism to control the number of requests sent per unit of time. This can involve adding delays or queuing requests to ensure you stay within the API's limitations. API errors. These are errors that may occur during communication with the Amazon Comprehend API, such as network issues, server errors, or authentication failures. Handle API errors gracefully and retry requests if necessary. When handling API errors, it's crucial to implement appropriate error handling mechanisms. This involves catching and logging errors gracefully. For transient errors, you may want to retry the request after a short delay. Langchainexperimental, comprehend moderation, base moderation exceptions, moderation toxicity error. This error is raised when the text provided for moderation is detected as containing toxic content. Toxicity can refer to various forms of harmful language such as hate speech, threats, bullying, or obscenities. The detection is performed by a machine learning model trained to identify such content. Inputs. The text input for this error is the content that needs to be moderated. This could be a user comment, a social media post, or any other text that needs to be evaluated for its potential toxicity. Outputs. The output of this error is an error message that indicates that the text was detected as toxic. The message might include additional information about the specific type of toxicity detected or the confidence level of the detection. Steps. The moderation toxicity error is raised after a series of steps. The provided text is first analyzed for toxicity by a machine learning model. This model has been trained on a large dataset of text and its associated toxicity labels. If the model determines that the text is toxic, based on its training and analysis, it will raise the moderation toxicity error. Prerequisites. For this error to be raised, the Amazon Comprehend service needs to be properly configured. Amazon Comprehend is a natural language processing service that provides various functionalities, including sentiment analysis, entity recognition, and moderation. To effectively use the moderation capabilities, the service must be set up and configured with the appropriate access credentials. Fine-tune parameters. The threshold for toxicity detection is a key parameter in the moderation process. It determines the sensitivity of the model to identifying toxic content. A higher threshold indicates that the model needs a higher level of confidence to classify text as toxic, resulting in fewer false positives but potentially missing some harmful content. Conversely, a lower threshold makes the model more sensitive, detecting more toxic content but potentially leading to more false positives. Fine-tuning this threshold allows you to balance between sensitivity and accuracy in your moderation system. Challenges and fixes. False positive detection. When the moderation system incorrectly labels non-toxic text as toxic, it's known as a false positive. This can be a problem because it can lead to the censorship of legitimate content. To mitigate false positives, one can review the moderation parameters, such as the threshold for toxicity detection. Adjusting the threshold can improve the model's accuracy and reduce false positives. Error handling. Robust error handling is crucial in a moderation system to ensure smooth operation and graceful handling of unexpected issues. When the moderation process encounters an error, the system should have a mechanism to gracefully handle the exception. This might involve logging the error, attempting to retry the moderation, or providing a fallback mechanism. Implementing proper error handling prevents the system from crashing and ensures a seamless user experience. Langchain experimental comprehend moderation base moderation exceptions moderation P error. This exception is raised by the moderation process when it detects potentially personally identifiable information P within the input text. This signifies that the text might contain sensitive data like names, addresses, or financial details, which should not be shared publicly or without proper authorization. Inputs: the input text that is being analyzed by the moderation process. This text could be a user-generated comment, a social media post, or any other type of text that requires moderation. Outputs: an error message is generated to signal the presence of P within the input text. This message typically includes information about the detected P, such as the type of information identified and its location within the text. Steps: the input text is subjected to analysis using Amazon Comprehends P detection capabilities. Amazon Comprehend is a natural language processing service from Amazon Web Services (AWS) that can identify various types of information within text, including P. If the P detection process identifies any potentially sensitive information within the input text, the moderation P error is raised. This indicates that the text requires further review or action before it can be shared or used. Prerequisites: Amazon Comprehend must be properly configured and accessible to the moderation process. This involves setting up an Amazon Comprehend account, granting the necessary permissions, and ensuring that the service is running and available. The moderation process itself must be enabled and configured to utilize Amazon Comprehend's P detection capabilities. This involves specifying the appropriate settings for the moderation process, such as the sensitivity level for P detection and the actions to be taken when P is detected. Fine-tune parameters. There are no specific fine-tune parameters available for this exception. Challenges and fixes. If P is detected within the input text, it is essential to take steps to address the issue. Review the input text carefully to identify the specific instances of P. This may involve manually inspecting the text or using tools to highlight potentially sensitive information. Once the P has been identified, consider the following options. Remove the P from the text entirely. This is the most straightforward approach, especially if the P is not crucial to the message. Mask or redact the P. This involves replacing the sensitive information with characters or symbols, such as asterisks. This approach allows you to maintain the context of the text while protecting the P. Obtain consent from the individuals whose P is included. In some cases, it may be necessary to obtain permission from the individuals whose P is included in the text before sharing or using the text. False positive P detection can occur when the moderation process mistakenly identifies non-sensitive information as P. Adjust the moderation settings to reduce the likelihood of false positives. This may involve increasing the sensitivity threshold for P detection or configuring custom P entities that match the specific types of information that should be flagged as P. Configure custom P entities to provide more precise guidance to the moderation process. This involves defining specific patterns or keywords that should be recognized as P, allowing for more accurate detection and reducing the occurrence of false positives. For instance, you could define a custom P entity to identify specific formats for phone numbers or email addresses, reducing the chance of mistakenly flagging common text strings as P. This helps the moderation process to focus on truly sensitive information, improving accuracy and efficiency. Langchain experimental comprehend moderation prompt safety comprehend prompt safety. A moderation tool that utilizes Amazon Comprehend for content analysis and filtering. It evaluates text for potentially harmful or inappropriate content based on predefined categories. Inputs: the text that needs to be checked for moderation. For example, a user comment, social media post, or website content. Outputs: the results of the moderation process, indicating whether the text is considered safe or unsafe based on the defined categories. Steps: the input text is sent to the Amazon Comprehend service via the application programming interface. API. Amazon Comprehend analyzes the text and identifies potential issues based on the pre-configured moderation categories. The results of the analysis, including any flagged issues and their severity, are returned to the user. Prerequisites: an AWS Amazon Web Services account with necessary credentials to access and utilize Amazon Comprehend. This includes an access key ID and a secret access key, which are used for authentication. The Amazon Comprehend service needs to be enabled and properly configured within the AWS account. This includes setting up the necessary permissions and ensuring that the service is active. Fine-tune parameters: the threshold for moderation, which determines the level of severity required for a content item to be flagged as unsafe. A higher threshold means only highly offensive content will be flagged. A lower threshold will result in more content being flagged. The list of categories to moderate. Defining the types of content to be flagged. This could include categories like hate speech, violence, sexual content, or spam. The user defines this list according to their specific needs. Challenges and fixes: if the provided AWS access keys are incorrect or expired, the tool cannot connect to Amazon Comprehend. To resolve this, verify the keys and update them with the correct values. If the tool lacks the necessary permissions to interact with Amazon Comprehend, it cannot analyze the content. Granting appropriate permissions to the tool will address this issue. If the Amazon Comprehend service is unavailable, the tool cannot complete its tasks. Check the service status and attempt to retry later. If there are delays in communication with Amazon Comprehend, the moderation process might become inefficient. Optimize the code to improve communication efficiency and reduce latency. If the moderation categories are not accurately defined, the tool may fail to identify specific types of inappropriate content. Update the list of categories to reflect the desired moderation criteria. If the threshold for moderation is set too high, the tool may miss potentially harmful content. Adjust the threshold to a lower value to increase sensitivity. If the threshold is set too low, the tool may flag harmless content as unsafe. Increase the threshold to reduce the number of false positives. If the tool exceeds the rate limits of the Amazon Comprehend service, its functionality may be restricted. Implement a rate limiting strategy to ensure that requests are sent within the defined limits. Langchain experimental comprehend moderation P comprehend PII summary. This tool leverages Amazon Comprehend, a service that analyzes text for understanding, to identify and mask personally identifiable information P in text. P refers to any data that can be used to identify a specific individual, like names, addresses, or social security numbers. By masking this sensitive data, this tool helps ensure privacy and compliance with data protection regulations. Inputs: this tool requires text as input, which will be analyzed for the presence of P. For example, a document containing customer information or a social media post with personal details. Outputs: The output is the original text with all identified P masked. This means the tool replaces sensitive information with placeholder values, effectively obscuring the original data while preserving the context of the text. For example, a customer's name might be replaced with name or a phone number with phone. Steps. The tool first uses Amazon Comprehend to analyze the input text. Comprehend examines the text to identify potential P based on predefined entity types, such as names, addresses, and dates. This analysis leverages machine learning and natural language processing (NLP) techniques. Once Comprehend identifies P, the tool then proceeds to mask it. This involves replacing the detected P with placeholder values. This masking process helps to protect sensitive data while preserving the original text structure and readability. Prerequisites. To use this tool, you need an AWS account, which is a platform for building, deploying, and managing cloud applications. This account must have access to the AWS Access Key ID and Secret Access Key, which are credentials used to authenticate requests to AWS services. This tool relies on the Comprehend service, a service within AWS that provides natural language processing capabilities. This service analyzes text to extract insights and understand the meaning of words, phrases, and sentences. Fine-tune parameters. This parameter, P entity types, allows you to customize the types of P that the tool will identify. This customization enables the tool to be more specific in its analysis and masking process. For example, you can choose to focus on identifying names and addresses while ignoring other types of P, like email addresses or phone numbers. Challenges and fixes. While effective, this tool can sometimes misidentify P, leading to false positives. For example, it might misinterpret a common phrase like Social Security as a reference to the Social Security number. To address this, you can use a custom model trained on specific domain data. This means tailoring the model to the specific language and context of the text being analyzed, improving its accuracy in identifying P. The performance of the tool might be limited by factors like the size of the input text and the complexity of the P patterns. To address these performance limitations, you can optimize the code for efficiency. This can involve techniques like parallelizing computations, using more efficient algorithms, or optimizing data structures. LangchainExperimental CPAL Summary. A summary of the LangchainExperimental CPAL library, a powerful tool for building and using language chains in Python. Inputs, LLM, an essential component for any language chain, refers to a large language model. These are powerful AI models trained on massive datasets of text and code. They can understand and generate human-like text, translate languages, write different kinds of creative content, and answer your questions in an informative way. Popular examples include models like GPT-3, BERT, and Lambda. Prompt. A crucial element in interacting with a LLM is a text-based instruction that guides the model towards generating the desired output. A prompt serves as a query or request, providing context and specific instructions for the LLM. A prompt can be a simple question, a creative writing prompt, or a request to translate a text from one language to another. Outputs. Chain output represents the result generated by the language chain. This could be a summarized text, a creative story, a translated text, a code snippet, or any other output based on the prompts and logic embedded within the chain. The output is directly tied to the input prompts and the processing steps within the chain. Steps. Initialize chain with CPAL involves setting up the language chain using the CPAL library. This step typically involves defining the desired LLM, the prompt, and the specific chain structure. This might include defining the order of tasks, the type of chain, e.g., a sequential chain or a question-answering chain, and the logic of how the LLM interacts with the data and other components within the chain. Run chain with prompt is the execution phase of the language chain. This step involves providing the prepared prompt to the chain, which then uses the LLM to process the information and generate the desired output based on a defined chain structure. The prompt can be a specific question, a set of instructions, or a piece of text to be summarized. Prerequisites. Install langchainexperimental means setting up the langchainexperimental library in your Python environment. This library is necessary for using the CPAL functionality, which allows you to construct and utilize language chains in your applications. Installation typically involves using the pip package manager to install the langchainexperimental package. Fine-tune parameters. LLM model refers to the specific large language model used within the language chain. Choosing the right LLM is essential for the quality of the output and can depend on the specific task and the desired results. Factors to consider include the model's size, training data, and capabilities. Some LLMs are better suited for specific tasks, like code generation, translation, or creative writing. Challenges and fixes. LLM unavailability refers to situations where the chosen LLM is not accessible or cannot be contacted. This could be due to network issues, server downtime, or limits on the number of API calls. Check for LLM access involves verifying that the LLM is reachable and available for use. This typically involves checking the network connection, ensuring the LLM's API endpoint is operational, and confirming that any usage quotas or limits have not been exceeded. Invalid prompt format refers to instances where the prompt provided to the LLM is not structured correctly or does not align with the expectations of the model. This can lead to unexpected or incorrect outputs. Correct prompt format involves ensuring the prompt is well structured, clear, and unambiguous. It should be tailored to the specific LLM and the desired task. Examples of common prompt formatting issues include incomplete instructions, lack of context, or using ambiguous language. Correcting the prompt format often involves revising the prompt to provide more specific instructions, relevant context, and clear language to guide the LLM towards the intended outcome. LangChain Experimental CPAL Summary. A descriptive overview of CPAL chain of prompt-assisted language is presented here. CPAL is a framework designed to create chains of prompts. These chains can be used for complex language tasks, like text summarization, question answering, or creative writing. It leverages the power of language models to perform these tasks iteratively by refining prompts based on generated outputs. Inputs. Input prompts are the initial prompts that are used to start the chain. They are the starting point for the iterative process. Relevant context refers to any additional information that is helpful for the language model to understand the task. This can include background information, specific instructions, or examples of desired outputs. Outputs. Desired output format specifies the expected form of the final output. For instance, it could be a concise summary, a creative story, or a list of answers to specific questions. Steps. Define the initial prompt as the first step. This involves carefully crafting a prompt that accurately reflects the task and guides the language model in the right direction. Generate an initial response using a language model involves using the language model to produce an initial output based on the defined prompt. Use the response to create a new refined prompt is the key part of the iterative process. The generated response is analyzed and used to improve the prompt for the next iteration, leading to more accurate and relevant outputs. Iterate until desired output is achieved is the final stage. This involves repeating the process of generating a response, refining the prompt, and generating a new response until the output meets the specified criteria. Prerequisites. A language model is essential for CPAL. It is the engine that generates the responses. Common language models include OpenAI's GPT-3, Google's BERT, or Hugging Face's models. For access to these models, you'll need OpenAI API key and authentication key from OpenAI to access their models. Google AI Platform API key and authentication key from Google to access their AI platform and models. Hugging Face API token, a token from Hugging Face to access their vast repository of pre-trained models. Prompt engineering skills are crucial for successful CPAL implementation. Prompt engineering involves crafting effective prompts that guide language models towards desired outputs. This requires understanding of language model capabilities, familiarity with the strengths and weaknesses of the chosen language model to optimize prompts for its specific capabilities. Ability to craft clear and concise prompt skills in expressing task instructions and desired output formats clearly and concisely. Fine-tune parameters. Number of iterations refers to the number of times the prompt is refined and the language model is used to generate a new response. The ideal number of iterations depends on the complexity of the task and the desired level of refinement. Prompt engineering techniques are strategies used to improve the effectiveness of prompts. These include techniques like providing context, using examples, and specifying constraints. By applying these techniques, the prompts can be tailored to elicit desired outputs from the language model. Challenges and fixes. Overfitting to specific data refers to a situation where the language model learns to generate outputs that are too closely tied to the training data. This can lead to issues with generalization to new data. To address this, introduce diversity in training data, expanding the training data to include a variety of examples helps prevent overfitting by exposing the model to a wider range of input. Use different language models, employing multiple language models with different training data and architectures can further mitigate overfitting by providing diverse perspectives and reducing reliance on a single model's biases. Prompt ambiguity refers to cases where the prompt is unclear or open to interpretation. This can lead to inconsistent or inaccurate responses from the language model. To solve this, clarify prompt instructions, ensuring that the instructions are clear and specific. Helps avoid ambiguity by reducing the room for misinterpretations. Use more specific examples. Providing concrete examples of desired outputs helps the language model understand the task requirements and generate more accurate responses. Implement prompt engineering techniques. Leveraging prompt engineering techniques like constraints, formatting, and specific instructions helps guide the language model towards the desired output format and reduce ambiguity. Ability to analyze and interpret text. The chain must be able to effectively analyze text to extract relevant information and identify relationships between events. This includes understanding the context, identifying key entities, and recognizing relationships between them. For example, in a text describing a car accident, the chain should be able to identify the vehicles involved, the time and location of the accident, and any other relevant details. Extract relevant information. The chain should be able to extract relevant information from text, focusing on the key events and their potential causes related to the input question. This involves identifying relevant keywords, entities, and their relationships within the context. For example, if the input question is "Why did the car crash?" the chain should extract information about the vehicles, the road conditions, and any actions by the drivers that might have contributed to the accident. Identify relationships between events. The chain should be able to identify relationships between events mentioned in the text. This includes recognizing temporal relationships, e.g., event A happened before event B. Causal relationships, e.g., event A caused event B. And other relevant connections between events. For example, the chain should be able to understand that a speeding car exceeding the speed limit, followed by a sudden braking maneuver, and a subsequent collision are related events, and that the speeding might have been a contributing factor to the crash. Language model capabilities. The chain needs the capability of a language model to process text, generate coherent responses, and understand the nuances of language. This includes the ability to comprehend the context of the provided text, understand the meaning of words and phrases, and generate text that is relevant, coherent, and grammatically correct. For example, the chain should be able to understand the difference between the car was speeding and the car was parked, and generate a response that is grammatically correct and reflects the information extracted from the context. Text generation. The chain must be able to generate coherent and grammatically correct text, both for the answer and the explanation. This includes constructing sentences and paragraphs that express the causal reasoning process clearly and accurately. For example, the chain should be able to generate a response like "The car crashed because it was speeding and the driver had to brake suddenly, causing the car to lose control." Text comprehension. The chain needs to understand the text it receives as input, extracting relevant information and interpreting the relationships between events. This includes comprehending the context, understanding the meaning of words and phrases, and recognizing the implications of different actions and events. For example, the chain should be able to understand that the car was speeding implies a higher risk of an accident, and that the driver had to brake suddenly implies an unexpected event or obstacle. Fine-tune parameters. Causal reasoning temperature. This parameter controls the randomness of the generated response. A higher temperature leads to more creative and unexpected responses, while a lower temperature leads to more predictable and consistent responses. This parameter allows the user to adjust the level of creativity and randomness in the causal analysis and explanation generated by the chain. For example, a higher temperature might lead to more speculative and alternative explanations, while a lower temperature would focus on the most likely and direct causal relationships. Causal reasoning top K. This parameter limits the number of candidate responses considered by the chain during K generation process. A higher value increases the number of potential responses considered, leading to a wider range of possibilities. A lower value restricts the search to a smaller number of candidates, focusing on the most probable and relevant responses. This parameter helps to control the scope of the chain's search for causal explanations and answer generation, allowing for a more focused or exploratory approach depending on the user's needs. Challenges and fixes. Lack of sufficient causal context. This challenge arises when the provided causal context does not contain enough information to analyze the event in question and provide a complete causal explanation. For example, If the input question is why did the company go bankrupt? But the causal context only mentions the company's recent financial losses, the chain might struggle to provide a comprehensive explanation. The solution is to provide a more comprehensive and relevant causal context. This could include information about the company's financial history, its market performance, its competitive landscape, and any other factors that might have contributed to its bankruptcy. Ambiguity in the input question. This challenge occurs when the input question is unclear or open to multiple interpretations, making it difficult for the chain to accurately identify the event in question and its potential causes. For example, if the input question is why did the world change? It's too broad and ambiguous to provide a definitive answer. The solution is to rephrase the question to make it more specific. For example, instead of why did the world change? A better question could be what were the key factors that led to the rise of the Internet in the late 20th century? Difficulty in identifying causal relationships. This challenge can arise when the causal relationships between events are complex, subtle, or not explicitly stated in the causal context. For example, it might be difficult to identify the specific causes of a political revolution, as it could be driven by a combination of economic, social, and political factors. The solution is to fine-tune the chain on a dataset of causal reasoning examples. This dataset could include examples of different types of causal relationships, different levels of complexity, and different domains, such as history, economics, science, and social sciences. This would help the chain learn to recognize and interpret complex causal patterns, even in the absence of explicit statements. Inaccurate or irrelevant explanation. This challenge arises when the chain generates an explanation that is not accurate, does not fully address the input question, or includes irrelevant information. This could occur due to biases in the training data, limitations in the chain's understanding of causal relationships, or simply errors in its reasoning process. The solution is to review the generated explanation and revise it as needed. This could involve comparing the explanation to the original causal context, identifying any inconsistencies or missing information, and rephrasing or adding details to ensure accuracy and relevance. This also highlights the importance of human oversight and intervention in the use of causal reasoning chains. Langchain-experimental comprehend moderation prompt safety. Comprehend prompt safety. Comprehend prompt safety is a tool for detecting potentially unsafe or inappropriate prompts. It leverages Amazon Comprehend's sentiment analysis and topic modeling capabilities to identify prompts that might contain offensive language, hate speech, or other harmful content. For example, the tool can be used to identify prompts that contain racial slurs, threats of violence, or other forms of harmful content. This can help to prevent the generation of harmful or offensive text by language models. Inputs. The prompt to be analyzed is a text string that is provided as input to the Comprehend prompt safety tool. This text string is then passed to Amazon Comprehend's application programming interface API for analysis. Outputs. The safety score is a numerical value that represents the likelihood that the prompt is safe or unsafe. This score is determined by Amazon Comprehend based on its analysis of the prompt. The reason for safety score is a text string that explains the reasoning behind the safety score. This reasoning is based on the results of Amazon Comprehend's analysis of the prompt. Steps. The prompt is sent to Amazon Comprehend for analysis. This involves sending the prompt text to the Amazon Comprehend API. Comprehend analyzes the prompt for sentiment, topic, and potentially unsafe content. This analysis uses Amazon Comprehends natural language processing capabilities to understand the meaning of the prompt and identify any potentially harmful content. A safety score is calculated based on the analysis results. This score is a numerical value that represents the likelihood that the prompt is safe or unsafe. The score is based on the results of Amazon Comprehends analysis, taking into account factors such as the sentiment of the text, the topics covered, and the presence of potentially harmful language. The safety score and the reasoning behind it are returned to the user. The safety score and the reasoning are provided as output from the Comprehend prompt safety tool. This allows users to understand the risk associated with the prompt and make informed decisions about how to proceed. Prerequisites. Amazon Comprehend access is required to use the Comprehend prompt safety tool. This involves having an account with Amazon Web Services (AWS) and setting up access to the Amazon Comprehend service. Challenges and fixes. Prompt is too long or complex for Comprehend to process efficiently. This can occur if the prompt contains a large amount of text or if it is structured in a way that makes it difficult for Comprehend to analyze. Use prompt shortening techniques. This involves reducing the length of the prompt or simplifying its structure. For example, users can try to summarize the prompt or break it down into smaller, more manageable chunks. Comprehend's analysis may not be perfect and may miss some unsafe content. This is due to the inherent limitations of natural language processing technology. It is important to note that Amazon Comprehend is not a foolproof solution for identifying all unsafe content. Use multiple safety tools in conjunction with Comprehend prompt safety. This involves using other safety tools, such as those based on machine learning or human moderation, to complement Comprehend's analysis. This can help to increase the accuracy of safety detection and reduce the likelihood of missing unsafe content. Langchainexperimental CPAL-based causal chain is a language model designed for causal reasoning. NaN. The causal chain is a large language model designed for causal reasoning and understanding. This model can predict the effects of actions, understand the causes of events, and generate explanations for causal relationships. It's like having a super intelligent assistant that can analyze situations and tell you why things happened or what might happen next, based on cause and effect. Inputs. The input text should contain a description of the scenario, the action being taken, and the desired outcome. For example, you could input imagine a person wants to buy a new car. They need to find out how much they can afford and what financing options are available. They want to know what their monthly payment would be for different car models. Outputs. The output is a causal explanation for the given input text, along with a prediction of the outcome. The output will highlight the key causal relationships that led to the predicted outcome. For example, the output for the input above could be based on the person's income and credit score. They can afford a monthly payment of $500. They could choose a car model that fits within that budget. The outcome is that they can buy a car within their financial capabilities. Steps. The input text is first processed by a transformer-based language model, which extracts the key entities and relationships. This is similar to how a human might read a story and identify the characters, objects, and their connections. For example, in the car buying scenario, the entities would be the person, the car, the price, the income, and the credit score. The relationships would be things like the person wants to buy the car, the person has an income, and the car has a price. The extracted information is then used to construct the causal graph, which represents the causal relationships between the entities. This is like creating a diagram that shows how different elements affect each other. For instance, the graph might show that the person's income influences how much they can afford, which then affects the types of cars they can consider. The causal graph is then used to predict the outcome of the action. The model analyzes the relationships in the graph to determine what is likely to happen next. In our car buying example, the model might predict that the person will choose a car within their affordability range. Finally, the model generates a causal explanation for the predicted outcome, highlighting the key causal relationships that led to the outcome. This explanation would be a clear description of why the predicted outcome is likely, based on the connections between the entities and their effects. In our car buying example, the explanation might say based on the person's income and their desired monthly payment, they can afford a car in the 15,000 to 20,000 price range. This leads to the prediction that they will choose a car within this price range. Prerequisites. For the causal chain to work effectively, the input text should be clear and concise. It needs to clearly describe the scenario, the action being taken, and the desired outcome. Avoid jargon or ambiguous language. Fine-tune parameters. The model's performance on specific causal reasoning tasks can be improved by adjusting its fine-tuning parameters. These parameters control how the model learns and can be optimized for particular types of causal reasoning problems, such as predicting the impact of policy changes or understanding the causes of historical events. Challenges and fixes. Challenges in causal reasoning include handling complex causal relationships, where multiple factors interact in intricate ways, and uncertainties in the input text, where information might be incomplete or ambiguous. Fixes for these challenges involve incorporating domain-specific knowledge, which can provide context and insights into the specific area of causal reasoning. For example, understanding the relationship between economic policies and inflation requires knowledge of economics. The model can also employ probabilistic reasoning techniques, which allow it to handle uncertainty by considering multiple possibilities and their associated probabilities. This helps in making predictions and explanations that account for the inherent uncertainty in the world. Langchain experimental CPAL-based causal chain summary. None. A chain for running causal reasoning tasks using a causal language model. A causal language model is a language model that can understand and generate causal relationships between events. This chain can be used to perform various causal reasoning tasks such as identifying the cause of an event, predicting the effect of an action, or explaining the relationship between two events. Inputs. A prompt for the causal language model. The prompt should be a question that asks the causal language model to identify the cause of an event, predict the effect of an action, or explain the relationship between two events. For example, what is the causal relationship between the rain and the flood? The context for the causal language model. The context should provide the causal language model with information about the events involved in the causal reasoning task. For example, the context might include a news article about a recent flood. Outputs. The response from the causal language model. The response from the causal language model should be a statement that explains the causal relationship between the events involved in the causal reasoning task. For example, the causal language model might respond to the prompt, what is the causal relationship between the rain and the flood? With the rain caused the flood by filling up the river and causing it to overflow. Steps. Initialize a causal language model. The first step in the chain is to initialize a causal language model. This can be done by loading a pre-trained causal language model from a library or by training a new causal language model. Process the prompt and context using the causal language model. The next step in the chain is to process the prompt and context using the causal language model. This involves feeding the prompt and context to the causal language model and then waiting for the causal language model to generate a response. Return the response from the causal language model. The final step in the chain is to return the response from the causal language model. This response will be a statement that explains the causal relationship between the events involved in the causal reasoning task. Prerequisites. A causal language model. A causal language model is a language model that can understand and generate causal relationships between events. Some examples of causal language models are GPT-3, GPT-4, and PaLM. A prompt for the causal language model. The prompt should be a question that asks the causal language model to identify the cause of an event, predict the effect of an action, or explain the relationship between two events. For example, what is the causal relationship between the rain and the flood? Fine-tune parameters. The temperature of the causal language model. Temperature is a parameter that controls the randomness of the causal language model's output. A higher temperature will result in more random outputs, while a lower temperature will result in more deterministic outputs. The top P of the causal language model. Top P is a parameter that controls the probability of the causal language model's output. A higher top P will result in the causal language model being more likely to generate outputs that are consistent with the prompt, while a lower top P will result in the causal language model being more likely to generate outputs that are unexpected. Challenges and fixes. The causal language model may not be able to generate accurate causal inferences. The causal language model may not be able to generate accurate causal inferences if it is not trained on a dataset of causal relationships. This can be fixed by training the causal language model on a dataset of causal relationships. The causal language model may not be able to understand the context of the prompt. The causal language model may not be able to understand the context of the prompt if it is not given enough information about the events involved in the causal reasoning task. This can be fixed by providing the causal language model with more context. For example, the context might include a news article about a recent flood, or a description of the events that led to the flood. Intervention chain summary. Intervention chain is a langchain chain that uses a conversational prompt assistant CPA to improve user-agent interactions. It facilitates intervention based on user input and agent response. Inputs. This describes the expected input data types required for the intervention chain. The user input is the text or query provided by the user to the agent. For example, what is the weather like in London? The agent response is the text generated by the agent in response to the user input. For example, the weather in London is sunny and 25 degrees Celsius. Outputs. This describes the expected output data type generated by the intervention chain. The intervention is a text message generated by the CPA to suggest improvements or changes to the agent's response. For example, you could also mention that the weather is expected to stay sunny for the next few days. Steps. The user input is provided to the CPA. The CPA is a language model that can understand and generate human-like text. It acts as an intermediary between the user and the agent. The CPA evaluates the user input and agent response to identify potential issues. This includes analyzing the user's intent, the agent's response, and comparing them to identify any inconsistencies or missed opportunities. Based on the identified issues, the CPA generates an intervention message. This intervention is meant to guide the agent in providing a better response to the user. Prerequisites. A conversational prompt assistant CPA is a language model capable of understanding and responding to natural language prompts. It is crucial for the intervention chain as it is responsible for evaluating user input and agent response to provide insightful intervention. An agent is a system or application that can understand and respond to user requests. In the context of intervention chain, the agent is responsible for providing an initial response to the user's input. Fine-tune parameters. The CPA model is a specific language model used by the CPA. Fine-tuning this model involves training it on a dataset of relevant data to improve its performance. In the context of user-agent interactions. Challenges and fixes. Challenge 1. The CPA might provide inappropriate or unhelpful interventions. This could be due to the CPA not understanding the context of the interaction, or its training data not covering the specific scenarios encountered. Fixes to challenge 1. Fine-tune the CPA model with relevant data to improve intervention quality. This involves training the CPA on a dataset of user-agent interactions with annotated examples of successful interventions. This will help the CPA learn to identify and address common issues in user-agent interactions. Challenge 2. The CPA might not understand user intent or agent response correctly. This could be due to the CPA not being able to identify the user's underlying goal or the agent's response not being clear enough. Fixes to challenge 2. Use a more sophisticated CPA model with better language understanding capabilities. This involves choosing a CPA model that has been trained on a larger dataset of text and code, and has been specifically designed to handle complex language tasks like intent recognition and response evaluation. Challenge 3. The CPA might generate interventions that are too long or complex. This could be due to the CPA not being trained to generate concise and understandable messages. Fixes to challenge 3. Train the CPA to generate concise and understandable interventions. This involves fine-tuning the CPA on a dataset of user-agent interactions with annotated examples of concise and helpful interventions. This will help the CPA learn to generate interventions that are easy to understand and actionable for the agent. Langchain-experimental CPAL-based query chain is an experimental query chain built using the CPAL framework, which enables effective query chain construction for various tasks. Description of Langchain-experimental CPAL-based query chain. A query chain leveraging the CPAL framework, designed for building complex and efficient query chains. Inputs of Langchain-experimental CPAL-based query chain. The user's question or task. For example, what is the capital of France? Background information for the query. Example: France is a country in Western Europe. Outputs of Langchain-experimental CPAL-based query chain. The generated answer to the query. Example: Paris. Steps of Langchain-experimental CPAL-based query chain. Prepare and standardize the user's input query. This may involve cleaning the input, identifying the core intent, and converting it into a form suitable for the subsequent steps. Access relevant information for the query. This might involve retrieving data from a knowledge base, searching a document database, or extracting information from a relevant web page. Produce the final answer based on the processed query and retrieved context. This could involve combining information, summarizing key points, and generating a coherent response. Prerequisites of Langchain-experimental CPAL-based query chain. The framework allows for modular Scalable and composable construction of query chains. CPAL facilitates managing intricate query chains efficiently. The framework provides building blocks and methods for assembling different components together, enabling developers to build tailored solutions for specific tasks. This modularity allows for easy modification and extension of query chains, making them adaptable to different use cases. The scalability of the framework allows for handling complex queries with large amounts of data and diverse sources, and the composability ensures that different modules can be combined in different ways, allowing for flexibility and customization. Enables accessing and interacting with diverse language models. Provides tools for text generation, summarization, and more. LangChain acts as a bridge between various language models and other components, allowing for seamless integration and utilization of these models within the query chain. LangChain simplifies the process of working with different models, offering functionalities for tasks such as text generation, summarization, translation, and question answering, making it a valuable tool for building sophisticated query chains. Fine-tune parameters of LangChain experimental CPAL-based query chain. Choose the language model best suited for the task. Different language models excel at different tasks. For example, a factual language model might be more suitable for question answering tasks, while a creative language model might be better for generating stories. Tailor the chain's internal components and configurations for optimal performance. This could involve adjusting the parameters of the language model, modifying the data sources used for retrieval, or optimizing the processing steps within the chain. Challenges and fixes of LangChain experimental CPAL-based query chain. Dealing with complex or ambiguous queries. For example, a query like "What's the weather like?" might require additional information to provide a meaningful answer. Implement robust query understanding and processing techniques. This might involve utilizing natural language processing (NLP) techniques to analyze the user's intent, identify key entities, and resolve ambiguities, ensuring context accuracy and relevance. The retrieved context should be directly related to the query and accurate. Employ advanced retrieval techniques and context augmentation strategies. This might involve using techniques like semantic search to retrieve the most relevant information from a large dataset, or enriching the context with additional information from external sources. LangChain experimental comprehend moderation prompt safety. Comprehend prompt safety. A LangChain tool that uses Amazon Comprehend to assess the safety of a given text prompt. It identifies potentially harmful content, including hate speech, profanity, and sexual content. Amazon Comprehend is a natural language processing service that uses machine learning to understand the meaning of text. It can identify various types of information in text, including the sentiment, language, and entities present in the text. Inputs. The text prompt to be analyzed. The text prompt that is to be analyzed by the Comprehend prompt safety tool. The input is the text that needs to be analyzed for safety. Outputs. List of identified safety labels. A list of labels that are identified by the Amazon Comprehend service as potentially harmful. For example, the labels might include hate speech, profanity, or sexual content. These labels indicate the type of potentially harmful content that was detected in the text prompt. List of confidence scores associated with each label. A list of confidence scores that are associated with each label. These confidence scores represent the likelihood that the content is flagged as unsafe. The higher the confidence score, the more likely it is that the content is flagged as unsafe. Steps. The prompt is sent to Amazon Comprehend for analysis. The text prompt is sent to Amazon Comprehend service for analysis. The Comprehend service then analyzes the text prompt to identify potentially harmful content. Comprehend identifies potential safety issues and assigns labels with associated confidence scores. Amazon Comprehend analyzes the text prompt and identifies potential safety issues. It then assigns labels to the content based on the detected issues. The labels are accompanied by confidence scores that indicate the likelihood of the content being flagged as unsafe. Prerequisites: AWS credentials, access keys and secret keys. For AWS, the Comprehend prompt safety tool requires access to the Amazon Web Services AWS platform. This access is granted through AWS credentials, which are access keys and secret keys that are used to authenticate requests to AWS services. These credentials are required to interact with the Comprehend service, which is a part of the AWS platform. Challenges and fixes. Challenge 1: The prompt contains sensitive information that should not be analyzed by Comprehend. This challenge arises when the text prompt contains sensitive information that should not be analyzed by Comprehend. For example, the text prompt might contain personal information, such as names, addresses, or financial data. This information should not be shared with Comprehend as it may violate privacy policies or security protocols. Fixes to challenge 1: Utilize a privacy-preserving technique like differential privacy or homomorphic encryption to anonymize the sensitive data. This challenge can be addressed by using privacy-preserving techniques such as differential privacy or homomorphic encryption. Differential privacy involves adding random noise to the data, while homomorphic encryption allows computations to be performed on encrypted data without decrypting it. Both techniques can be used to anonymize sensitive information in the text prompt before it is sent to Comprehend for analysis. This ensures that the sensitive information is not exposed and that the analysis is conducted in a privacy-preserving manner. Challenge 2: Comprehend fails to identify certain types of harmful content. This challenge arises when Comprehend fails to identify certain types of harmful content. This could be due to the limitations of the Comprehend model or the specific context of the text prompt. For example, Comprehend might not be able to identify subtle forms of hate speech or specific types of profanity that are not commonly used. Fixes to challenge 2: Fine-tune the model with additional examples specific to the desired context. This challenge can be addressed by fine-tuning the Comprehend model with additional examples specific to the desired context. This involves providing the model with more data related to the specific types of harmful content that need to be identified. By training the model on this additional data, it can improve its ability to detect these types of content. This fine-tuning process can enhance the model's accuracy and effectiveness in identifying harmful content in the specific context of the text prompt. Entity Setting Model Summary. Entity Setting Model helps to create embeddings from specific entities, like a product from a specific vendor. It is used to enhance the retrieval process in a knowledge base. For instance, if you have a knowledge base of products, you can use Entity Setting Model to create embeddings for each product. These embeddings can then be used to find similar products or to retrieve information about a specific product. Inputs. Text input that contains the entity information. For example, the input text could be the name of a product, the description of a product, or a review of a product. The entity type. Defining the category of the entity. For example, the entity type could be product, vendor, or review. Outputs. Entity embedding representing the input text. This embedding is a numerical representation of the input text. It can be used to find similar entities or to retrieve information about a specific entity. Steps. 1. The input text undergoes preprocessing for cleaning and formatting. This step removes any unnecessary characters or formatting from the input text, such as punctuation or capitalization. 2. The processed text is then converted into an embedding using the chosen embedding model. This step uses a pre-trained model to convert the processed text into a numerical representation. Prerequisites. An embedding model that suits the entity type. For example, you could use a sentence transformers model for text data or a pre-trained model like OpenAI's TextEmbeddingAda 002. For example, sentence transformers. OpenAI's TextEmbeddingAda 002. etc. These models have been trained on a large corpus of text data and can be used to generate embeddings for new text data. A knowledge base containing information about the entities. This knowledge base could be a database, a file, or a web service. The knowledge base should contain information about the entities that you want to embed. Fine-tune parameters. Fine-tuning parameters for the embedding model. Fine-tuning parameters can be used to adjust the embedding model to better suit the specific task. For example, you could fine-tune the embedding model to generate embeddings that are more relevant to a specific domain or to improve the accuracy of the embeddings. Challenges and fixes. Entity identification difficulties. It can be challenging to accurately identify the entities in the input text. For example, a product name might be spelled differently in different sources, or it might be part of a longer phrase. Preprocessing techniques to improve entity identification accuracy. There are a number of preprocessing techniques that can be used to improve entity identification accuracy. These techniques include using regular expressions to identify patterns in the text, using dictionaries to map words to their canonical forms, and using named entity recognition tools to identify named entities. Embedding model selection challenges. Choosing the right embedding model for the task can be challenging. The choice of embedding model will depend on the specific task and the type of data being embedded. Experimenting with different models to choose the best fit. It is important to experiment with different embedding models to find the best fit for the specific task. You can compare the performance of different models by evaluating the embeddings that they generate. Summary of LangChain experimental CPAL-based CPAL chain. The CPAL chain is a chain of thought code-based code generation tool. Inputs. This chain accepts an input prompt describing a task. For example, the prompt could be a simple instruction like write a function to calculate the factorial of a number, or a more complex task description like write a Python script that retrieves data from a given URL, processes the data, and stores it in a database. Outputs. The output of the chain is the generated code for the task. Steps. 1. The input prompt is processed and understood by the model. 2. The model generates a chain of thought which represents a logical reasoning for the task. 3. The chain of thought is converted into code in the desired programming language. 4. The generated code is output as the result. Prerequisites. A CPAL model is required to run this chain. This model could be either the coded DaVinci 002 or the text DaVinci 003 model from OpenAI. Fine-tune parameters. Temperature parameter controls the randomness of the generated code. Higher temperature values lead to more creative and unexpected outputs. Top P parameter controls the diversity of the generated code by selecting a subset of the most Probable words. Top K parameter controls the number of possible code snippets to be considered during code generation. Challenges and fixes. Challenge 1: if the task description in the prompt is unclear or ambiguous, the model might generate incorrect code. Fixes to challenge 1: ensure that the prompt is written in a clear and concise way, specifying the task in detail. Challenge 2: the generated code might contain errors or not work as expected. Fixes to challenge 2: always review and refine the generated code to identify and fix potential errors. Challenge 3: the model might not have enough context or information to generate the desired code. Fixes to challenge 3: provide the model with additional context and information related to the task. For example, you can include relevant code snippets, documentation, or data examples. Langchain Experimental CPAL Models Entity Model Summary. Entity model is a langchain model that represents a specific entity, such as a person, place, or thing. For example, an entity could be a specific individual like Albert Einstein, a geographical location like Paris, or a concept like quantum mechanics. Inputs. Entity data such as name, description, and related entities. Entity data can come from various sources, like structured databases containing information about people, places, and things, or unstructured text corpora like news articles and social media posts. Outputs. Entity representations in different formats, such as text, embeddings, or knowledge graphs. Entity representations can be used for various tasks, like question answering, information retrieval, and recommendation systems. For example, an entity model representing Albert Einstein could be outputted as a text summary of his life and work, an embedding that captures his scientific contributions, or a knowledge graph connecting him to other entities like relativity and physics. Steps. 1. Extract and store relevant information about the entity. This step involves identifying key attributes of the entity, such as its name, description, and relationships with other entities. For example, extracting information from a database entry about Albert Einstein might include his birth date, nationality, and key scientific discoveries. 2. Generate an embedding for the entity. Embeddings are numerical representations of entities that capture their semantic meaning. This allows for comparisons and analysis of entities within a vector space. Generating an embedding for Albert Einstein could involve processing his relevant text data through a language model, resulting in a vector that represents his scientific contributions, theories, and historical context. 3. Connect the entity to a knowledge graph. If available, knowledge graphs are structured representations of entities and their relationships. Connecting an entity to a knowledge graph allows for exploring and understanding its connections to other entities. For example, connecting Albert Einstein to a knowledge graph could reveal his relationships with other physicists, his theories, and the institutions he was affiliated with. 4. Provide access to the entity data through application programming interfaces, APIs, and other interfaces. This step allows for programmatic access to the entity data and its representations. For example, an API could allow developers to retrieve the text summary of Albert Einstein, his embedding vector, or the related entities connected to him in the knowledge graph. Prerequisites. Entity data source. Entity data can be obtained from various sources, such as structured databases containing information about people, places, and things, or unstructured text corpora like news articles and social media posts. Database. Application Programming Interface API, or text corpus. For example, a database might store information about individuals. A web service might provide information about locations. And a collection of documents might contain information about specific events or concepts. Embedding model. Embedding models are used to generate numerical representations of entities that capture their semantic meaning. This allows for comparisons and analysis of entities within a vector space. OpenAI's Ada, Babbage, Curie, or Da Vinci. These are examples of powerful language models offered by OpenAI that can be used to generate embeddings for entities based on their text descriptions. Fine-tune parameters. Entity embedding dimensions. The number of dimensions in the embedding vector affects the complexity of the representation and the computational resources required. Higher dimensions allow for more detailed representations but can be more computationally expensive. Knowledge graph connection parameters. These parameters define how the entity is connected to the knowledge graph. Factors like the type of relationship and the strength of the connection can be adjusted to fine-tune the model. Challenges and fixes. Entity data inconsistency. Different data sources may contain conflicting or incomplete information about the same entity. Use data cleaning and normalization techniques. This involves identifying and correcting errors in the data, such as inconsistent spellings or conflicting information. Techniques like data standardization and data deduplication can be applied to ensure data consistency and accuracy. Entity ambiguity. Entities can have multiple meanings or interpretations, leading to confusion. Implement disambiguation techniques using context and relationships. This involves using contextual information and relationships with other entities to determine the correct meaning of an ambiguous entity. For example, the entity apple could refer to the fruit or the technology company. Analyzing the surrounding text or the relationships in a knowledge graph can help determine the intended meaning. Entity evolution. Entities change over time, and their associated information needs to be updated to reflect these changes. Develop mechanisms for updating entity data and representations over time. This involves implementing mechanisms to monitor and update entity data and representations as new information becomes available. For example, an entity model representing Albert Einstein may need to be updated with new discoveries about his life and work, or with updated information about his contributions to physics. Langchain experimental CPAL models query model. This YAML structure defines the query model used for the conversational personal assistant for language CPAL. This model is responsible for processing user input, understanding context, and generating appropriate responses. Inputs. The raw text input provided by the user, such as a question or a command. For example, what is the capital of France? Or set a reminder for tomorrow at 10 a.m. Relevant contextual information that aids in understanding the user's request. This could include previous conversation turns, the user's profile, or any other relevant data. Outputs. The assistant's generated response based on the input and context. This can be a direct answer, a follow-up question, or any other relevant information. Steps. The model first receives the user input. The model processes the input using a powerful language model, such as GPT 3.5 or GPT-4. This involves understanding the language, intent, and context of the user's request. The model generates a response based on the processed input and the provided context. Prerequisites. A powerful language model is necessary for understanding the input and generating responses. Popular choices include OpenAI's GPT 3.5 and GPT-4. These models have been trained on massive datasets of text and code, giving them the ability to comprehend complex language and generate human-like text. Contextual information is crucial for the model to understand the user's request accurately. This can include previous conversation turns, providing valuable insight into the user's goals and interests. Additionally, user profile information like location, preferences, and past interactions can help tailor the response. Fine-tune parameters. The temperature parameter controls the randomness of the model's responses. Higher values lead to more diverse and creative outputs, while lower values result in more predictable and deterministic responses. Top P is a sampling technique that controls the diversity of the model's output. It limits the probability distribution of the next token to a certain percentile. This helps to avoid generating nonsensical or improbable responses. Challenges and fixes. Ambiguous queries can pose a challenge for the model, as it may be unclear what the user intends. Context can be used to resolve ambiguity by providing additional information that helps the model understand the user's true meaning. For example, if the user asks what is the capital, the context might be a previous conversation about France, indicating that the user is asking about the capital of France. The model can sometimes generate irrelevant responses, especially if the training data is not comprehensive enough. Improving the training data by adding more relevant examples in diverse scenarios can help a model learn to generate more accurate and relevant responses. Providing incorrect information can be detrimental to the user's trust in the assistant. To ensure accuracy, the model can be integrated with external sources of information, such as knowledge bases or APIs. This allows the model to verify the information it generates and provide more reliable answers. Narrative Model for Langchain Experimental CPAL. NAN. This narrative model utilizes LangChain and CPAL to generate engaging narratives from various data sources. Input data in various formats including textual, tabular, or structured formats. Examples of input data include a list of historical events, text from a news article, data from a spreadsheet, narrative-related instructions, providing guidance on the desired narrative style, tone, or specific elements. Examples of instructions include: write a story in the style of a detective novel, describe the characters in detail, focus on the historical significance of the events. A coherent narrative incorporating information from the input data and adhering to the provided instructions. Potential supplementary outputs such as detailed character profiles, descriptive settings, or plot outlines, based on the specific use case. Ingesting and processing the input data. Analyzing the structure of the data to identify key elements, relationships, and the overall narrative flow. Generating the story using language models. Adhering to the input instructions and incorporating insights from the data analysis. Formatting and refining the output, potentially involving multiple iterations and revisions. LangChain's capabilities for data retrieval, processing, and integration. This includes example values for prerequisite 1. Retrieving data from application programming interfaces APIs, such as weather data or financial information. Summarizing large amounts of text. Extracting key points and information. Extracting relevant data from unstructured text, such as news articles or social media posts. CPAL's framework for narrative generation and manipulation. This includes example values for prerequisite 2. Storytelling templates, providing a structured framework for building different types of narratives. generating characters and settings with specific characteristics and attributes, developing plot structures and outlining the sequence of events in the story. Specific language models used for narrative generation, potentially including fine-tuned models for particular genres or styles, such as models trained on historical fiction or fantasy writing. Weights for different narrative elements, such as character development, plot complexity, or descriptive detail, allowing the model to prioritize specific aspects of the story. Narrative flow control parameters, adjusting the pacing, focus, and level of detail in the generated story, allowing for variations in storytelling style and engagement. Maintaining factual accuracy while crafting a compelling narrative, as there is always the potential for inconsistencies or inaccuracies in the generated story. Fixes to challenge 1. Fact-checking mechanisms integrated into the model. Verifying information against reliable data sources. Using data sources known for their high reliability and accuracy. Ensuring coherence and consistency in the generated narrative. Preventing jumps in logic or inconsistencies in the storyline. Fixes to challenge 2. Narrative structure analysis and refinement. Ensuring a smooth flow and logical progression of events. Using language models with strong coherence and consistency capabilities. Minimizing the likelihood of illogical jumps or contradictions in the story. Langchain-experimental CPAL models. Result model summary. None. The user's input serves as the starting point for any interaction with a conversational agent. This could be a question, a command, or even just a casual remark. An agent's internal state represents its memory and understanding of the ongoing conversation. It includes information about past interactions, collected knowledge, and any relevant context. An agent's response is the output generated based on the user's input and the agent's internal state. This response might be an answer to a question, a suggestion, a piece of information, or a simple acknowledgement. An updated agent's internal state reflects the changes made to the agent's memory and understanding. After processing the user's input and generating a response, this includes incorporating new knowledge, adjusting context, or modifying the internal representation of the conversation. Receiving user input involves capturing the text or voice input provided by the user and preparing it for processing by the agent. Processing input and generating a response involves analyzing the user's input, understanding its meaning, and using the agent's internal state to generate a relevant and coherent response. This step often involves using a language model to understand the input and generate the output. Updating the internal state involves updating the agent's memory and understanding of a conversation based on the processing of the user's input. This might include adding new information to the internal database, adjusting the context, or modifying the internal representation of the ongoing conversation. A language model is essential for a conversational agent to understand the meaning of user input and generate appropriate responses. These models can be based on deep learning architectures like transformers and are trained on massive text datasets. Examples of widely used language models include GPT-3 and Llama, which are both capable of understanding natural language and generating coherent text. Agent memory is a key component of conversational agents, allowing them to remember past interactions and maintain context throughout the conversation. A vector database is a specialized type of database that stores data in the form of vectors, making it suitable for storing and retrieving information related to natural language. This allows the agent to efficiently access and retrieve relevant information from previous interactions, enhancing the conversation flow and providing a more personalized experience. Prompt engineering involves carefully crafting the prompts or questions given to the language model to elicit the desired responses. This involves designing prompts that are clear, concise, and provide sufficient context for the language model to understand the user's request and generate an appropriate response. A reward function is used to guide the training process of a conversational agent by providing feedback on the quality of its responses. This function assigns numerical values to different responses, with higher values indicating better responses. By maximizing the reward function, the agent learns to generate responses that are more informative, relevant, and engaging. Bias and fairness are significant challenges in conversational agents, as they can perpetuate existing societal biases embedded in the training data. Addressing this requires using diverse datasets that represent a wide range of perspectives, employing bias mitigation techniques to minimize the impact of biases in the training data, and regularly evaluating the agent for potential biases. Safety and reliability are crucial considerations for conversational agents, as they can have a significant impact on user experience. Implementing safety mechanisms, such as filtering inappropriate content, verifying the accuracy of information, and preventing harmful actions, is essential. Additionally, validating responses generated by the agent to ensure they are consistent with the expected behavior and adhere to ethical guidelines is crucial for maintaining reliability and ensuring a positive user experience. Langchain-experimental (CPAL) models. Result model summary. NaN. Langchain-experimental CPAL model result summary. The name of the CPAL model used in the run. This is a descriptive name that identifies the specific model being used, such as sentiment analysis model or text summarization model. The version of the CPAL model used in the run. This indicates the specific iteration or release of the model, allowing for tracking of changes and improvements over time. For instance, version 1.0 might have different parameters or training data than version 2.0. The output generated by the CPAL model. This could be text, a numerical score, a classification label, or any other format relevant to the model's purpose. The format of the output generated by the CPAL model. This provides clarity on how the output is structured and what type of data it represents. Common formats include JSON, CSV, plain text, or a custom format specific to the model. Initialize the CPAL model. Load and prepare the CPAL model for use, including loading its parameters and any necessary resources like vocabulary or weights. Load input data. Retrieve and format the input data to be processed by the CPAL model. This involves ensuring that the data is in the expected format, such as a list of sentences, a text file, or a structured dataset. Execute the CPAL model. Run the CPAL model on the prepared input data. This involves applying the model's internal logic and algorithms to process the data and generate an output. Collect outputs. Gather the output generated by the CPAL model and store it for further processing or analysis. This could involve storing the output in a variable, writing it to a file, or sending it to a specific location for later retrieval. Process the outputs. Post-process the output generated by the CPAL model, such as formatting, cleaning, or interpreting the results. This might involve converting raw model output into a more readable or usable form. CPAL model. A pre-trained CPAL model that is ready to be used for the task at hand. This might involve using a publicly available model or a model trained specifically for the task. The specific name of the CPAL model used in the run. This is a descriptive name that identifies the specific model being used, such as sentiment analysis model or text summarization model. The version of the CPAL model used in the run. This indicates the specific iteration or release of the model, allowing for tracking of changes and improvements over time. For instance, version 1.0 might have different parameters or training data than version 2.0. Input data. The data that the CPAL model will process and generate an output from. This could include text, images, audio, or any other type of data relevant to the model's purpose. The format of the input data, such as text files, JSON objects, or CSV files. The format should match the expected input format for the specific CPAL model being used. Learning rate. This parameter controls how quickly the model adjusts its internal weights during training. A higher learning rate might lead to faster training but potentially overfitting to the training. Data. Batch size. This parameter determines the number of data samples processed in each iteration during training. A larger batch size can speed up training but might require more memory. Number of epochs. This parameter determines how many times the model goes through the entire training dataset during training. More epochs generally lead to better model performance but can also increase training time. Model convergence issues. This refers to the situation where the model's training process does not reach a stable and optimal state. Adjust learning rate. If the learning rate is too high, it can cause the model to jump around the solution space and fail to converge. Decreasing the learning rate can help the model converge more smoothly. Increase epochs. If the model is not converging, increasing the number of epochs can allow the model to continue learning and potentially reach a better solution. Memory constraints. This arises when the training process requires more memory than available, leading to slow performance or even crashing. Reduce batch size. Reducing the batch size lowers the amount of data processed in each training iteration. Reducing memory demands. Use gradient accumulation. This technique allows the model to accumulate gradients over multiple mini batches, effectively simulating a larger batch size without increasing memory usage. Input data quality. The quality of the input data significantly impacts the model's performance. Issues like noisy data, inconsistencies, or missing information can affect the training process and the model's output. Clean and pre-processed data. This involves removing errors, inconsistencies, and irrelevant information from the input data. This step ensures that the model is trained on high-quality data, improving its accuracy and generalizability. Output interpretation. Understanding the meaning and implications of the output generated by the CPAL model can be a challenging task, especially for complex models. Post-process model outputs. This step involves analyzing, formatting, and potentially transforming the model's output into a more meaningful or usable form. It might involve converting raw numerical outputs into human-readable labels, applying thresholds to classify predictions, or using domain knowledge to interpret the results. Langchain experimental data anonymizer summarization. Description of the langchain data anonymizer, a tool designed to protect sensitive data within langchain applications. It focuses on protecting user data and confidential information during data processing. Inputs. Input data, the data that needs to be anonymized. This could be a document, a dataset, or any collection of information containing sensitive data. Examples: a customer database containing names, addresses, and phone numbers, or a medical record containing patient information. Anonymization configuration: a set of instructions specifying the techniques to use for anonymization and the level of anonymity required. This includes types of information to anonymize, for example, names, addresses, financial details, medical records, etc. Desired level of anonymity: techniques like pseudonymization, generalization, or complete removal of sensitive data. Outputs: anonymized output, the result of the anonymization process. This is a version of the input data where sensitive information is either masked, replaced with appropriate substitutes, or removed entirely, depending on the configuration. Examples: replacing names with random identifiers, blurring addresses, or completely removing specific fields from a dataset. Steps. Step 1: Data ingestion. The initial step involves loading the data that needs to be anonymized. This data can come from various sources like files, text files, CSV files, databases, or application programming interfaces (APIs). Step 2: Data analysis. The next step is to analyze the data and identify sensitive information that needs to be anonymized. This involves recognizing personal details, names, addresses, phone numbers, financial data, account numbers, transaction details, or medical records, patient names, diagnoses, treatments. Step 3: Anonymization based on the provided configuration. The anonymizer applies chosen techniques to protect the sensitive data. These techniques include pseudonymization, replacing real names or identifiers with artificial ones; generalization, making specific data more general by aggregating or grouping it; removal, deleting sensitive information entirely from the data. Step 4: Output generation. The final step involves generating the anonymized output. This can be in various formats depending on the original input and desired outcome. Examples: a text file, a database table, a CSV file, or an API response containing the anonymized data. Prerequisites: data preparation before processing. The input data should be in a suitable format. This could be a text file, a CSV file, a database table, or any other format that can be easily processed by the anonymizer. Fine-tune parameters. Anonymization techniques. These parameters allow fine-tuning of the anonymization process. The user can specify the techniques to be applied. Examples: pseudonymization, generalization, removal, or a combination of these. Data sensitivity levels. The user can define the desired level of anonymity for different types of sensitive data. This allows for a more granular approach to anonymization. For example, names might require pseudonymization, while addresses might be generalized, and some other information might be removed completely. Challenges and fixes. Challenge 1. Data integrity. Maintaining the integrity of the data while anonymizing it is crucial. The anonymization process should not introduce errors or inconsistencies into the data. Fixes to challenge 1. Fixes for data integrity. Data quality checks. Thorough checks need to be performed to ensure that the anonymization process does not introduce errors or inconsistencies into the data. Verification strategies. Methods should be implemented to verify that the anonymized data is still useful and valid for its intended purpose. Challenge 2. Privacy compliance. The anonymization process should strictly adhere to relevant privacy laws and regulations. This ensures that the anonymized data is handled ethically and legally. Fixes to challenge 2. Fixes for privacy compliance. Legal expertise. Consulting legal experts familiar with privacy Regulations is crucial to ensure compliance with data protection laws. Privacy-preserving techniques utilizing advanced anonymization techniques that are compliant with privacy standards is essential. Challenge 3. Scalability. Handling large datasets and ensuring efficient anonymization performance is a challenge. The anonymizer should be able to process large volumes of data efficiently. Fixes to Challenge 3. Fixes for scalability. Parallel processing. Utilizing parallel processing techniques can significantly speed up the anonymization process for large datasets. Optimized algorithms. Employing optimized algorithms for data processing can improve efficiency and reduce processing time. Challenge 4. Data accessibility. Balancing privacy concerns with the need for access to anonymized data for research or analysis is a delicate balance. Fixes to Challenge 4. Fixes for data accessibility. Access control. Robust access control mechanisms should be implemented to restrict access to anonymized data only to authorized users. Data usage agreements. Clear data usage agreements should be established to ensure that anonymized data is used only for its intended purpose. Langchain Data Anonymizer Summary. This tool, Langchain Experimental Data Anonymizer, is designed to process text containing sensitive information and replace it with anonymized tokens. The goal is to maintain the structure and semantic meaning of the original text while ensuring that sensitive data is obscured. This tool is especially useful in scenarios where you need to share or analyze text while protecting private or confidential information. Inputs. Text containing sensitive information. For instance, a text document might contain personal information such as names, addresses, phone numbers, or financial details. This input text is the source material for the anonymization process. Outputs. Anonymized text. The output is the original text with sensitive information replaced by anonymized tokens. These tokens could be random characters, hashes, or other representations that maintain the structure of the text but do not reveal the original sensitive data. Steps. Identify and extract sensitive information. The tool first needs to identify the sensitive data present in the input text. This step might involve pattern recognition, regular expressions, or other techniques to locate specific data types like names, dates, or financial information. Replace sensitive information with anonymized tokens. Once the sensitive information is identified, it is replaced with anonymized tokens. These tokens are chosen to be distinct from the original data and ideally maintain the structural integrity of the text. Maintain the original structure and semantic meaning of the text. The anonymization process aims to preserve the original text structure and semantic meaning. This is important to maintain readability and to prevent any distortion of the information. For example, if a name is anonymized, the surrounding context should still make sense, and the overall meaning of the text should remain intact. Prerequisites. Python 3.7 or higher. This tool is developed using Python and requires a specific version of the language for proper execution. Langchain library installed. Langchain is a library that provides tools for building and deploying language models. This tool requires the Langchain library to be installed for its functionality. Fine-tune parameters. Anonymization strategy, e.g., hashing, tokenization, masking. There are various techniques for anonymizing data. The chosen strategy will determine the method of replacing sensitive information with anonymized tokens. Hashing involves converting data into fixed-size strings using cryptographic algorithms, while tokenization uses unique identifiers to represent data. Masking involves concealing parts of the data. For example, by replacing digits with asterisks. Specific sensitive information to anonymize. The tool can be configured to specifically anonymize certain types of data. This might include names, addresses, phone numbers, credit card numbers, or other sensitive information that needs to be protected. Challenges and fixes. Preserving the context and meaning of the text. One challenge is ensuring that the anonymized text maintains the context and meaning of the original. If the anonymization process is not carefully implemented, the resulting text might become nonsensical or lose its intended meaning. Using appropriate anonymization strategies and techniques. Choosing the right anonymization strategy is crucial to preserving context and meaning. Strategies like tokenization or hashing that maintain the length and structure of the data can be more effective in this regard. Maintaining the structure and formatting of the text. The tool needs to maintain the structure and formatting of the text to ensure readability and avoid introducing any errors. For example, if a name is anonymized, the surrounding text should still be grammatically correct and the original format of the text should be preserved. Leveraging pre-trained language models and techniques for text reconstruction. Pre-trained language models, which are trained on massive text datasets, can be used to assist in text reconstruction after anonymization. These models can help maintain the grammatical structure and coherence of the text. Langchain-experimental data anonymizer base reversible anonymizer base summary. This class serves as the foundation for creating reversible anonymizers, which are designed to transform data into an anonymized form while retaining the capability to reverse the anonymization process and retrieve the original data. Inputs. The data that needs to be anonymized. This could be any kind of data, such as text, numbers, or images, that needs to be protected while still being usable for analysis or other purposes. Outputs. The anonymized version of the original data. This data will be transformed into a form that makes it difficult to identify individuals or sensitive information, while still preserving the overall structure and meaning of the data. A mapping that links the original data to its anonymized counterpart. This mapping is crucial for reversibility, allowing the anonymized data to be restored to its original form. Steps. 1. The process begins by generating anonymized data. This involves applying anonymization techniques to the input data, replacing sensitive information with substitutes that maintain the data's structural integrity while concealing identifying details. 2. A mapping is created that meticulously records the relationship between the original data and generated anonymized data. This mapping acts as a key to unlock the original data from its anonymized form. Prerequisites. A function designed to generate anonymized data is necessary. This function will handle the transformation of the input data into its anonymized representation. A function is required to store the mapping between the original data and its anonymized counterpart. This function ensures that the mapping is securely maintained, allowing for the reversal of the anonymization process when needed. Fine-tune parameters. There are no specific fine-tuning parameters required for this base class. Challenges and fixes. Challenge 1. Maintaining data integrity. A key challenge in anonymization is preserving the data's structural integrity and meaning. If anonymization significantly distorts the data, it might render it useless for analysis or other applications. Fixes to challenge 1. Reversible anonymization techniques are essential to address this challenge. These techniques ensure that the anonymized data can be transformed back into its original form, guaranteeing data integrity and preserving the data's usability. Challenge 2: Ensuring data privacy. Protecting sensitive information is paramount when anonymizing data. Anonymization methods must be robust enough to prevent unauthorized access or disclosure of personally identifiable information. Fixes to Challenge 2: Employing strong encryption techniques and implementing rigorous access control mechanisms are crucial for safeguarding data privacy. Encryption secures the anonymized data, making it unintelligible to unauthorized parties. Access control ensures that only authorized individuals can access and manipulate the anonymized data, further mitigating privacy risks. Langchainexperimental data anonymizer base, reversible anonymizer base summarization. This class represents a foundational structure for reversible anonymizers. Reversible anonymizers play a crucial role in data privacy by masking sensitive information while retaining the ability to restore the original data. This class lays the groundwork for anonymizing data while preserving the capability to retrieve the original values. Inputs. The input to the anonymizer is raw data that requires anonymization. This data could be in various formats, such as text, numbers, or structured datasets. For instance, a list of customer names and addresses would be an example of data requiring anonymization. Outputs. The output of the anonymizer is the anonymized data. This data is a transformed version of the input data, where sensitive information has been masked or replaced with non-sensitive values. The anonymized data maintains the structure and overall meaning of the original data but obscures sensitive details. For example, customer names might be replaced with random identifiers, and addresses might be generalized to city-level information. Steps. The anonymization process involves an abstract method that defines how the input data is transformed into anonymized data. This method could involve techniques such as data masking, tokenization, or pseudonymization. For instance, the method could replace names with random strings, dates with generic dates, or addresses with city-level locations. The reversibility aspect of this class is achieved through an abstract method that reverses the anonymization process, restoring the original data from the anonymized data. This method would use the inverse of the anonymization method to retrieve the original values. For example, it could use a mapping table to replace random identifiers with original names, dates with specific dates, or city-level locations with original addresses. Prerequisites. The input data must be in a format that allows anonymization. This could involve ensuring that the data is structured in a way that permits mapping and unmasking. For instance, if anonymizing names, the data should include fields for names. If anonymizing dates, the data should include fields for dates. Fine-tune parameters. There are no fine-tune parameters for this base class. This class provides a basic framework for reversible anonymizers, and any specific parameters would be defined in subclasses that implement the anonymization and reversibility methods. Challenges and fixes. The ability to perfectly reverse anonymization is not always guaranteed. This can happen due to factors such as data loss during anonymization or the use of irreversible transformations. To address this challenge, robust reversibility checks should be implemented to ensure that the original data can be reliably recovered. These checks could involve comparing the restored data with the original data and reporting any discrepancies. During the anonymization process, some data might be lost, resulting in an incomplete or inaccurate representation of the original data. This can occur due to data masking or data generalization techniques. To address this challenge, Data preservation techniques should be implemented to minimize data loss. These techniques could involve storing additional information alongside the anonymized data or using reversible data transformations that preserve more information. Langchain-experimental, data anonymizer, base, reversible anonymizer base. Summary of langchain-experimental data anonymizer base. Reversible anonymizer base. Reversible anonymizer base class is the base class for reversible anonymizers. This class serves as the foundation for creating anonymizers that can both anonymize data and restore it to its original form. Inputs. The input to the anonymizer is the data that needs to be anonymized. This data can be in various formats, such as text, numerical data, or structured data like JSON or CSV. For example, a list of customer names, addresses, and phone numbers. This is an optional dictionary that allows customization of the anonymization process. This dictionary can contain parameters specific to the anonymizer implementation, such as the type of anonymization to perform or the level of anonymization desired. For example, specifying whether to use a deterministic or probabilistic approach to anonymization or controlling the level of obfuscation applied. Outputs. The anonymizer outputs the anonymized data. This data will have been transformed to protect sensitive information while preserving the overall structure and meaning of the original data. This output could be a modified list of customer names replaced with random aliases, obfuscated addresses, or hashed phone numbers. Steps. The first step is to initialize the anonymizer. This involves setting up the anonymizer with any configuration parameters and preparing for the anonymization process. This initialization might involve setting up internal data structures, loading anonymization dictionaries, or initializing random number generators. The second step involves applying the anonymization technique to the input data. This step transforms the original data into its anonymized form based on the chosen anonymization method and configuration. This could involve replacing sensitive values with random values, hashing or encrypting data, or applying other data transformation techniques. Prerequisites. The reversible anonymizer base class serves as the foundation for all reversible anonymizers. This means that all reversible anonymizers will inherit from this base class, inheriting its core functionalities and ensuring consistency in their implementation. For example, all reversible anonymizers will need to provide a way to reverse the anonymization process, allowing the original data to be recovered from its anonymized form. Fine-tune parameters. A configuration dictionary allows for customizing the anonymizer's behavior. This dictionary provides a way to specify options for the anonymization process, such as the level of anonymization desired, the specific anonymization techniques to use, or any other parameters specific to the anonymizer implementation. This dictionary allows for fine-tuning the anonymizer's operation, adapting it to the specific requirements of the data being anonymized and the desired level of privacy. For example, this dictionary might include settings for the strength of hashing, the types of obfuscation methods to apply, or the specific anonymization techniques to prioritize. Challenges and fixes. Implementing reversible anonymization presents a unique challenge. The anonymizer must not only transform the data to protect sensitive information but also provide a mechanism to recover the original data. This requires designing the anonymization process in a way that preserves sufficient information to allow for reverse mapping. For example, instead of simply replacing sensitive values with random strings, The anonymizer might use a reversible hashing algorithm or maintain a mapping between the original values and their anonymized counterparts. The solution is to provide a reverse mapping for the anonymized data. This mapping allows the original data to be recovered from its anonymized form by associating each anonymized value with its corresponding original value. For example, the anonymizer might maintain a dictionary where each anonymized value is linked to its original counterpart. This mapping can then be used to reverse the anonymization process and restore the original data. Handling different data types is another challenge in anonymization. Different data types require specific anonymization methods. For example, anonymizing text data might involve replacing names with random aliases, while anonymizing numerical data might involve replacing specific values with ranges or rounding. The anonymizer needs to be flexible enough to handle various data types effectively and provide appropriate anonymization methods for each type. The solution involves implementing type-specific anonymization methods. This approach involves tailoring the anonymization process to the specific data type being handled. This might involve using different techniques for different data types, such as using deterministic methods for numerical data and probabilistic methods for text data. By implementing type-specific anonymization methods, the anonymizer can handle diverse data types effectively and ensure that the anonymization process is appropriate for the data being processed. System setting model is a langchain model that defines a set of system settings for use with LLM chains. None. This model defines a set of system settings for use with language model chains. These settings control how the language model interacts with the user and processes the input. For example, they can define the allowed tone of voice, the maximum length of the response, and the constraints on the content. Inputs. This model expects a system settings dictionary as input. The dictionary should contain key-value pairs where keys represent the system setting names, and values represent their corresponding values. For example, the dictionary can include settings for the tone of voice, maximum length of response, and content constraints. Outputs. The output of the model is the same system settings dictionary applied to language model chains. This ensures that the language model will use the specified settings when interacting with the user. Steps. The first step involves defining system settings. This involves creating a dictionary that specifies the desired settings. This dictionary can include various settings, such as tone of voice, maximum length of response, and content constraints. The second step involves applying these defined system settings to the language model chain. This step integrates the specified settings into the language model's behavior, ensuring that it follows the defined rules and guidelines. Prerequisites. This model requires the LangChain library for its functionalities. The LangChain library is a powerful framework for building and deploying language model applications. It provides tools for interacting with language models, creating chains of processing steps, and managing data flow. It also needs an LLM chain, which is a series of steps that processes user input and generates a response using a language model. LLM chains are built using components like Chat LLM and Conversation Buffer Memory. Chat LLM is a language model interface that allows conversational interaction. Conversation Buffer Memory manages the context of the conversation, enabling the language model to understand the conversation flow and generate coherent responses. Fine-tune parameters. The system settings parameter is used for fine-tuning the model. This parameter allows you to adjust the settings that define the model's behavior, such as the tone of voice, response length, and content constraints. By tuning these settings, you can customize the model's output to meet your specific needs. Challenges and fixes. The system settings must be in a specific format for the model to function correctly. Ensure that the system settings are provided as a dictionary containing key-value pairs, where keys are setting names and values are their corresponding settings. For example, the dictionary could contain settings like tone of voice friendly, max length 500, content constraints no violence. If the system settings are not applied correctly, the language model will not use the specified settings, potentially leading to unexpected output. To ensure that the settings are applied correctly, use the system settings parameter when defining the language model chain. This parameter will pass the settings to the language model, allowing it to use them during processing. For example, when creating a LLM chain, you might include a parameter like system settings tone of voice friendly, max length 500, content constraints no violence. This ensures that the language model will generate responses in a friendly tone, with a maximum length of 500 characters, and without any violent content. Langchain Experimental Data Anonymizer Summary. A tool for anonymizing data within a LangChain application by using various methods to make it more privacy-friendly. This tool helps protect sensitive information by obscuring it while maintaining the usability of the data for analysis or other purposes. Inputs. The data that needs to be anonymized, which can be in various formats that LangChain can process, such as plain text, structured data like JSON or CSV, or even data from databases. For example, a text document containing personal information like names and addresses, or a database table with customer data, could be input into this tool. The chosen strategy for anonymizing the data. Different methods are available, such as masking sensitive information with characters like tokenizing values by replacing them with unique identifiers, or generalizing data by grouping values into broader categories. Outputs. The anonymized data will be returned in the same format as the input. For example, if the input was a text document, the output would be a text document with the sensitive information replaced by the anonymized values. Similarly, if the input was a database table, the output would be an anonymized version of that table. Steps. First, the tool identifies sensitive data within the input data. This involves analyzing the data and identifying fields or segments that contain potentially private information, such as names, addresses, phone numbers, or financial details. After identifying the sensitive data, the tool applies the chosen anonymization technique to the data. This could involve masking the data with special characters, replacing it with unique tokens, or generalizing it into broader categories, depending on the chosen strategy. Prerequisites. The LangChain library is a powerful tool for working with language models and data. It is crucial to have this library installed and configured properly to utilize the data. Anonymization tool. A fundamental understanding of data privacy and the various techniques used for anonymizing data is essential. This knowledge will enable you to choose the most appropriate anonymization methods based on the specific data and the intended use of the anonymized data. Fine-tune parameters. The choice of anonymization method is a critical parameter. This choice depends on the sensitivity of the data, the intended use of the anonymized data, and the trade-off between privacy and data utility. For example, masking might be suitable for simple anonymization, while tokenization and generalization offer more robust protection but might require careful consideration of the implications. Specific anonymization techniques are the specific implementation details of the anonymization methods. For example, for masking, you might specify the number of characters to use for masking. Or for tokenization, you might define a specific token generation algorithm. These techniques need to be carefully chosen and implemented to ensure effective anonymization, without compromising the utility of the data. Challenges and fixes. Over-anonymization, where too much information is anonymized, can lead to a loss of valuable data. For example, if all names are masked, it might be impossible to analyze trends related to different demographics. Choosing appropriate anonymization methods for specific data types and intended use is crucial. For example, generalizing the age of individuals to age groups might be sufficient for some analyses. But if the goal is to study the relationship between age and specific diseases, masking or tokenization might be better choices to preserve individual-level data. Data leaks can occur if anonymization is incomplete, leading to the potential exposure of sensitive information. For example, if a unique identifier, like a social security number, is only partially anonymized by removing a few digits, it might still be possible to identify the individual. Thoroughly testing anonymization techniques with various data scenarios is essential. This involves simulating real-world situations and trying to re-identify the anonymized data to identify potential weaknesses in the anonymization strategy. By rigorously testing and improving the anonymization process, the chances of data leaks can be significantly reduced. Langchainexperimental, data anonymizer, base, reversible anonymizer base summarization. A base class that provides the fundamental structure for building reversible anonymizers. Reversible anonymizers are essential for protecting sensitive data while still allowing for its meaningful analysis and use. They achieve this by transforming the original data into an anonymized form, preserving the essential information needed for analysis, but making it difficult to identify individual subjects. The core concept is that the anonymized data can be transformed back into its original form. This allows for data privacy while ensuring the integrity of the information used for analysis. Inputs. The input to the reversible anonymizer is the data that needs to be anonymized. This can range from a simple list of names to complex datasets with sensitive information such as medical records or financial data. The key objective is to process this raw data and prepare it for anonymization. Outputs. The output of the reversible anonymizer is the anonymized data. This data is transformed from its original state to protect sensitive information. The anonymized data preserves the essential features of the original data, enabling analysis and insights while safeguarding privacy. Steps. The first crucial step in building a reversible anonymizer is to implement the anonymization logic. This involves defining the specific methods used to transform the input data into an anonymized form. The method should be designed to effectively conceal sensitive information while maintaining the essential characteristics of the data for analysis. The second critical step is to implement the de-anonymization logic. This logic is responsible for reversing the anonymization process, allowing the retrieval of the original data from the anonymized form. This step is essential for maintaining the reversibility of the anonymizer and ensuring that the original information can be restored when needed. Prerequisites. The LangChain experimental library is a prerequisite for using reversible anonymizers. This library provides the framework and tools necessary for building and utilizing these anonymizers, enabling developers to implement the necessary logic and leverage the capabilities of LangChain for Data anonymization tasks. Fine-tune parameters. The anonymization strategy is a crucial parameter that defines the specific method used to anonymize the data. The choice of strategy depends on the nature of the data, the level of privacy required, and the analytical objectives. For instance, a simple strategy might involve replacing names with random identifiers. More complex strategies could employ differential privacy techniques to ensure that even statistical analyses cannot compromise individual privacy. Challenges and fixes. One of the primary challenges in designing reversible anonymizers is ensuring the reversibility of the anonymization process. The anonymized data should be transformed back into its original form without loss of information. This is crucial for maintaining the utility of the data and enabling its use for various analytical and decision-making purposes. To address this challenge, implement de-anonymization logic that precisely reverses the anonymization process. This logic should be carefully designed to ensure that it can accurately reconstruct the original data from the anonymized representation. Maintaining data integrity during the anonymization process is another significant challenge. This involves ensuring that the anonymization process does not introduce errors, distortions, or inconsistencies into the data. The goal is to preserve the essential characteristics and relationships within the data, even after anonymization, to enable accurate and reliable analysis. Thorough testing of both anonymization and de-anonymization logic is essential to address this challenge. This includes rigorous verification to ensure that the anonymized data is accurate, consistent, and can be reliably de-anonymized back to its original form. This thorough testing helps ensure that the data integrity is maintained throughout the anonymization process.